Welcome to the C++ tutorial of the VR character series. Quickly before we start, I want you to know that if you don't want to sit through hours of tutorial, you can just buy the project template on Fab. It is currently in early access and therefore cheaper. The price will go up eventually when more stuff is added. By showing early support, you are actively helping me make it better. For this tutorial, I assume that you have some Unreal Engine C++ knowledge. However, even if you don't, you can just follow along and you should end up with a working project. Anyway, let's get started. Let's start by creating a new project. I am using Unreal Engine 5.1 for this and the Visual Studio 2022. First, I'm going to name the project. I am just going to call it @VRCar. Just going to abbreviate it and tut for tutorial. Then make sure this is a game and we want to choose a blank project. Then we also want it to be in C++, and for the target platform I'm going to choose mobile and the quality preset as scalable. And then we hit create. Now that everything has loaded, we are first going to go to the project settings. I have this tab by default, but if you don't have it, you can come over here to the right to settings and open the project settings. And also when you create a C++ project, by default your Visual Studio will have opened in the background. So in here, we are going to go to the rendering section. And then in here, we want to disable lumen. So for dynamic global illumination method, choose none. For the reflections, also choose none, or you can choose screen space, but we are going to choose none. And further down in the VR section, where is it? There. We want to disable mobile HDR. Then we want to enable forward shading, so make sure that is ticked. Back in the VR section, we want to enable instant stereo. And then if we come all the way up to all settings, we want to make sure that Start in VR is enabled. One more setting, we want to search for clip plane. And here in the near clip plane, we want to set this value to something like 0.1. Because if it's set out too far and you look down, you can basically look into your own torso, which would be weird. And with this, you can also get closer to like a wall without having your camera clip into the wall. For this to be applied, you need to restart the editor, but we need to do that anyways because of our other settings, so we are just going to restart now. Now that the editor has restarted, we first want to create a new map and save it as our default. We are not going to use this one because it uses this landscape and world data layer thing, and I've had more trouble than success with it. So I'm going to go into the content browser and first create a new folder called maps. And in here I will create a new level. I'm going to call this the playground. Now we can open it, and right now we don't have anything in it. No light source, no skybox, nothing. However, if you go to the top left and click on Window and open the Environment Light Mixer, you can choose a preset here. I'm going to choose Minimal, and then create Skylight, create Atmospheric Light, create Sky Atmosphere, create Volumetric Cloud, and create the Height Fog. Now all of these things are movable. However, since we're in VR, we want the max performance possible. So I'm actually going to change all of this to stationary. This, of course, means that you will have to build the lighting, but it's much more performant when you create a shipping build. Then for the floor, I'm going to use a cube. The reason I'm going to use a cube and not a simple plane is because a plane is two-dimensional and its collision is also very thin, meaning if something hits it too fast, the weapons will just glitch through it. Therefore, we are going to use a cube. I will set it to 0, 0, actually to -50 height, so its top surface is aligned with the grid. And then here in the scale, I'm just going to give it a scale of 100 by 100. This is a bit too bright for me, and actually there is a material in the templates that they use, which I like because it's sort of a grid material. However, before we are going to do that, it's important that we go to the plugins and search for OpenXR and make sure that OpenXR is enabled. You will have to restart the editor once you've done that. before we are going to restart the editor, what we want to do, we want to add the control rig from Unreal Engine because it makes it easier to create animations later, and it also gives us the character that we need for our full VR body. So in 5.1, fab wasn't a thing, so in here you don't have the add fab button, so we can open up the Epic Games launcher. If you already have it, which I'm not sure if it is by default, but you can search for Mannequin Pack, and this is from Unreal Engine. It's also the newest of their mannequin skeletons. If you don't have it, you can simply go on Fab and download it from there. It should be free from what I know. But anyway, let's add it to project, add it to our tutorial, and select add. For some reason, always asks to overwrite the files. And in here now you have the controller characters. Then one more thing I want for the background is a grid material that's from Epic Games because it's really neat. So we're going to add feature or content pack. I'm going to choose the third person. You can choose any, it doesn't really matter. And add the project. Now all we need from this is the level prototyping folder. So you can select the folder's characters and third person, right click and delete. And since we've added the plugin before, we are now going to restart the editor. After a quick restart, you can see we're back on this map, mainly because I forgot to set it in the settings. So in the project settings, come to maps and modes. And in here you have the editor startup map. That's when you start up your editor. And the game default map. This is when you export your game for a shipping build or whatever. So in here, I'm going to get our playground. I'm going to do this for both. I'm going to go to the level prototyping folder, the materials, and I'm going to get the prototype grid gray 2 because it's a dynamic one. I'll show you what that means in a second. Meaning if you move it, you can see the grid stays the same. This is really neat because if you have another cube, for example, put it on there. If you have the normal grid material and you move it, you see it, the lines move with it. However, with this one, the lines always stay consistent. So it's a little bit fancier. We also need a player start. So in basic, go to player start and drag it out into your world. Before we are going to add anything in C++, we're going to create some stuff in the editor that we will need later, like collision profiles and input mappings. So first, let's add the collision profiles. Under the project settings, in the collisions section, we want to add 3 new channels. The first one is called grabbable object, and its default response is block. Accept. Then the next one is called projectile. Its default response is also block. Accept. And then the last one is called menu. This is what we are going to use for our hand menu. And the default response should be ignore. Now in our presets, we are going to add a new one. First one is called grabbable object. It has collision enabled, query and physics. The object type is our created grabbable object. And then we want it to ignore visibility, ignore pawn, vehicle, and projectile. We ignore the pawn and vehicle because we don't want the weapon or whatever we grab to interact with our collision capsule, because this would launch us across the field. And we don't want it to interact with the projectile, because if we spawn a projectile and it hits its own weapon, then the weapon would basically shoot itself. And the menu, of course, we don't want to do anything with the menu other than interact with it when we click on it, so that's ignored by default. Then we can hit accept. Next, we are going to add another preset. This one is called projectile. Its default collision is also collision enabled. The object type is the projectile. And here we also want to ignore visibility, ignore pawn, so we don't shoot our collision capsule or the collision capsule of an enemy. We only want to be able to hit the mesh. Then we want to ignore grabbable object, projectile, and as per default, the menu. Then the last one we are going to add is called menu. Here we only want query collision, and the object type is the menu. Then we want to ignore everything except for other menus. We want to block other menus. This is because we will use this for the widget interaction component, so you can make sure that it only hits menus and nothing else. Then you can click accept. That's it for the collision profiles. Next, we are going to add the inputs. So create a new folder called input. And here I'm going to add another folder called actions. And I will add a input mapping context. So right click, go to input, input mapping context. I will call this IMC default. Now in here we are going to add our input actions. Right click, go to input and add a new input action. I will call this IA change firing mode left. And by default it is a bool. This is okay for this one, so we can leave it and then copy it. And we also want this for the right. Okay, again. Then we are going to call this one IA grab left. Same for the right. Next one is the IA grip left axis. This is what we use to control our fingers. Now this we want to change to a float, axis 1D. Duplicate this, and also do it for the right. Sure to save sometimes, so in case the editor crashes. Duplicate again, IA index left axis. Now since we've duplicated it from here, it's still a float, so this is fine. Then also for the right. For the next one, we are going to duplicate the grab right, or just one of those where we know it's a boolean. And we are going to call this IA interact left. And then also for the right, as usual. And the next one is also type bool is IA jump. Jump. Then we need an input action for moving, so IA move. However, this one is going to be an axis 2D, so a vector 2D. Next one should be a bool again, so duplicate one of those, call it IA release mag left, and then also for the right. Then another bool, IA run. Copy one of the axis ones, call it IA thumb left axis and thumb right axis. Then the last one, also of type float, is IA turn. There you go, that's all the input actions that we need. I know this was a bit crisscross, but I created them in this order because I've created this project before to make sure everything works the way I want it to. And now I'm basically copying it. And instead of just copy-pasting everything, I will just create everything in order. So this way it's a bit easier to track the progress. Great, now we can go into our IMC default, into the input mapping context. And in here, this is where we set up the inputs and which button does what. Here first we are going to select the plus, then select the IA move, input action, and we want to move with our left stick. So for me it's the Oculus touch L thumbstick 2D axis. Make sure you get the 2D axis because if you remember, we set the input value to a vector 2D. Next one is the jumping. So IA jump. We want to jump with the right thumbstick. So for the Oculus, it's just touch R thumbstick button. Then turn. I'm going to show you each one how I do it. Of course, you can assign them to whatever you like. This is just how I do it. For turning, we want to get the right thumbstick. And here we only want to get the x-axis. So thumbstick x-axis. This is the change firing mode right. Change firing mode left. Here we want to get the Y press. Or there should only be the touch controller for this one. Then the same for the right. And for the right, it is the B press plus touch. And I'm only setting it up for Oculus because that's what I have. Then the next one is the release mag left. This is going to be the X press button on touch. And therefore, the next is the release mag right. This will be the A press. Next is the interact left. This is the trigger of the Oculus left touch, and the same for the right. Select right. Next is the grab left, which is the left grip button, and same for the right. Now for the thumb axis, the thumb left axis, we want this to move the thumb every time we touch one of the buttons. So I'm going to add 3 more inputs to this, and here we want the thumbstick, the left thumbstick touch from the Oculus, from L the X touch, the Y touch. And then of course the same for the right. There we go, now we're almost done. Next is the index axis, index left axis. This is when we touch the left trigger, so trigger touch, and then again the same for the right. Then also for the grip axis, grip left axis. This is from the left motion controller, the grip touch. Never mind, sorry, the grip axis, I mean. And I just realized I made a mistake. This shouldn't be the trigger touch, but it should be trigger axis. Because there we want to move the trigger finger, or the index finger, or the also on the grip, we want to slowly move them as you press the button. Here we are using touch because the thumbstick doesn't have an axis when you press it, it's just a individual button. So yeah, that was my fault, and also not Vive, but the Oculus. Left grip axis, the right I mean. And at last, the run. There, and we want the player to run if we press the button that we move, where we move, so the left thumbstick button from Oculus. There we go, that's that. So let's add our first class in C++. By the way, if you don't see this C++ folder, what you can do is come to the right, go to the settings of the content browser, and in here you can show engine content and show all this. Then down here you have the engines. You can go into a C++ folder of the engine, right click, new C++ class. Now if you already have this folder, you can of course do that in there. The first one that we are going to add is just going to be a blank one, because we are going to add some enums. And the reason why I start with this is I've created a structure where I minimize the hopping around between different classes part. So, which is why we will start with weapon enums, then go on to some interfaces, and then so on, because I wanted to avoid hopping between character and weapon class and then animation class and whatnot. So we can first start with classes that have no dependency on anything else, and then build up everything else that depends on those classes. So anyway, let's select none for the next one. And in here, I'm going to call this weapon enum types and select public. So it is generated in the public folder. And which is a bit weird in Unreal Engine. If you want to add this to a custom folder, down here in the path, you simply add the name of that folder. So for this, it would be in the public/enums folder. And now we can select create class. Great, now that that's loaded, we can go into the Visual Studio, reload all, and for the C++ class, we do not need this. We can go here in the private where weapon enum types.cpp is in. We can simply delete this. And however, just deleting it here does not mean that it is actually deleted. To delete it, we need to go to our project folder, source, project name, private, enums, and delete this. To go to the Build.cs file. And in here, we are going to add some modules. This is very important because otherwise there will be missing includes and your code won't compile and it will just give you weird errors. What we want to add is the enhanced input, then the head mounted display, the UMG, this is used for widgets, Niagara, this is used for the particle effects, and the Anim graph runtime. Now we can build this by clicking Control B, or on the top left, on the top you can go to Build and Build Solution. Now you see everything was successful, and I recommend after you add a new module that you go to your project folder, and in here you right click your solution, show more options if you're on Windows 11, and then generate Visual Studio project files. This loads, and then this message will probably show again, reload all, and now you should be up to date. And in our header class, we don't need the core minimal. However, what we do need as an include is the weapon enum types dot generated dot h. For now, it won't find this. This is because this is generated when we compile the code. And this is for the blueprint, so also the blueprints know what types there are. And now we will add the first enum. So we need the enum macro, and in this we want to pass the blueprint type. This means that our blueprints also recognize this enum that we're creating. Then we have the enum, and we call it E for enum weapon melee type. And in here I will abbreviate our name, WMT, and then call it blunt. And for our blueprints, we also need to add a display name so the blueprint knows what it's called. So we will add umeta, open bracket, and then this display name equals blunt. Duplicate this, and then we also want to add sharp. We will use this enum to differentiate between a baseball bat and an axe, whereas the axe can penetrate and the baseball bat cannot. Just to make sure this works, because you can see this has all red lines under it, and it says it can't find it and it's undefined. However, if we compile it, you can see that it actually successfully compiled. This is just a Visual Studio problem, but in the end, all that matters is that it successfully works. So let's add another enum. This is the enum e-firing mode. So we have fm single, umeta display name single. Then we want 3 more. The next one is the semi-auto. The single one is for things like pump action shotguns or bolt action sniper rifles. Just things where you have to manually load the next round. Then semi-auto is, for example, like a Glock, where the next round is loaded automatically. Next is triple or triple fire. And the last one is full auto for full auto. Go, then the next one is the E damage type. So damage type none, umeta none. Next one would be the DT hit. Next one is the DT penetration for like knives. And the last one is the DT projectile for projectiles. Next enum is called emag check result type. We will use this to check if a mag is attached, if it still has ammo and whatnot. However, this is not something that we are going to use in Unreal Engine itself. This is only for us to see in backend. So here we won't use the UMeta tags. So this is just going to be MCRT not attached, MCRT not empty, and MCRT empty. And then the same again, just for the backend, ammo check return type. Here we have ACRT success, ACRT failed, and ACRT mag empty. So let's compile and make sure everything is still good. Next, we are going to add the damage interface. So go to C++ classes, right click, new C++ class, and scroll all the way down in common classes to Unreal Interface and select next. This we will call damage interface. Then in the folder interfaces. Again, very important that you add the folders down here, otherwise moving the classes can be quite a pain. Go, and in our damage interface H, you will have two classes. First of all, you will have the U damage interface and the I damage interface. This U damage interface class, you can just leave this. You don't need to touch it. It's just for Unreal Engine. You don't need to touch this class. Everything will be done in the I damage interface. Before we add our function, we are going to include our enum. Since our folder is one up, we need to add two dots, /enums, then our weapon enum types. And public, we are going to add a virtual void function called damage. And then first we pass the damage type, then how much damage has been applied, so a float amount, and then which bone has been hit, so fname bone name. And now you see you get a green dotted line. You can right click it and go to quick actions, or just press Ctrl dot, and then you can select create definition of damage in damage interface CPP. This you can leave empty. You will implement it in your character that can be hit or whatever. Great, let's compile again just to make sure everything is fine. Now back in the editor, we can actually go and check out our structure here. So interfaces, here we want to add another interface. Again, an Unreal interface. This we will call weapon interface. And in our Visual Studio, we will reload all again. For our weapons interface, we will actually add some includes before we do anything else. Hashtag include animation / animation asset, because we want to be able to get the animation that's used, for example, for gripping the weapon or holding it the main hand. And then include motion controller component. And in the weapon interface.h, we can begin by adding our function. First one is the virtual void fire weapon, then virtual void stop firing weapon, and all of these need to be virtual, by the way. Change firing mode, release mag, pull trigger. This takes a parameter of a float called alpha. We use this to rotate the trigger while we're pulling it. Then we have start moving slide. This takes a parameter of the U motion controller component, MC. Make sure you pass it as a pointer. The next one is the stop being slide. Then we have the move slide function. This is updated every tick, but that's all for later. Again, a U motion controller component, MC, and an F name called slide grip bone. Virtual void set primary hand. Here we pass a parameter controller hand, and we can duplicate this and set secondary hand. The next one, we want to return a U primitive component, get slide component, and then U animation asset, get primary and animation, and then again a U animation asset for the get secondary and animation. Copy this. We want to get the slide grip animation, and at last we want to get the primary hand trigger pulled animation. Select all of it, right click, quick actions, and create declaration / definition. Now in here we should have all of this. Now here you can see that it has an issue with this UMotion controller component, even though we included it here. So what we need to do, back in our .h file, we will simply create a definition. So class U animation asset, class U primitive component, and class U motion controller component. So with this, our code in the H file always knows which class we're talking about. Just make sure that you spell it correctly. That you could, of course, also just add the class down here, but if you have multiple, you would have to add it multiple times, so it's easier to just do it this way. But you still need the include, so this is still very important that you have this. And we don't need an include for the primitive component because it's already part of the engine. I believe it's in the core minimal or somewhere. It's somewhere, so yeah.
The next class we are going to add is the Projectile Base class. So let's create a new C++ class, and this is of type actor. Now I will call this Projectile Base. And I want it to be in the folder weapons, magazines, ammo, projectiles. So this class will be created in the projectiles folder, which is in the ammo folder, which is in the magazines folder, which is in the weapons folder. Let's create the class now. Let's start by adding our includes. So first we want to include our damage interface. So interfaces and damage interface. Next, we are going to include engine content. So that's why I leave a gap here and use different brackets, just so it's a bit easier to distinguish which classes are from me and which are from the editor. So first we want the Niagara systems. Then we also need to include the sound base from the subfolder sound, the Niagara function library, the Kismet gameplay statics. This is what we use to play sounds. Next, we need the Kismet math library, Kismet math library. Then from the component, we need the decal component. From material, we want the material instance, the components, the static mesh component. This will be the projectile itself. And at last, from the game framework, the projectile movement component. Now we can go to the header file. And first I'm going to add the class definition. So class U sound base, class U Niagara system, class U material instance, class U static mesh component, and then U projectile movement component. Now in classes where we have a lot of variables and functions, I will create little categories, so it's easier for me to tell which is which. So on the public, I will write a hashtag pragma region, and then I will call this region variables, then pragma and the region. So this is where the region should end. And then I will do the same for the functions. So here, and you can see now that we have defined this region for functions, if I collapse this, it's collapsed into this tab. So it's just, when you have a lot of stuff, it's much easier to scroll through it. So not everything is always expanded. And then you have to scroll for like, I don't know, 1,000 rows. So this way it's much easier. Well, before we add any variables, we are going to go above public and add a private section. And in here, we want an F timer handle called lifetime EH. This is used for the lifetime of our projectile. If you fire into the air, we want it to despawn after, let's say, 5 seconds, or to explode if it's a rocket. So now here, I will create again a region called components. Again, you don't have to do this. It's just for me, visible anywhere, blueprint, read only, and category components. Now this category here refers to the category in the details panel. So for example, if I select the floor here, the cube, you can see here you have transform, static meshes, materials. This is what these categories refer to. And our first component is the static mesh component. This is the static mesh of our projectile, so let's call it projectile mesh. Then the next component is our projectile movement component. Let's call it projectile movement. Then our next region I will call projectile. So I know all of this is the part of projectile itself. Again, it's just for me. You don't have to do this. Change this from visible anywhere to edit anywhere. And the category I will change to variables and then create this pipe thing and call it projectile. I will call all variables that we can change variables and then projectile. This will create a subcategory. And then our first variable is a float called damage. And let's set it to a default value of 50. The next variable is the lifetime. So load again, lifetime. Let's set a default of 5 seconds. Another float of the decal lifetime. I'll set this to 10 seconds. This is how long the decals, so for example, the bullet holes are visible. You don't have to make this a variable. You can also just hardcode it. I created a variable since I'm going to ship this project, so it's easier for other people to understand. And this way they don't have to touch the C++ side of things. They can just change everything in the editor. Then the next is another float. This is the decal base screen size. I'll set it to 0.001f. This is the size of the decal compared to your screen, as far as I understand it, which if it's below this screen, so if it's really far away and only takes up like 0.001% of the screen, from what I understand, I'm not 100% sure here, but just if it reaches a certain size, it will fade out, so you won't be able to see it. You can set this to something bigger if you want them to disappear faster for performance reason or whatever. This is a value that works for me, so I'll leave it at that. Then the next one is the bool called bIsExplosive. I won't set a default value here. That means it's false by default. We will use this later to decide if it should just despawn or if it should explode in the air. The next is a U-bound base, and this is the impact sound. Next is our U Niagara system, our impact particles. And make sure to also put a U property above it. Then we have our U material instance. This is our impact decal. There we go. Now we just need to add a few functions. First, and these are all U functions, so we can also call it from blueprints if we want to. I'm not going to in this tutorial, but again, since I'm shipping it, I want some functions to be accessible through Blueprint if someone wants to use this class or build upon this class in Blueprints. So U function, blueprint callable, void destroy projectile. And here we want to add a hit result, so const f hit result hit. And we also want to know when the projectile has actually hit something. So U function. This does not need to be blueprint callable since it's an event. And this is void on projectile hit. And here we need a U primitive component. This is our hit component. The A actor, the other actor. And this is a bit weird in our relation. The hit component refers to our component, so the projectile mesh, and not the other component. The other component is, well, called the other comp. So U primitive component, other comp. And it's important that you do it in this order. I will show you why shortly. So then we have the F vector, which is our normal impulse, and the const F hit result, which is our hit. Now let's create these functions. And here we want to make sure that the canEmptick is false. And just to make sure, I will also set this start with tick enabled also to false, just to make sure this actor never ticks. Then we get our projectile mesh, create a default subobject, type U static mesh component. This is what actually creates the component in the editor. And then the projectile mesh. This is just the name that will be displayed in the editor. And you want to set this the root component, projectile mesh. And you also want to make sure it uses the projectile collision profile. So projectile mesh, set collision profile name, projectile. And then let's also create our projectile movement component. So create default subobject, new projectile component, call it projectile movement, and set its initial speed to something like 10,000. Actually, I will create a variable out of this. Let's realize that maybe better. Projectile speed. 10,000. Now in the begin play, this is where we set up the hit event. So get our mesh because we want to set up the hit event based on this component, and then on component hit, add dynamic. This is another weird Visual Studio to Unreal problem. It says it only has an internal add dynamic function, but if we only write it as add dynamic, you can already see it change the color, so it does actually exist. Then input this and a reference to our function. So a projectile base and then on projectile hit. And you see the error disappears. Now I'm going to show you why we need to do this in order, because if we open up this component hit and go to where this is defined, you can see declare dynamic multiclass, sparse, delegate, whatever, 5 params. And here you have first the U primitive component, then what's it called? So here we have our hit component, the other actor, the other component, normal impulse, and hit. Now, for some reason, they've also declared on component hit itself for these other 5 params. Yeah, I'm not too sure why they also added this. I never did that when I created these types of delegates. But if you're never sure about the order, you can just look here and then you know what components you need to pass or what parameters you need to pass. Anyway, after that, we are going to create a new local variable, which is a fHit result called hit. And here we initialize the lifetime timer of our projectile. So we also need an fTimer delegate. Let's call it dt. And then in the delegate, we want to bind U function and put the object this, and then f name and the name of our function, which is destroy projectile. Now I'm going to paste this like this just to make sure that it's exactly the correct name. And then you're going to pass our hit result, because again, if our projectile is still in the air while its lifetime timer has expired, then we don't actually have a hit, but we still need to pass something. So we can just pass this hit and then get our world timer manager, set timer lifetime th, input our timer delegate, and set time to our lifetime. And we don't want it to loop, so false. In C++, you can actually create a timer where you can pass parameters. This, at least from what I know, is not possible in blueprints, so this is really neat to do. Then the tick function, we don't need that since we've disabled tick altogether on this actor, so we can just delete it. And in destroy projectile, here first we want to get the world timer manager and clear our timer lifetime th. Just in case we actually hit something, then we no longer want this timer to expire. So we expire right away, so this function will never be called again when it expires. Otherwise, you will get an error. Then we want to check if our hit that we pass is a b blocking hit, and if the hit component is valid. Get hit component. In theory, the component should always be valid if it's a blocking hit, but just to make sure, because if it somehow isn't through, I don't know, magic, then your whole entire project will crash since it's C++. Blueprints can handle it, but in C++ you have to be more careful and include a few more checks here and there just to make sure that if something goes wrong, that your whole game won't just crash. But if it is a blocking hit and the component is valid, we want to get our U Niagara function library. And in here, we want to spawn a system at location. And first, it wants the world context object, so we will get world. Then for our system template, we will use our impact particles. The location is the hit.location. And for the rotation, we will get the U-Kismet math library. And here we want to make rot from X. And then input our hit.impact normal, meaning our decal will always face the way of the face that it hit. Sorry, not the decal, the system. But same goes for the decal. So actually, might as well copy that. Then next, we want to get the new gameplay statics and play sound at location. Again, get word, input the impact sound and the hit.location. Now, first we need to check if our decal actually spawns successfully. So in a if clause, so u decal component spawn decal equals u gameplay statics spawn decal attached. Then here it wants our impact decal. Then it wants the size of the decal. This is very weird in Unreal Engine. For some reason, if it's below 3, you won't be able to see it, at least from my testing. So we want to get a vector and set it to 3.0. Next, we need the component. So the component to attach to, so hit.get component. Then the bone name, hit.bone name. Then the location, so hit.location. And then the same from before, the impact normal. And then it also wants to know the attached location. So E attach location, E whirl position. And then its lifetime, so decal lifetime. So if this is successful, we want to get this spawned decal. And in here we want to set the fade screen size to our decal fade screen size. There we go. Now, if our hit wasn't a blocking hit, meaning it's most likely coming from begin play and we didn't hit anything and the bullet is still in the air after 5 seconds, or maybe even under the map or whatever, then we first want to check if it is explosive, so E is explosive. Now, if it is, we want to spawn the impact particles, which would be the explosion if it's explosive, and play the sound, which in this case wouldn't be a ricochet, but like an explosion sound. So again, Niagara function library, spawn system at the location, word, impact particles, and get the actor location and the actor rotation. And for the sound, same, do gameplay static. Play sound at location, get word, impact sound, and get the actor location. And if we went through all of this, then we can just destroy the actor by calling destroy. There we go. And now the last thing to do is in the onProjectileHit event, we want to check if the other actor that we hit implements our damage interface. So I damage interface, let's call it DI. Then we want to cast to it. So cast I damage interface from our other actor. And if it does, we want to damage it. T projectile, damage the damage amount, and hit bone name. And then we want to destroy the projectile. Here we can just input the hit. And that's that. Make sure that destroy projectile is outside of this if clause, because if it isn't, then it wouldn't despawn if you hit just a regular wall that doesn't implement the damage interface. But yeah, that's that for the projectile base class.
Next, we are going to add our ammo base class. So make sure you are in the ammo folder, right-click, create a new C++ class, and then create a new actor. Let's call this ammo base. Great, now that we have created the class, we are going to add the includes again. So first we want to include our projectile base that we just created. Weapons, magazines, ammo, projectiles, projectile base. And then we also want to include a static mesh component. And static mesh component. Here we can delete the tick and the begin play functions since we're not going to need them. The same here. And here we are going to have the class definitions for the A projectile base and the U static mesh component. Create my regions again. Now for the variables, we are going to add 2 components. So U property visible anywhere, blueprint read only, and category components. And this is of type U static mesh component, and we will call this ammo mesh. Copy that and paste it again, and this one is the fired ammo mesh. We do this so we don't have to store individually a bullet and a shell mesh. because on a shotgun slug it wouldn't be as easy because a shotgun itself shoots pellets usually, but the ammo is like the red thing where it's just blown out in the front. This is why we distinguish between the ammo mesh, which would be the shell and the bullet on a pistol, for example, and the fired ammo mesh, which would be the shell on a pistol or the blown out slug on a shotgun. Then for the ammo variables, we want this to be edit anywhere, blueprint read only. And here we are going to put it in the category variables and the pipe thingy and ammo. And this is a T subclass of a projectile base. And we will call it projectile class. Based on this ammo class, we then will get the projectile class, which matches with the ammo. And then we will be spawning the projectile based on the projectile class. The next is a float called despawn delay. Let's set this to 5 seconds. This is how long it takes to despawn the ammo after it has been ejected. And then we also want a bool called b was fired. We need this to know if the ammo that is currently loaded has already been fired or not. Then for the functions, we will need 3 functions. First one is called void init despawn ammo, then void despawn ammo, and void set ammo fired. We can generate these 3. Now in here we also want to set bCanEverTick to false and make sure with b start with tick enable this false. And then let's set up the ammo mesh. Create default subobject, use static mesh component called ammo mesh. Set this as the root component. Set root component ammo mesh and set its collision profile to a grabbable object. Set collision profile name to grabbable object. Then for the fired ammo mesh, we can just copy this one since it's basically the same. Then we want to attach it. So fired ammo mesh, set up attachment ammo mesh. This collision profile is also a grabbable object. And at last, we want to set it to hidden, since this should only be visible after the ammo has been fired. So set visibility to false. Then on init despawn ammo, we first need an f timer handle, ph, and then get the world timer manager, set the timer, ph, the object is this, and the function is a ammo base, despawn ammo, delay, it's the despawn delay, and we don't want this to loop. We don't use the begin play function for this, because when we spawn the ammo, it might be still in the weapon and attached to the slide. And at that point, we don't want to initialize the despawning. Otherwise, it would despawn inside of the weapon. We only want to call this and start the despawning after the ammo has been ejected. And in the despawn ammo, we will just call destroy. In the set ammo fired, we want to set the b was ammo fired true. The ammo mesh, we want to set its visibility to false, and the fired ammo mesh to true. The next class we're going to add is our ammo container component. So we are going to add a new C++ class. However, now we want to add an actor component. Click next. Make sure you are in the magazines folder, and we will call this ammo container component. This is our class that we are going to add to anything that can hold ammo in any way. For example, a magazine, a ammo box for the shotgun, or the shotgun itself. And here we do not need the tick component, so we can remove this function. We'll do this in the header file. For the includes, we are first going to include our ammo base class. Include weapons, magazines, ammo base. Then from the engine, we want to include from the components the static mesh component and the instance static mesh component. We use the instance static mesh component to spawn the individual bullets in the magazines. So for example, if you have an AK magazine that holds 30 rounds, with this we can easily spawn all of the 30 rounds without actually lagging the game, because if you spawn them as a static mesh component and you have many magazines lying around, it can get pretty laggy pretty fast. So now in the header file, we are going to define our classes. Class A ammo base, class U static mesh component, instanced static mesh component. The first U property is edit anywhere, blueprint read only, and category variables ammo container. This is a T subclass class of ammo base, and this is our ammo class. From this class, we will get the ammo mesh that we want to spawn. Then the next view property is visible anywhere. This is an integer, and we will call it current ammo count, and we will set it to 0. The next property is edit anywhere again, and this is the max ammo count, and I will set a default value of 10. Then we will be adding a visible anywhere again. This is our use static mesh component, and we will call this mesh ref. This is the reference to the owner of this actor component. So for example, the magazine mesh itself, because we will be using sockets to set the position of the ammo meshes, and this is how we can access those. And then at last, our U instanced static mesh component, which is called stored ammo. Now for our functions, the first one is a U function, blueprint callable, and this is called refill ammo. The next one is also a U function, blueprint callable, void update all ammo instances. The third one has a return type of bool, remove single round, and another bool, add single round. Find those. And in here, can ever tick is set to false again. Also, we start with tick enable is false. Then we have our stored ammo. Create a default sub object. This will automatically add this object to our owner of this actor component. So we don't need to get the owner first and then spawn this component and then attach it. So this will do everything for us. So you instance static mesh component, text, stored ammo. Then we want to set the collision profile name to no collision, because we don't want the spawned ammo to actually collide with anything, neither with the magazine nor with the weapon. And we also want to make sure that set notify rigid body collisions is set to false. This is the onGenerate hit event, if I remember correctly, in the blueprint. And at last, we also want to make sure that set generate overlap events is set to false as well. In the begin play function, I will put this up here. Don't worry about it if it's underlined red. It's just another Visual Studio thing. It will still compile. First, want to check if the owner is valid. So get owner, and if our ammo class is actually set. So ammo class get default object. Both of these are valid. We then can get the root component of our owner. So if use static mesh component root comp equals to cast use static mesh component, get owner, and get the root component. We need to cast it because this returns a scene component. However, in our magazine case or ammo box or shotgun, this is always a static mesh. If this is valid, we can set our mesh ref to this root component. Then outside of that if clause, we can get our stored ammo and attach to component mesh ref app attachment transform rules snap to target including scale. My fault, I said this also attaches it. This is just for creating the component. Down here we actually attach it. Although again, I'm not sure, it may also attach it, but with this we can be 100% sure that it's attached. Then here we want to set the static mesh. We will get this from the ammo class, get default object, and the ammo mesh, and from that we will get the static mesh. And after all that, we can refill the ammo, so the magazines that we spawn are full. In refill ammo, all we will do is set the current ammo count to the max ammo count, and then call the function update all ammo instances. And in update all ammo instances, we first check if the mesh ref is set, and if the stored ammo is valid as well, stored ammo. Then in the stored ammo, we first clear all instances, and then we want a for loop, I equals 0. As long as I is less than the current ammo count, we want to increase I by 1. And now let's create the name of the ammo bone. Ammo bone name, the name of ammo bone. And to that, we will add the f string from int, our index. How all of this works, I will show you later when we create the magazines. Basically, we set up the sockets so we can set the rotation and location of individual ammo, and this just loops through those bones and then spawns the ammo where needed. So if the mesh ref does socket exist. This is important because otherwise it will just spawn the ammo at 0, 0. Ammo bone name. If it does exist, we get this stored ammo and we add an instance. And here we will get from our mesh ref, we'll get the socket transform of the ammo bone name, and the transform space is RTS component. Go. Now only 2 functions left. You can leave the return false, but above it, first we want to check if the stored ammo is valid and if the current ammo count is greater than 0. If it is, we subtract 1 from the current ammo count, and if the current ammo count is less than the stored ammo instance count, only then we want to actually remove an instance from the last index. So stored ammo, remove instance, and this one's an index, so store ammo, get instance count, and subtract 1. This will remove the last bullet. This allows you to have a magazine that, for example, can only show 30 rounds, but actually has 1,000 rounds. And at last, we want to return true. Then for the last function, for adding a single round, we want to check if the current ammo count is less than the max ammo count. And if it is, we increment the current ammo count and update all ammo instances and return true. And just to make sure that the current ammo count is never greater than the max ammo count, we will just set it to the max ammo count in case it is equal or greater than the max ammo count, and then return false. The next class we are going to add is going to be our magazines. So in our magazines folder, we right click and create a new C++ class. This is of type actor, and I will call it magazine base. Now let's add the includes again. So the first one is our created ammo container component, weapons, magazines, ammo container component. And from the engine, we need the static mesh component and the instance static mesh component. Components, static mesh component, instance static mesh component. Now in here, let's define these 2 classes again. So use static mesh component, view instance static mesh component. Now here we can also remove the tick functions because this actor never needs to tick. And let's define some variables. So here we have view property visible anywhere, blueprint read only. Category is components. Use static mesh component, and we'll call this mesh. This is the mesh of our magazine. Another use static mesh component. This is the carry mesh. So this is the mesh that makes it look like it's pushing the rounds up. And at last we have our U ammo container component, which is our ammo container. And actually I just realized I forgot to add it up here. There we go. Now for the functions. The first one is a U function, blueprint callable. And it's void update carry position. Another U function. This is a virtual void refill mag. Next one is also virtual. It returns a bool. This is remove single round. Update all ammo instances. Then we want to be able to get the ammo count. So get current ammo count. And we also want to be able to get the ammo class. So T subclass of a ammo base and get ammo class. Here I forgot to include this. So weapons, magazines, ammo base. Great. Now again, can never tick is false. Same with B start with tick enabled. And first we want to create the mesh. So mesh equals create default subobject. Use static mesh component. Call this mesh. Then set it as the root component. And set its collision profile name to grabbable object. And also make sure that it simulates physics. Great, next we'll do the same for the carry mesh. So carry mesh equals create default subobject, use static mesh component. Then we want to attach this to our mesh. The carry shouldn't have any collision, so set its collision profile name to no collision. And the last component is the ammo container. Now, since this is just a basic actor component, we can't actually attach it, but it will be there. In the begin play, I will move this up here. We will call update carry position. In this function, first we want to check if there is actually stored ammo. So if ammo container has stored ammo, if this is valid, now we want to create the carry bone name. So name carry bone name. This equals fname carry bone, and then we add fstring from int, and we get the ammo container, get the stored ammo, and get the instance count, and subtract 1 to get the index. And if the socket exists on our mesh, we can set the carry mesh to that transform. I just realized it didn't actually. Okay. For some reason, it didn't want to create those. Try again. Nope, it doesn't want to do it. All right, well, then we'll have to do that manually. But we'll do that when we get there. So in refill mag, we will get our ammo container and call refill ammo. And then we want to update the carry position again. Update carry position. Then the next is the bool a magazine base remove single round. First to check if the ammo was removed from the ammo container. So we create a new bool b was round remove. This equals to ammo container remove single round. Then we want to update the carry position and return b was round removed. The next is the update all ammo instances. So void a magazine base update all ammo instances. And here we call the ammo container and update all ammo instances. And again, update the carry position. Update carry position. Then we have our get current ammo count. So int a magazine base get current ammo count. Here we just return ammo container and the current ammo count. And for the last one, which is the subclass of a ammo base, magazine base get ammo class. Here we just return the ammo class from the ammo container. And this is already it for this class. Now let's compile, just to make sure that it still compiles. Failed, let's see why. Okay, not too sure where. Oh, okay, I believe it did that because we auto-generated these classes. So let's remove this again. And actually, yeah, now it should be fine. Okay, now back in the editor, we are going to add another new C++ class, which again is an actor. And this one we will call ammo box base. This is what we use to take out ammo like shotgun shells, for example. So where it doesn't go into a weapon, but we actually want to extract ammo from that we then can put into a shotgun or whatever weapon that uses it. And let's add our includes again. So include weapons, magazines, ammo base, and then our ammo container component. And from the engine, we want the components skeletal mesh component. Here we need to get the skeletal mesh component reference because we are going to attach the ammo that the player is grabbing to the mesh of the player. And so in order to interact with it, we need the skeletal mesh component. And then also the static mesh component. Static mesh component. Now, before we begin, we can get rid of the begin play function and the tick function. Here we don't need to begin play because if you remember, we set up the ammo in our ammo container component. And the reason that we needed the begin play function in our magazine was because we needed to update the carry position. Now in the header file of the ammo box base, we are going to add the class definitions again. Class a ammo base, use static mesh component, skeletal mesh component as you ammo container component. Then the first view property is visible anywhere, blueprint read only, and category components. This is the use static mesh component. This is the mesh of our ammo box. Then the next one is the a ammo base. And this is a reference to our spawned ammo. We use this because if we let go of the ammo, then we want it to return to the ammo box without just falling on the ground. So we need to know which one this belongs to. And then the last one is the U ammo container component. The ammo container. Now for the functions, we have a U function blueprint callable. This returns an A actor, take ammo, and here we input the use skeletal mesh component, character mesh, and a bone to attach to the const f name bone to attach to. The next U function is the return ammo, so void return ammo. And the last one is the clear spawned ammo. We will use this function after putting a shell into the shotgun, so this reference is cleared and the ammo is despawned without returning to the ammo box container. So for take ammo, first we want to check if our spawned ammo is valid, because just due to simplicity reason, we are only going to make it so you can only take one ammo out at the time. So return null pointer. This is so after we try to take some ammo, we know that no ammo was taken. Then if the ammo container can remove a single round, I just realized I forgot to do the constructor setup. I will get that after this function. So if we can remove a single round, we want to create f actor spawn parameters. I'll call this ASP. In this, we want to set the owner to this, and we want to set the spawn collision handling override e spawn actor collision handling method always spawn, no matter of collision. This will make it so the actor will always spawn, no matter if it collides or not. Then we will spawn the ammo. Spawned ammo equal get word spawn actor a ammo base, and here we input the ammo container ammo class. The transform doesn't matter since we're going to be attaching it later. F transform plus an empty transform and our spawn parameters. Then we check if the spawning was successful, so the spawned ammo is valid. We will create F attachment transform rules, a E attachment rule. Here we want to snap to target, because if we look at this, here we can input a location rule, rotation, and scale rule. And we want the location and rotation to snap to it, but keep the scale. Since our character mesh may be scaled depending on the player's height. Copy this, and then paste, and change this to keep relative. And weld simulated bodies, set this to true. Now we can actually attach the spawned ammo, so attach to component. Here we will get our character mesh, input the ATR and the bone to attach to. Then in the spawned ammo mesh, here we want to set the collision response to all channels. So set collision response to all channels to ECR overlap, since we don't want it to collide with anything and only overlap with the hitbox of the shotgun. And then the same for the fired ammo mesh. Set collision response to all channels. Since this is hidden, it still can collide. And then we return the spawned ammo. There we go. Now let's go to our constructor, and as always, turn this to false and turn off the start with tick enabled. The mesh is create default subobject, static mesh component. This is the root component. And mesh set collision profile name to grabbable object, and also make sure it simulates physics. So set simulate physics true, and then also create the ammo container. Now we only need to implement the last two functions. So return ammo is if spawned ammo is valid, then the ammo container should add a single round, and clear spawned ammo. And in clear spawned ammo, if the spawned ammo is valid, then we want to destroy this. So spawned ammo destroy, and after that we want to set the spawned ammo to null pointer. That's it for this class. Next, we are going to create our first weapon class. This is of type actor, and it is in the weapons folder, and I will call this WeaponBase. This is our base class for all of our weapons. In here we will handle blunt hits and sharp penetrations, and it will have the basic hit logic for any type of weapon. So first we want to include our weapon interface, so interfaces, weapon interface. Then from the engine, we want to include a bunch of things. First being the Niagara system, system.h. Then the sound base. Next being the gameplay statics, net gameplay statics. The Niagara function library. A box component. This is what we use to check if it is overlapping a penetrable actor. We also want the Kismet map library. Then you also want decal components, so we can indicate where we've hit something. Components, decal component. Then a material instance, a static mesh component, from components. And lastly, from the physics engine, the physics constraint component. And here we will leave the tick function because we will later use it in the projectile weapons class. So in the header file, we will define our classes again. Class U box component, class U Niagara system, U material instance, U static mesh component, and the U physics constraint component. Now, to implement our interface, here where it says public actor, which is our parent class, we can add another comma and public I weapon interface. And first, we will add some components. So U property visible anywhere, blueprint read only, and category components. This is a U static mesh component, and we'll call this weapon mesh. Copy all of this. And this I will call blade mesh, because with these two meshes, for example, if you have a knife, you can do a blunt hit if you hit someone with the handle. And here with the blade mesh, you can do a sharp hit. And the next one is the U physics constraint component. We use this to get the blade stuck in the object that we've penetrated. Call this penetration constraint. The last component is the U box component. This will call the penetration hit box. Now we are going to add some melee variables. These properties we want to be edit anywhere, and the categories variables and the pipe thing and melee. First one is the damage, so float damage, and I'll set a default value of 10. The next is the linear breakable. This is how much force is required to break our penetration constraint. Next is the hit rate, which determines how fast we can hit something. So let's do 0.2. This is necessary because otherwise we would basically be playing the hit sound, spawning the particles, and spawning the hit decal every tick, or just every time there is a hit without any cooldown. This is why we use a hit rate. Then we also need the last hit time, and actually this can be visible anywhere. We'll set a default value of 0. Then we also want to be able to set the minimum speed required to actually penetrate something. So min penetration speed, I'll set this to 200. and 200 means 200 units per second or 200 centimeters, so 2 meters per second. The next one is a visible anywhere. F name penetrated bone. We want to store this value because if the penetration constraint is broken, but the knife is still inside of the object, we want to set it again. So it's constrained again, and that's why we need to store the penetrated bone and also the penetrated actor and the component. Then the next property, which is also visible anywhere, is the A actor. This is the overlapped penetrable actor. It's the actor that we can penetrate because we will be determining this by a actor tag. So we don't just want to be able to penetrate anything. And the next one is the U primitive component, which is the penetrated actor. The next one, which is edit anywhere, is a T Enum as byte, and it's a E weapon melee type. And I just realized I forgot to include this. So here we want to include, go a step back, enums, weapon enum types. And here we also want to include the weapon interface. So interfaces, weapon interface. There we go. Now we can set this the weapon melee type. If we open this, you can see the default is WMT blunt, so that's fine. This is supposed to be edit anywhere, and in the category SFX, this is a U sound base. This is the hit sound, and the next U sound base is the penetration sound. Next, we will be adding a VFX, also editable anywhere, and here we have a U Niagara system, which is our hit effect, and another U Niagara system, which is our penetration effect. And the last region is for the decals. And before I forget it, let's also change the subcategory here. Here we have a U material instance, which is the hit decal. Then we have another U material instance, which is the penetration decal. And all of these are supposed to be edit anywhere. And then we have the decal lifetime, which I'll set to 10. And another float, the decal fade screen size, which I'll set to 0.01, the same as we did with the bullets. And the last region is the animations region. Here we have a new animation asset. This will call primary hand animation, and then the same for the secondary hand. This way we can set individual animations when you grab something. If you leave them empty, then we will just use the procedural hands to grab onto something. But since that is less accurate than actual animations, this is why we also want these. And this also makes it easier to handle it in the animation blueprint, because then we don't have to add another enum for every individual weapon. And this way we can just add the animation, and that's fine. Okay, now all we need to do is to add the other functions. First, we are going to create a U function. However, this won't be blueprint callable because it will be an event. This is void on constraint broken, and the input is an int broken index. This is the index of the body, but we won't really be using that. It's just what we need to bind the event. Next is void deal damage. And here we input a U primitive component. This is the component that we hit. Then the E damage type, which is the damage type, and the bone name, an F name, bone name that we hit. Next, we want a function to spawn all of the effects. This is a void spawn effects. First, we input the sound, so U sound base SFX. Then the U Niagara system. This is the VFX. Then the U material instance. This is the decal. Then next we are going to add a U primitive component. It's just the comp, F name, bone name. Here we will set a default value of name none. Then an F vector, which is the location where we want the systems to spawn. Here we will set the default value of F vector 0 vector, and then the same with the impact normal, so we can duplicate this and call this impact normal. There we go. Next, we are going to add another U function, which is also an event, so we don't need to pass anything. This is the on blunt hit. And here we input a U primitive component, which is the hit component, then the actor, which is the other actor, then another U primitive component, which is the other component, and an F vector, which is the normal impulse, and at last a const F hit result hit. And I'm going to copy this and paste this again. Also make sure that this is a U function. And this we will call OnSharpHit. Then we only need the begin and end overlap events. So again, U function, void on penetration begin overlap. It wants a U primitive component, which is the overlapped comp, then the other actor and the other component, and an integer, which is the other body index, a bool from sweep, and the sweep result, which is again an F hit result. And we can pretty much duplicate this for the end overlap function on penetration end overlap. And here we don't need the hit result and the from sweep. That's it for that. And then we only need two more functions from the weapon interface. These are functions that we are going to override. So virtual U animation asset get primary and animation. Override, duplicate this, and here we want the secondary hand animation. Great. So now we can select them and create the declarations. And now in our C++ class, we can go ahead and do the rest again. Here we want to leave can ever tick to true. However, we want to set the B start with tick enabled to false. This is because a melee weapon itself doesn't need to tick. However, a projectile weapon will tick when firing, for example, when it wants to triple fire or fire automatically. This is why we want the actor to be able to tick, but not to start with it. Great, now we can create a weapon mesh. A weapon mesh equal create default subobject, use static mesh component. And this is the root component. And we want this to be a grabbable object. So weapon mesh set collision profile name to grabbable object. We also want the weapon mesh to simulate physics. So set simulate physics true. And we also want this to generate hit events. So set notify rigid body collisions to true and disable overlaps just for performance reasons. Since we don't use it, generate overlap events to false. Great, now we can basically copy this and then change the weapon mesh to the blade mesh. So make sure to change the name here. And then of course we don't want this to be the root component, but we want the blade mesh to attach to the weapon mesh. So set attachment, weapon mesh, there we go. You can press your left Alt key and then select multiple rows to paste multiple rows at once. And here we don't need to specifically set simulate physics to true because it's a child item of the weapon mesh and this already has set it to true. Then the next thing is the penetration hitbox. Actually, here we paste this again, change this to a U box component, the penetration hitbox. This we will attach to the weapon mesh as well, or you can also attach it to the blade mesh. That doesn't really matter. However, here the collision profile name should be overlap all. It doesn't need to simulate physics, and we don't want it to generate hit events. However, we do want it to generate overlap events. Make sure that is set to true. And at last, we need the penetration constraint. Create default subobject, U fix constraint component. This we will attach to the weapon mesh as well. And here we want to set all of the linear and angular limits to locked. So here we have set linear X limit LCM locked and 0.0. You can just duplicate this 2 times and change this from an X to Y and Z. Now for the angular constraint, we get the penetration constraint and set angular swing limit 1 to ACM locked, also 0.0. Duplicate it twice, swing limit 2, and the last one is the twist limit. And also very important, we want to set the collision disabled between the two bodies that are constrained. So set disable collision true. There you go. That's the constructor setup. Now in the begin play, we can bind the events. Here we will get the weapon mesh and on component hit, add dynamic, this and a weapon base on blunt hit. And now we are going to add a switch. Here our switch case is the weapon melee type. So here we have our first case, WMT blunt. The break case, and then second case is WMT sharp. Now we are adding this so we can remove unwanted components so they aren't cluttering up our actors when we are playing. So here we will get the blade mesh and we want to destroy this component since it's a blunt weapon. So the blade mesh component, we don't need it. Then here we have the penetration hitbox. Since a blunt object can penetrate, we also destroy this component and the penetration constraint as well. Now in case it being a sharp object, we will get the blade mesh and we will set the on component hit events to add dynamic, this and a weapon base on sharp hit. Then the penetration hitbox. Here we have the on component begin overlap, add dynamic, this and a weapon base on penetration begin overlap, and then the same for end. Also make sure that you get the on component end overlap event. And for the penetration constraint, here we will set the linear breakable to true and to our linear breakable variable. And at last the penetration constraint again. And here we will add the event on constraint broken, add dynamic, this a weapon base on constraint broken. There we go. That's everything for the begin play. Then the tick we will just leave empty. And in the on constraint broken, we want to first check if the penetrated component is still valid. I just realized this is not the penetrated actor, but the penetrated component. There we go. Now if this is valid, we get the penetration constraint. And we will just simply set the constraint components to the blade mesh. Name the bonus in name none. And then we input the penetrated component for the second component, and bone name 2 is the penetrated bone. Now for deal damage, we will first check if the input component is valid. So component, and if get world time since last hit time, this is greater or equal to our hit rate. This will check if the last time that we've hit something is greater than our hit rate, so we can hit again. The first thing we'll do, we'll set the last hit time. You get world, get real time seconds. And then we want to check if the object that we've hit implements the iDamage interface, which I believe I forgot to add. Yes, I did. Includes interfaces damage interface. And here iDamage interface t equals to cast iDamage interface. And here we want to cast the component and then the owner of the component. So get owner. Oh, and make sure that this is a pointer. We will get the DT, the DI. Actually, I should name it damage interface. Don't know why I named it. So DI damage and the damage type, damage, and the bone name. Next, we are going to spawn the effects. First thing we want to do is check if we are actually past the hit rate. And if we are, we first need to get the new rotation. And since we use this multiple times, I'm going to save this in a local variable. So f rotator, new rotation equals to u kismet math library make rot from x. And here we want the impact normal. The new rotation dot roll should be the same as the negative of the weapon mesh roll. This is something I found out through trial and error, because otherwise the decals had some trouble spawning correctly. So first we will play a sound. So u gameplay statics, play sound at location. Here we have our get world first, then the sound effect, so SFX, and the location. Next we want to spawn the Niagara system, so Niagara function library, spawn system at location, get the world, input the VFX, the location, and the new rotation. Then we will spawn a decal, and to make sure that the spawned decal is valid, since we need to set the fade screen size like we did in the projectile, we will first create a pointer to U decal component, which is our spawned decal. This is equal to U gameplay statics spawn decal attached. Here we will import the decal. Size again is f vector 3 at the minimum. Then we input the component, the bone name, location, the new rotation. For the E attached location, we want to keep world position, and then at last the decal lifetime. Now, if this is true, we have the spawned decal, and from here we will set the fade screen size to decal fade screen size. On the blunt hit, we first want to check if getOwner is valid, because we don't just want weapons lying on the floor and then enemies tripping over them and dying because of it. And then next we want to check if the penetrated component is invalid, and if the weapon mesh getPhysics linear velocity size is greater than our minimal penetration speed. If all of that is true, then we can set the penetrated component to our other component, the penetrated bone, to the hit.bone name. Then the penetration constraint. Here we can set the constraint components to the blade mesh. The bone name is name none, and to the penetrated component and the penetrated bone. And then we will call spawn effects. Here we will input the penetration sound, the penetration effect, the penetration decal, then for the component the other component, hit.bone name, hit.location, and hit.impact normal. And then we want to deal damage for the other comp, DT penetration and the hit. Oh, actually, I mind this is DT hit. Here we have the hit sound, hit effect, and hit decal. My bad. And here, of course, if you press Control X, you can cut it out. That was my fault. We will need it down here on sharp. Now here for the sharp hit, if the overlapped penetrable actor is valid and the weapon mesh has exceeded the minimal penetration speed. Actually, let me change the name of that. Press Control and then double tap R to rename this, and I'm going to change this to minimal damage speed, so it's a bit more general. Save this as the header file as well. So if this is also true, then here we want to insert our penetrated component and set all that, and then we can also copy paste this and just change it from hit to penetration. Go. The penetration. Now all that is left are the overlap events and the animations. So for the begin overlap, first again check if the owner is valid, and then if the other actor has tag, here we want it to have the tag penetrable, and if the other actor does not equal the owner, because we don't want to stab ourselves. Then we can set the overlapped penetrable actor to the other actor. Now in the end overlapped event, we first want to check if the other actor is equal to the overlapped penetrable actor, because we don't want to unset that value if we just stop overlapping anything. We will set the overlapped penetrable actor to null. The penetrated component as well is also a null pointer. The penetrated bone is named none, and the penetration constraint, we can just simply break this, because if you remember up here in the onConstraint broken event, it will first check if this is valid, which it no longer is, so it won't reset this constraint. And for the animation asset, we will simply return the primary hand animation, and for the secondary one, so secondary hand animation. There we go. That's it for the weapon base class. Now let's compile and see if everything is still fine. So everything was successful. Great. Then the next class we are going to add is part of the VR character. Now we won't be implementing the whole class, because there are some classes that we need to create to be able to finish this, but we will just create whatever we can for now. So I will call this the VR character. I will put it in the public folder and then create it. And as usual, let's start adding the includes. Now, some includes I will comment out for now, just because we don't have these classes yet, but this way they are here, and so it's easier for me to implement them later. Include VR save game.h, and the next is the include weapons, weapon base, include weapons, shotgun base. Then we have include widgets slash and menu widget. Duplicate this, and here we have the settings menu widget. And we have the interfaces, weapon interface, weapons, magazines, ammo box base, and the ammo base. And the next includes are the engine includes. Here we want the enhanced input library, the Kismet animation library, camera component, which is in the folder camera. Then we have the Kismet gameplay statics, Kismet math library components, and then scene component, motion controller components, then the widget component. We also want a spline component, capsule component, spline mesh component. Also need a skeletal mesh component, a physical material from physical materials. Here we have physical material. There we go. We will use that for sliding while climbing. Then the widget interaction component. Then we have the game framework. Here we will get the character movement component. Then the physics engine, physical animation component. And at last, from the physics engine, a physics constraint component. There we go. That's all the includes that we need. And now we can go into the header file. In here, we want to make sure that we include the enhanced input component. And we also want to include the input action. If you add includes in the header file, you have to make sure that this .generated.h include is always on the bottom, because otherwise it will throw an error. This always needs to be included at last. So now let's add our class definitions. We have class u VR save game, class u hand menu widget, u scene component, u widget component, the u camera component, a weapon interface, u spline component, the u spline mesh component, u motion controller component, u widget interaction component, u physical animation component, and the u physics constraint component. There we go. And next, we are going to declare a delegate. We can do this by calling declare dynamic multicast delegate, and you want one with 3 params. This is the same as these on begin overlap or on hit events. This is how they are defined. However, we want an F and animation changed. Then we have our U animation asset. And here you don't set the type and then directly the name. Here you have to set the type, then a comma, and then you add the name. I'm not sure why it is like that, but that's how it is. So I will call this hand anim asset. Then the next param is the U animation asset again, which is the trigger anim asset. And at last we have a bool, which is b mirror animation. We pass this bool because all the animations that we will be creating, for example, for holding the weapon, will be for the right hand. And then we can simply set this to true, and then it's automatically mirrored for the left. And for the grip, it's inverse. So grip animations are usually animated on the left hand, and then it will be mirrored to the right. This way we only have to create every animation once, and it just makes it easier. Next, we are going to add some enums. So u enum blueprint type, so we can call it in blueprint as well. Enum e turn style. TS snap umeta set the display name. I will set it to snap, duplicate it twice. Then the next one is the smooth, TS smooth. And the last one is the TS max. And here I don't add an underscore because there is already a TS max defined enum somewhere in the Unreal Engine, so there would be compatibility issues because it already has one that has that name. And I will call this max. We will use this to know which is the last element from this enum, so we can, after we've set it to smooth, we can automatically go back to snap. And of course, you could just check if you're at the smooth one, but if you want to add your own later, this way you have a dynamic way where you don't always have to remember which is the actual last item, and you can just use TS max. Then for the next enum, this is the E movement direction. Here we want to set what is used to decide the movement direction. So first one is the MD controller. So if you want to move where your controller is pointing, and the other one would be the camera. And here again, we also need the max. Great, now let's add a private section. And in here we will define a struct f enhanced input action value binding. This is the move action binding. This is so we can get the current value of our movement input, so we can decide if the character can run. So for example, if the y-axis of this binding is negative, we cannot run because that means we are moving back. Then next we are going to define some names. F name, first one is the right hand bone. I defined this here, so in case your bone names change for whatever reason, you can only have to change it here and you don't have to search through the whole code and change it at multiple places. And or duplicate this and do the same for the left hand bone. Then the next one is the right ammo bone. This is where we want to spawn the grabbed ammo. For example, if you grab a shotgun shell out of the ammo box, ammo underscore bone underscore R. You can name this whatever. You just have to make sure that you name the socket the same when you add it to the character mesh. Left bone, ammo, bone, L. There you go. That's all the private stuff. And then I will take these two and move them up here because they're also public. And yeah, I don't know why Unreal Engine splits this up by default. And here I'm going to add my regions again. And now we can start by adding the components. First, a U property, visible anywhere, blueprint read only, and category components. First one is the U scene component. This is a VR origin. Copy the U property, and this is a U camera component. This is our camera. Next, we have the U motion controller component, which is our RMC for right motion controller, and then the same for the left LMC. Then we also want a right and left physics constraint, so U physics constraint component, RPC, LPC. Then we have our U physical animation component, which is our physical animation. We have our U widget component, which is the hand menu. U widget interaction component, which is our widget interaction. Then we need a U spline mesh component, which is our laser pointer line mesh. Well, I just realized I forgot one. And this is the U line component. This is our laser pointer spline. There we go. That's all of the components. I'll leave it open actually so I know which one I've done. Now down here, we change the U property to edit anywhere and the category to variables and the pipe thing and enhanced input. And this is our U input mapping context, IMC. These are all of the inputs we will be setting in the blueprint class. Then we have our first U input action. This is our IA move. Then another U input action. Copy all of this since we're going to need it a few times now. This is the IA turn. Then we have IA jump, IA run, IA interact right, and IA interact left, IA grab right, then also left. IA release mag right, IA release mag left, IA change firing mode right, and same for the left, change firing mode left, IA thumb right axis, thumb left axis, IA index right axis, index left axis, IA grip right axis, and at last the IA grip left axis. Right, now we can go on to the movement. These are also edit anywhere and variables and then movement. Copy that. First one is a float, the base prone speed, which I will set to 50. Next would be the base crouch speed, which is 100, and the base walk speed, which I'll set to 150, and base run speed, which I will set to 300. We want to be able to control the base step height, which I will set to 45. These, by the way, or especially for the base step height, this is the default value that's also set by Unreal Engine. The reason why we store this in a variable is because we will be changing that. For example, when you start climbing and you still have this at 45 in the character movement component, there will be snapping. So as soon as you're above this threshold, you will snap upwards to the position where you're actually climbing at. And if you get too close to the ground, it will just snap it to the ground. This is why we will be setting this to 0, the one in the movement component, and store the base value in this variable. So as soon as we stop climbing, we can change this back to our base step height. Then we have our crouch ratio. Crouch ratio is, I will set to 0.6. This determines the height ratio of which the character will consider itself to be crouching, and anything above would be standing. Then we do the same for the prone, so prone ratio. This I will set to 0.3. Next bool B is running. Then we have an F vector, previous camera location. We will use this for velocity calculations, which we will then use in our control rig for the procedural walk animation. F vector camera velocity. Next one should be edit anywhere again. Here we have our turn style, so T enum as byte, E turn style, called turn style. Same for the movement direction, T enum as byte, E movement direction. Here for the turn style, the default will be the snapping, and for the direction, the controller. That's that for the movement category. Next, we get to grabbing. Here we are going to use visible anywhere, the grabbing category. First is the A actor, the right grabbed actor. These are our references to the actors that we have grabbed, so we always know if we are currently grabbing something. For the left, next one can be edit anywhere. The float, this is our grab radius. I will set it to a default of 10. The bool, which is B, is right main hand, and the same for the left. We will use this bool to check if we are holding the handle of a weapon, because if it is the main hand, then we are supposed to be able to fire. With this, we prevent grabbing the weapon with, for example, our secondary hand, which for me is usually the left hand, but then still be able to fire the weapon from there. Then the last one is edit anywhere again. And here we will set an array of all the object types that we can grab. So T array, and here we want an T enum as byte, the E object type query enum, and we will call this grabbable object types. And here I will set a default value of object type query 7. This is by default our grabbable objects. If you want to know which value your custom object types are, if you select anything and scroll down into the collision presets and you set it to custom, you here have object types. So, and here you can see 1, 2, 3, 4, 5, 6, and then 7, 8, 9. So that's where I got this object type query 7, 8. And here you see 1 is world static, 2 is world dynamic. So that's how you can find out which one is yours. Next, we will go to the climbing. We have edit anywhere again. Climbing can climb. And I will set this to true by default. Here, if you disable this, then your character won't be able to climb at all. I added this so if someone gets the project on Fab, but he doesn't want his character to be able to climb, he can just disable it altogether, and then he won't have to worry about it. The next one is another bool. bIsClimbing right, and then the same for the left. bIsClimbing left. Don't need to be editable anywhere. This can be visible anywhere. Next one is a float, which can be edited anywhere just for debug purposes. We have climbing body z offset, which I will set a default value of 0.0. Here we have another float, climbing offset lerp speed, which I will set to 2.0. This determines how fast our climbing body z offset changes, because if we start climbing, then we want our collision capsule to shrink down into a ball, so it's easier to climb up on ledges. However, we need to offset the mesh then, because otherwise our camera would no longer align with our head, so we need to move it down. And for that to not happen instantly, also for the collision capsule not to collapse to a ball instantly and then back to your height when you stop climbing. This is why we want to lerp that. Then next we have our climbable object types. So t_array, t_enum as byte, and then e_object type query, climbable object types. Here I will set a default value of the object type query 1 and object type query 2, which, if I'm not wrong, should be the static and world dynamic. And then next we are going to add a bool, which is also edit anywhere. Can slide down overhang. I will set the default to true. This determines if you are climbing up an overhang and it uses a slippery material, do you just slide straight down and then start to fall, or can you slide along the edge? Next we want can launch character. We'll also set this to true. This will determine if your character will keep its momentum after launching off of an edge. If this is disabled, your character just stops in air and then just starts falling. But I still want to add it as an option, because maybe you don't want your character to launch. So yeah, this way you can still change that. And next we have the can slip while climbing. Set it to true. If you have a mesh that you can climb on, but you don't set any physical material to it, it uses a default friction of 0.7, which is just from the default physics material from Unreal. And maybe you don't want your character to be able to slip at all. So instead of having to change every physics material on every material that is used in your game, you can just untick this and then you won't be sliding anymore. Then the next property is visible anywhere. This is a float called current slipping speed. Then next property is also visible anywhere. Actually, the next few are going to be visible anywhere, so I'll copy this. Hit result latest hit, and then a hit result for the previous hit. We will get to that when implementing it. These hits are when we are sliding and we transition from one mesh to the other. Then we have an F vector, which is our MC for motion controller start location. We will always only be able to climb with one hand at a time. If we are climbing with the right, for example, and we grab onto something that we can climb on with the left hand, the right will basically let go. So this is why we only use one of these variables and not one for the right and the left. After that, we have the F vector, which is the previous MC location. This is used to move the character and at the end calculate the speed at which you launch off of the edge. Another F vector, which is the sliding start normal. Then the next vector is our climbing offset. And at last we have an F quad. This is our last climb actor quad. We will use this to rotate with an actor. And the climbing offset is, for example, if we grab an actor that's rotating or a skeleton mesh, we still have the offset to the bone, because as soon as it's moving, things can get weird. So we always need to remember these positions. And we use a quad and not a rotator, because with rotators, you have the issue that when you get to 360 degrees and it goes back to 0, there's sometimes a weird rotation offset, and I've only been able to fix that with an F quad. Next we have the character. Here again, visible anywhere, variables and character. Then we have a float. Actually, I want this to be editable anywhere. And this is our base height, which for me is 191. Here is just your height in centimeters. Then the next property is editable anywhere, so edit anywhere. Next viewer, so I'm going to copy this. Then we have a float body z offset. This is editable, so you can debug it easier. Then we have a float the body camera offset. Next we have the recoil. Here we have a visible anywhere, and category is recoil. Net vector right recoil offset, then the same for the left. We have a float, which is the right recoil pitch, and another float for the left recoil pitch. Then we have our recoil lerp timer interval. Set it to 0.1 to make this editable anywhere. The next one is also edit anywhere. This is the recoil lerp alpha. This is how fast we lerp. And I use a lerp timer, so this is only lerping while we are actually applying recoil, so it doesn't have to run into the tick. Next is a visible anywhere property again. Here we have the F timer handle, which is our right recoil th, and the same for the left. The next ones are all going to be visible anywhere, and let's call this category fingers. First, you have a float of our right thumb axis value. They all have a default value of 0.0. Copy all this, duplicate it, because it's the same for the left. Then we have the same for the left index, for the right and left index, and for the right and left grip. We will be using these values to set the procedural finger position in the animation blueprint. For the interfaces, these are also visible anywhere. And first we have a T script interface, I weapon interface. This is our right weapon interface. And then we do the same for the left. There we go. And at last, the events. Here we have view property, category events, and this one. These are also visible anywhere. Here we have the F hand anim changed, animation changed. Actually, we'll rename this to anim just so it's a little bit shorter. But of course, you can leave it. It doesn't really matter what you name it, as long as it doesn't already exist, I believe. And I will call this on right hand anim changed. We compile it should still, no, it does not. Typos, of course. Where this is always important to always make sure that you type this stuff correctly. Now let's compile again. There we go, success. So this is just another Visual Studio thing. Copy this and then have on left hand anim changed. And that's it for all of the variables. Now you can go ahead and define our functions. First, I will start in the general section. The first function is going to be static, and it returns an F physical animation data type, and I will call it get physical animation settings. If you know how to, you can also just set up a physical animation profile. I'm going to use a settings function, which will simply just return a F physical animation data struct. I'll call it pad, and here we will set all of the parameters. So if you want to use the same animation data multiple times, you can just call this function and you don't have to duplicate anything. So all you have to do is change it here if you want to in the future, and then it's changed everywhere. First, b is local simulation equals false. Then this orientation strength, I'll set it to something like 5,000. Then the angular velocity strength, I'll set it to 500. The position strength to 5,000, the velocity strength to 500, max linear force to 5,000, and the max angular force also to 5,000. These are just values that I chose through trial and error. It's what works for me. Feel free to play around with them. And then we'll simply return the pad. Next, we want a function to get the height ratio. This will be float get height ratio. And we want to be able to calculate the floor level. So float calculate floor level. And here we want to be able to input the body Z offset and the climbing body Z offset. So first we'll add a float parameter, body Z offset value. I will call it value because we already have a body Z offset variable. And I will set a default value of 0.0, so we don't actually have to pass 0.0. We can just leave it empty if we don't want to add any body Z offset. And then here another float, climbing body Z offset value, also a default value of 0.0. Then the next function is going to be void update VR collision and void apply height. We will get to the implementations shortly after we've created all of the functions here. Next we have the calculate height. Then we need a function to initialize the physical animation, so init physical animation, and then also want to enable it. Enable physical animation. Next is going to be a U function. This is called on settings applied. We will use this to apply our settings, but we will get to that later when we create the settings menu. And then also a void load save game. That's it for the general region. Next we have the movement inputs. Create a void move function, and the input for this is a const f input action value. And next we want a stop moving, so stop moving, and then it's always the const f input action value. This is required so Unreal Engine can map it to our inputs. Then the next function is a void update movement speed. This is the only regular function that doesn't need the input. Then the turn, snap, turn, since we want multiple ways to turn. Then we have the try jump function, and I call it try jump because there is already a jump function from the character. That's why I named it try jump. Run, and at last the void calculate camera velocity. Let's continue on to the grabbing section. Here we have void start grabbing, which again has this f input action value. I meant to write start grabbing right. Then we have update grabbing right, and at last stop grabbing right. And then we can copy paste these and rename them for the left. Then we want a return type of a actor and call this function start grabbing. Here is our actual grabbing function. We use the start grabbing right and left only to pass the correct parameters to this function. So all of the logic is here in one place. The input parameter for the start grabbing function is a U physics constraint component, the PC, F name, which is the bone to constrain to. Then we need an A actor, which is our other grabbed actor. Then a U motion controller component, DMC. Then a bool that we pass by reference, which is called bIsMain hand. And another regular bool, bIsOther main hand. Then we are also going to create a function for update grabbing. Here we want a actor, grabbed actor, a bool bIsMain hand, a U physics constraint component, the PC, and a U motion controller component, the MC, and at last name bone to constraint 2. Last is stop grabbing, which wants an U physics constraint component, PC, a actor, the grabbed actor, and another a actor, which is the other actor. Then we need a function to release the grabbed actor. This we use when we insert a magazine into a weapon and it snaps to a weapon. We want the weapon to tell the owner of the magazine, which would be the player, to let go of the magazine. That's why we need this function. And here we have a actor where we pass the grab actor. And to check if we are hitting something that we can grab, we want to create a function that returns an F-hit result. And the function is called trace for objects. And the input parameters are a U motion controller component we'll use for the location, the MC. And the second input is our object type. So TRA, T enum as byte, and the E object type query object types. Great. Next we have interacting, void interact write, this input value again. Then we have update interacting write to make sure it's void, and void stop interacting write. And again the same for the left. For the interacting part, next we have the weapon interactions. Here we have void release mag right and void release mag left, void change firing mode right, and also for the left. And then we also want to be able to apply recoil to the player's hands. So apply recoil. Here we have the E controller hand, which is the hand. We have vector, which is the location offset, the recoil, and the pitch. Then we create a U function. We create a U function so we can call this with parameters from a timer delegate. We will call this lerp recoil. Here we pass a F vector, and we will pass this by reference, the location offset, and also a float the pitch, and an F timer handle, which is the recoil th. Next, we want a function that checks if we can grab the slide of a weapon. So bool check for slide, and here we input an A actor, which is the actor. Then we need a T script interface, which is the I weapon interface. We will also pass that by reference and call it WI. Then the F name, which is the bone to constraint 2, the U physics constraint component, PC. And last, the U motion controller component, the MC. Then the next two functions are for getting the grip and the handle bones. So first we want to return F name, which is the get grip bone name, and the input is the hand bone name. This is just so we can dynamically get the name of the grip bone, which would be grip underscore hand underscore R or L. That's why we create these functions: get handle bone name, name, and bone name. Then next we want to check if we can start the weapon interaction. So bool start weapon interaction. Input an actor, which is the grab actor, and we actually want to make this a pass this pointer by reference. So grab actor, then a T script interface, the I weapon interface, WI. This does need to be passed by reference, and the U motion controller component, the MC name, which is the bone to constraint 2, and at last the U physics constraint component, the PC. Okay, we want to return a bool if we can update the weapon interaction. Here we will input the T script interface of the I weapon interface WI. We do not need to pass this as a reference. Then the bool B is main hand, and the U motion controller component, the MC, the bone to constraint 2, and the U physics constraint component, PC. And at last the stop weapon interaction, which also has a return type of bool, T script interface, I weapon interface. This time we pass it as by reference again, WI, and a bool B is main hand, a actor, the grabbed actor, and a U physics constraint component, the PC. That's that. Next, we have the ammo box interactions. Here we need two functions, one to start and one to stop the ammo box interaction. So first, void start ammo box interaction. Here we input the motion controller, so U motion controller component. See the A actor. At this point we will pass by reference, so the grabbed actor, and the F name bone to attach to. And by the way, we pass this pointer by reference, so we can set this to null or to the grabbed object inside of the function. So we don't have to create one for the right and for the left hands. This way we can input, for example, the right grabbed actor and then set the right grabbed actor variable that we've defined here. We can set it to the ammo that we grabbed. Next we have the void stop ammo box interaction. Here we only pass a reference pointer for the grab actor. Now we are almost done. For the climbing, we have the function void start climbing, which wants a U motion controller component, the MC, a bool which is passed by reference, B is climbing, and another bool passed by reference, B is other climbing. Next is the UpdateClimbing function, again a U motion controller component, MC, and this time just passing it by value. The B is climbing and bool B is other climbing. And at last, the stop climbing function, again a U motion controller component, C, and this time only the first one by reference. B is climbing and by value B is other climbing. The next few functions are for checking if the player is slipping and can continue slip. Bool check slipping. Then the only parameter we need is a U motion controller component, MC. Then the next is the check secondary slipping, which again takes a U motion controller component. We need the secondary slipping check when transitioning between two meshes, so we can check if the direction we're slipping towards, if we can continue to slip, or if by the next update we should stop climbing altogether and just fall to the ground. And the next function is to set some climbing offset, so void set climbing offset, and here we pass the hit result, F hit result. We will pass that by reference. And we have the update climbing offset. Again, we pass a hit result. Then for the update slipping, we return a vector, which is the new slipping offset, update slipping const F hit result hit. And the last climbing function is the void lerp climbing body z offset, where we input a float target offset and another float the target of height. And then at last, or almost last, we need to set the finger values. So void thumb right axis, and here we can input our F action value again. Then I'm going to duplicate this for the left. And then we need the same for the index and the grip. Void index right axis. Now the very last function we need is a protected function, which is virtual void possess by, and this takes the parameter of a controller, new controller. Make sure to override it, and we will use this to set up our input mapping context. Now I will create this first, right? And then just as usual, select all of these, except for our get physics animation settings because it's set here. And then create the declaration definitions. Okay, now we can start implementing all of the logic in the PR character. So first, since we have defined new base walk speed and base step height variables, we are going to set those. So we will get the character movement, and here we will get the max walk speed, and we will set this to base walk speed. This is just to make sure that everything is initialized properly. And again, get the character movement, and then the max step height is our base step height. Next, we want to set the capsule size. So get capsule component, and then set capsule size, and I'm going to go for a radius of 22 and a height of 88. This is just the default height. You can also set the half height to the radius. That doesn't really matter since we will be adjusting it dynamically at runtime. Next, we want to set up the mesh. So we will get the mesh and set the relative location and rotation. And for the location, we are creating an F vector, and X and Y axis should be 0. And the Z axis is the negative of the capsule half height. So get capsule component and get the scaled capsule half height. With this, we will be setting the mesh to the bottom of the collision capsule, since the origin of our mesh is also at the bottom. And then for the rotation, we are going to create an F rotator. And here the pitch is 0. The yaw is -90, because otherwise our mesh would be facing to the right. If you're using a custom mesh that faces the X direction, you don't have to change this, but the Unreal Engine 5 default mannequin mesh looks in the Y direction. This is why we need to add a 90-degree yaw offset. And then for the roll, it's 0, 0 again. Then we will get the mesh again. And then we want to set the collision enabled to collision enabled query and physics. Then get the mesh again. Now we are doing the collision setup, and I will do this and then I will talk about it so it goes a bit faster. There we go. So first we set the collision of every channel to block. And then, as we did with our custom collision profile in the blueprint part of this series, we then individually set the collision response of the visibility, pawn, and vehicle to ignore. We want to ignore visibility because otherwise we would be interfering with some collision traces that we will need for our collision capsule. For some reason, this still happens even if we ignore our pawn. So that's why we set this to ignore. And then pawn, of course, because our collision capsule is a pawn. And with physics, these tend to interact with each other, which would send the player off flying. And vehicle is just, in the future, we will be adding vehicles, so we don't want to collide with that either. And then we set the collision object type to a physics body, so other physics actors interact with it. Next, we will be setting up the VR origin. So VR origin, and here we will call create default subobject. This is a uScene component. We'll call it VR origin. Then we want to set this up, that attachment. We want to attach it to the capsule component, so get capsule component. And then we also add a world offset, just like we did with the get mesh, offsetting it again by the capsule half height. VR origin set relative location. It's the same since it's only being called once. There we go. Now we will set up the camera. We'll create default subobject camera component. Text camera. The camera will be attached to the VR origin. Set up attachment, VR origin. That's pretty much it we need for the camera. Then we will be setting up our motion controllers. First one being the RMC. New motion controller component. This we will also attach to the VR origin. And for the RMC, we will set the tracking source. Make sure you get the tracking source and not the tracking motion source. This will be the controller hands right. Then you can copy and paste this and change everything from right to left. So LMC, and the tracking source is the left hand. Now we continue on with the physics constraint component. Again, I will create them and then I will tell you what we did. So first thing we did, again, we created the component. Then we attached it to the mesh and to the right hand bone, which, if you remember, we defined in our private section, which is the hand R. And then I add the relative offset. This is eventually where the weapon will approximately be. We put it right there to avoid twisting, because even though we set all of the linear and angular limits to locked, there sometimes still is a little bit of bending, which I'm not too sure why, but I found out that it sometimes depends on where the physics constraint component is located. So if it's really far away, you have a lot of error. and if it's closer to the two constrained components, then it's less. That's why we add this offset. And then in the end, we want to disable the collision between the hand mesh collision and the object that we will be eventually holding. And now I will be duplicating this and doing the same for the left. But on the left, the only thing we need to change are the offsets. So for here, it's +7 and -3. And instead of 180 on the yaw axis, we add it to the roll axis. And then if you click the left Alt on your keyboard, you can select all of these and then press L to rename them to LPC. And also make sure that here you use the left hand bone. There we go. Next, we have our physical animation. So physical animation is also a default subobject. Physical animation component. We don't need to attach this. This can just stay as it is. Next, we will be creating our hand menu. This is what we use to dynamically set our height. This is a Widget component. And we will be making it so every time you look at the back of your left pawn, the menu will appear. So you don't have to press any buttons, because I kind of ran out of buttons to press. That was useful without having to check if you're currently holding a weapon or not. So yeah, that's just my approach. If you want to change it, of course, feel free to do whatever you like. Menu, then we will set up attachment. We will actually attach this to the LMC and not to the mesh. And hand menu had a relative rotation, and this rotation I purely got through trial and error. So yeah, you might want to adjust this to suit yourself. We want to set the draw size. This is a vector, F vector, and I will use 1920 by 1080, a vector 2D, not a 3D. Also want to set its world scale 3D to a vector of 0.05. It's a comfortable size that works for me, otherwise it's quite large. And then we also need to set its collision profile name, so set collision profile name to menu. Next we have our widget interaction component, so we will create this. Then attach it to the RMC and add a local rotation offset, F rotator of -70 on the pitch and 0 on the rest. And then we set its trace channel to our ECC game trace channel 3. This is our menu trace channel. If you go to your default engine ini and scroll down a bit, you will come to the collision profiles. And down here you see ECC game trace channel 3 is our menu. Next, we will be creating the laser pointer spline. And we want to attach to the RMC, just like we did with the widget interaction. Next, we have our laser pointer spline mesh. We will attach this to our laser pointer spline. Then we will set cast shadow to false, set mobility to E component mobility movable, and at last we will set collision enabled to E collision enabled no collision, because otherwise it would be interfering with our collision capsule and it just doesn't need any collision. And in the begin play function, first thing we want to do, we want to call the function load save game. So all of our parameters are loaded, for example, like the base height. Then we want to apply height and init the physical animation. Now, one thing that we will be adding later is from our hand menu an event to apply these settings when we change something in the settings. So for example, if we changed our turn style, then we want this to be applied to our character as soon as a value changes. We will be using a delegate for that, but more on that later. So for now, just for debug purposes, I will add a debug message so we can be sure that we don't miss it. So G engine add on screen debug message -1. I'll post it for 2 seconds in the color red, and for the text I'm going to say implement hand menu delegate initialization. That should be enough. So more on that later. Next, in the possessed by function, we are going to set up the enhance input subsystem. So first we want to get our controller, and we will cast this to a player controller. I'll call it PC. And this is the new controller. Then we want to get the subsystem. So U enhanced input local player subsystem. I'll call it subsystem. U local player get subsystem. U enhanced input local player subsystem. And from our player controller, we want to get the local player. In here, we call a subsystem and add our mapping context, the IMC, with the priority 0. Next, in the tick function, we want to update the VR collision, calculate the camera velocity. And next, we are going to implement the part where we check if the player is looking at the hand menu. And if left motion controller get the right vector, because the vector that looks in the direction of the palm is the right one, then we want to check if this is equal to the camera forward vector with a tolerance of 0.5. If it is, we want to check if the hand menu is visible. So is visible, and we want to check if it isn't visible. And if it isn't, we want to set its visibility to true. So set the visibility to true. However, if we are not looking at it and the hand menu is visible, we want to set its visibility to false. In theory, we don't need to add these extra checks. I'm just adding them so we don't always set this, since it's in the tick event. So we only set it once, and then it will just here go into false and get out of it. And same with the else clause, but it's a minor detail. Next, we want to update the laser pointer spline from our widget interaction. And by the way, here I didn't add any comments. In the version that's on Fab, there will be comments for everything, so you know what's going on. So first we get our widget interaction, and here we want to get the hovered widget component, because we only want to display it when we are hovered over a widget. Then we will get the laser pointer spline and set the location at spline point with the index 0 to widget interaction, get component location, and for the spline space coordinate, we want to get the world. So E spline coordinate space world. Then we can duplicate this, change the index to 1. And here, instead of the component location, we want to get the last hit result and then the location. However, if this is false, we want to collapse the spline. First, I'll create a local variable, which is of type vector. I'll call this StartPos. Then we have laser pointer spline, get the location at spline point, index 0, and E spline coordinate space world. And then we'll set the laser pointer spline and set the location at spline point, index 1, start, pause, E spline coordinate space world. You don't have to create this variable. I just did it so it's a bit more readable, because if you cram this in here, it's much harder to read. Then after this condition, we are going to create 4 new variables, because now we need to set the spline mesh. So first we will create a vector start pause. I'll duplicate it 3 more times. Then we have the start tangent, the end pause, and the end tangent. Then we will call the laser pointer spline and get the location and tangent at spline point at point 0. Then we want to set this to the start pos and the start tangent. And the E spline coordinate space should be local. Then we can duplicate this, change 0 to index 1, and input the end pos and the end tangent. And at last we can set our laser pointer spline mesh. So set start and end. Here we input the start pos, start tangent, end pos, and the end tangent. Make sure to divide the end pos by the laser pointer spline mesh, get component scale, and the x. This is so if you're using a cube, for example, from the editor, this is usually 1 by 1 by 1 meter, so it's way too large to be used as a pointer, but then you can just simply scale it down. However, if you scale down the mesh, then the length of the spline mesh will also be shortened. This is why we divide the end position by the x, meaning if it's below 0, it will actually get scaled up. Great, now we can continue with setting up our inputs. First, we want to cast to a U enhanced input component. I'll call it EIC, and we want to cast from the player input component. Now in here we can bind our actions. Call IC, bind action. First I'll use IA move, E trigger event triggered, this a VR character move. And actually I'll add a comment movement just so we know where we are. I'll duplicate this and add another one when on completed, and this will call stop moving. Duplicate this 4 more times. This one is for turning, then snap turn, try jump, and run. And over here we have to change from IA move to IA turn. This is also IA turn. We have IA jump and IA run. Hey, it's editing me here. I realized after recording that here everything was still on completed. These are the correct values. So move should be triggered, stop moving should be completed, turn should be triggered, snap turn should be started, try jump should be started, and run should also be started. There we go. Next inputs are for grabbing. So I'll copy one of those, change it to IA grab right. This should call started. And we want to call the function start grabbing right. So yeah, that's how you set up the actions, and I will do this now. I'll be right back. Just quickly, right here, we basically duplicate the same event just for the completed event, because if we only use the triggered one, it sometimes doesn't catch this last value. And then, for example, your thumb will get stuck at 0.5 and won't go all the way back to 0.0 when lerping its position. This is why we need the final completed input, just to make sure that we also get the last value and don't get stuck somewhere in the middle. And at last we will set our move action binding. This we will set to the address of IC bind action value IA move. With this we can read out the action value of IA move anywhere in our VR character or in other classes. Then we want to get the height ratio. Per default we will be returning 1.0, and now here we want an F hit result. I'll call this hit, and then in an if clause we want to do a line trace, so get world line trace single by channel, and then we have our hit. Then we get the camera get component location, and we add an F vector 0.0 on the X and Y value and the scaled capsule radius on the Z axis. And for the end, we get the camera location again. We subtract another F vector, and X and Y is going to be 0 again. And for the height, we are going to subtract the base height. This makes sure that we get a line trace from all the way from the top of the head, since the camera is where our eyes are located. But with the added radius of the collision capsule, we have the top of our head. It will trace all the way down to the bottom, or where the bottom should be. And here we will use the ECC visibility trace channel. And then if this is true, we return the math clamp hit.distance divided by the base height. And then we clamp this from 0.0 to 1.0. Oh, and this should be F math and not just math. There we go. And if the line trace doesn't hit anything, it means that we are, for example, falling or already standing straight up. So then we can just return 1. Next, we are going to calculate the floor level. Here we want to add a bracket. And in that bracket, we will get the capsule component. From this, we will get the component location.z. And from that, we will subtract the half height. So get capsule component, get scaled capsule half height, close the bracket, and then add the body z offset value and add the climbing body z offset value. There we go, that's already it for the floor level. We use the body z offset value and climbing body z offset value, for example, to change the actual floor level when we are climbing, because we want our mesh to always be on the floor level. However, when we're climbing, we are collapsing the collision capsule, and therefore we need to adjust the floor level. And with the body z offset, you can adjust it. For example, if you want to play in a seated position, you can add an offset so you are still standing up in game while sitting in real life. Okay, next we will be setting up the smooth collision for our VR character. And here first I will be writing a block of code and then I will explain it to you, because I am not that good at talking and programming at the same time. So yeah, I will do it one after another. Okay, so what we've done here, we are calculating the X and Y offset of our camera and capsule. So for example, if we are standing at a wall, our camera will be slightly off-center compared to our capsule component. And here we set the HMD.Z to 0, because we will need to recalculate this anyway, because we've set the Z location of the VR origin to the floor level. And for our next step, we will be recalculating this anyway, so we don't have to split this up here into a vector. This is why we set it to 0. And then we apply the positive to the capsule component. And very important here, you can see the bool that we input is a bSweep. So it traces the way to its target location. If this is false, the capsule component will be clipping into the wall that you're trying to collide with, and then as soon as it reaches the middle, it will just snap outside of it, which obviously isn't what we want. So by setting this to true, you will get a smooth collision without snapping. And then we need to apply the negative offset to the VR origin, because this component is attached to the capsule component, meaning this component is moved twice this length. This is why we subtract it, so we're at net 0 again. And then again, for the floor location, we just set the world location of the VR origin to its X and Y location and then to the floor level. And now we can continue with applying the Z offset. And instead of creating a new variable, I am just using the HMD offset.c for this. And just in case you're asking yourself why we do this again, because we should still have this from up here. We don't, because if you remember, if the collision capsule is colliding with something, however you're falling, for example, then after calculating the floor level, the sea level will be different than from up here. This is why we have to recalculate it. And then if the HMD offset .z value is less than 0.0, it would mean that we are currently clipping into the floor. So we get the VR origin and we add a world offset. Here we create a new vector, and we only want to apply the Z value, which is the negative of our HMD offset. Since this value is already negative and we want to go up in the positive direction, this will prevent us from sticking our head through the floor. For example, if your floor in the room scale is offset to the actual floor in game, then you could stick your head through the floor. This will prevent that. Next, we are going to update the half height based on if we are climbing or not. So I'll implement that and then I'll explain. All right, So first thing we did, we calculated the new theoretical half height, which is just the top of our head, which is the location of our eyes, so our camera, plus the capsule radius, minus the VR origin, because this should always be at our feet, and then divided by 2, since it's a half height. Then we are checking, first of all, if our character can climb, and if he can, we are checking if he is currently climbing, and then we need a target offset. And this target offset is where our body should be while we are climbing. Since our collision capsule is simply being reduced to a ball while climbing, so it's easier to climb up ledges, we also want to offset the mesh so it looks like we are hanging there. And if we didn't do this, it would look like our character is laying just in the air, which would look weird. If your character cannot climb or isn't currently climbing, then we first want to check if our climbing body Z offset isn't nearly 0 with a tolerance of 0.1. This is if you recently stopped climbing, but your capsule isn't back at its original size. Then we want to lerp our climbing body Z offset to 0 and set the target half height to the half height that we've calculated up here. This will slowly set the collision half height back to its original size, and this will avoid snapping straight in place. However, if the climbing body Z offset is already at 0, then we can simply just set the half height. This is also the case if you cannot climb, then that's the same result. And next we are going to implement the checking the top, meaning if you're underneath a surface or just somewhere where the room isn't that high and you stand up, normally your camera would clip into the roof and then you would get stuck there because it tries to expand the half height of the collision capsule. However, since it's trying to expand into a mesh, it then gets stuck there and you won't be able to move. So we are going to adjust for that. Great, so first thing we did a line trace where our starting location is our collision capsule component and the end is where our top of the head should theoretically be. And for the collision profile name, we are just using the same collision as our collision capsule component. Then this false one refers to the trace complex. So if you see here, you have trace complex. Then the next is our actors to ignore, which is just this actor itself. The eDraw debug trace is set to none. You can set this to, for example, for a duration or 1 frame. I'll leave it at none. This is just for debug purposes. Then the hit is our hit result. And the last one is to ignore this actor, or ignore self, I should say. I added this actor, despite it saying ignore self down here, also to the actors to ignore array, just because I've had some issues in the past. So just to make sure that it doesn't collide with itself. Then if we don't have a hit, we don't need to do anything. However, if we do have a hit, we want to set the collision half height to the hit distance, since we're tracing out from the middle of our collision capsule, so we only receive the half height, and subtract 0.1 from it. We subtract 0.1 because if we set it to the exact height, we will still end up getting stuck. So we need to subtract a small amount so we can still move. And of course, it's possible that our camera is still much higher. So let's say if the space is only 1 meter tall, however you are 2 meters, then you would still be sticking your camera 1 meter into the wall. And if we only set the half height, then sure, you can still move and all, but your camera is still way up too high. So we need to apply the offset to our VR origin. Now, the next part is for when we are under a narrow space. And for example, we do stand up, and if we get out from under it, then our capsule half height will snap back to its original size. However, this can lead to it being stuck in the ground. So we will add another line trace to the floor just to make sure that our collision capsule won't get stuck in the floor. For that, I'm going to copy the one from up here. And then all we need to change is the end, component location, Z, minus the half height. Get capsule component, get scaled half height. And then if this is true, we get our capsule component again and set the capsule half height to the hit distance. And we subtract 1.0 from it again to make sure there's still a little bit of space so we can move around. And that's already that. And at last, we will be updating the mesh position and rotation. So all we did here, we will set the origin of the mesh to the floor without adjusting for the body Z offset. And for the rotation, we will just simply make it that it always looks in the yaw direction of the camera. We subtract -90 because the Unreal Engine 5 mani mesh is looking in the Y direction and not the X direction by default. That's why we subtract 90. So it looks in the X direction. Now that's that for the update VR collisions function. Next, we want to be applying the height. So we will get the mesh and we'll set the world scale 3D and we'll set this to an F vector of the base height divided by 180. We divide by 180 because that's the approximate height of the default mannequin. So if you use a custom mesh, then measure it, make sure you have this size and you can input it here. Now to calculate the new height, we will create a new float, new base height. We'll set this to camera, get the component location, the Z value and the capsule component is scaled capsule radius and subtract the floor level from it, calculate floor level, and here we don't need to input anything. Then the new base height is fmath, and here we want to clamp the new base height from 50. I'll just set this as a minimum height to the new base height. This is just to make sure that, for example, something goes wrong or anything with the tracking, so your character isn't infinitely small or gets a negative height. So yeah, that's where we clamp it. And then we apply the height. Next, we will get to the initialization of the physical animation. So first we want to get the mesh and set all bodies below simulate physics. And for this, I'll use the clavicle bone, R bone, set it to true. I'll duplicate this and do the same for the left. Then we have our F timer handle. I'll call this TH. Now get the world timer manager. Set a timer, TH, for this function is a VR character, enable physical animation, and we want a delay of 0.2. We use this delay because I've noticed that if you try to initialize the physical animation right after a character has spawned, it can potentially crash the engine. That's why we need a delay. And in Blueprints, you would just add your delay node. However, here you can't add a delay. Should I say you have to do it using a timer handle. That's why we also create these two functions. And now in the enable physical animation, we are going to get our physical animation variable. And we want to set this skeletal mesh component to our mesh. So get mesh. And then we want to enable the animation for the two bones that we've set to simulate up here. So we will apply physical animation settings below. Here again we have our clavicle R bone, and here we will get the physical animation settings, duplicate this, and then do the same for the left. And that's already that for the animation. Then in onSettings applied, all we have to do is just load save game. And in load save game, I will print another debug message because we don't have the VR save game yet. So we will be adding this later. Next, we will be implementing the movement. So first we want to get our vector 2D. I'll call it input is equal to value dot get. Then we want a vector 2D. Now first we want to update the movement speed, and then we want to switch on the movement direction. Max, we don't need that, and the default we can just leave as it is. I will add the curly brackets just because in my opinion, it's a bit more structured this way. Just be moving direction, not E moving direction. If it's the controller, we want to add movement input. And here we want to get the LMC because that's where we also press the button to move around, and then get the forward vector and we want to get a safe normal 2D. We get a 2D normal because otherwise when you point it straight down, you won't actually be walking forwards. And this way it will get normalized, so you will still be moving forward the same speed and won't slow down. And then here we just want the input.y value. We can duplicate this. Here we want the input.x, and from the LMC we want to get the right vector. Copy these two, come down here to camera, and all we need to change now is just change LMC to camera. There we go. That's already it for the movement. Then in stop moving, all we are going to do here is just set B is running to false. Now in movement speed, we want to update the movement speed based on if we are crouching or proning or whatever we are currently doing, or running, of course. Get a float current height ratio, and get height ratio. And here I'll create this variable because in here we are doing a line trace, and with this variable, since we'll use it twice, we can reduce the amount of performance that is needed. So first we want to check if the current height ratio is less than or equal the crouch ratio. Now, if it is, we want to update the max walk speed accordingly. So get the character movement, max walk speed, and here we want to map range clamp our value. So f math get map range value clamped. We want to clamp a float, t range a float, and here we input our prone ratio and our crouch ratio. Then the second range is t range, again a float. This is from our base prone speed to our base crouch speed. And then in here we have our value, which is the current height ratio. So what we do here, we take the input and then we check if it is between these two values. So between the prone ratio, which for me has a default value of 0.3, I believe. Yes, 0.3, and crouch. And we do this only when we are below the crouch ratio or equal. And then map range clamp that value to the base prone speed, so between 50 and the base crouch speed 100. So as soon as we go lower, we slowly start to move slower. And then we will also set is running false, because me personally, I only want the character to run if it's above the crouch ratio. And then we can turn. Then secondly, we want to check if the move action binding get value dot get, and here we want to get an f vector 2d. If the y value of this is less than or equal to 0.0, then we also want the character to not be running, and we want the max walk speed to be the base walk speed. Get character movement, max walk speed is our base walk speed. And of course here you could also do the lerp thing just between the crouch ratio and the ratio 1.0, meaning standing straight up. I won't do this here because I don't think it's needed as much here, because here we also do this to transition from crouching while moving into proning. And here we can just copy this because we also don't want to be running anymore and we want to return. And at last, if b is running is still true, then we want to get the character movement, set the max walk speed to our base run speed, and return. And if for some reason none of this is true, we will just set it to the base walk speed. Great, that's it. Now turn itself is going to be used for our smooth turning, so we want to check if our turn style is equal to ts underscore smooth. And if it is, we get the input, which is a float, equal to value dot get float, and then we add a controller yaw input of our input. Of course, you could also cast this directly in here, but I'm doing it like that, so it's a little bit cleaner. Now here in snap turning, we are going to first check if the turn style is equal to ts snap. So here we want to check if our value is positive, value get load. This is greater than 0.0. Then we want to add a controller yaw input of 22.5 degrees. You can also use 45 or something else. I'm going to use 22.5. And then after that, we are going to add else. And here we can just copy this down here, but make sure to negate the value. And here, if the float value is positive, we are trying to turn to the right. If it's negative, we are going to the left. And we don't need to check if it's equal 0, because if it's equal 0, this event won't even be triggered, because it will only be triggered when the event has started, meaning after the stick is already moving. Then in try jump, all we need to do here is first check if the height ratio is greater than the crouch ratio. So get height ratio. And I do this because I only want to be able to jump while standing up and not while crouching. Greater than crouch ratio. And if you're currently not climbing. So if B is climbing right is false, and if B is climbing left is false. Then we can just simply call the jump. Now here in the run input, we can copy and paste this if statement because it has the same condition for running. And if this is true, we want to set B is running to true. Then to calculate the camera velocity, we simply, first set our camera velocity to our camera get component location and subtract the previous camera location from it. However, this is only a tiny distance since this is being updated every tick. So we need to divide it through the delta seconds. So get world, and then from here get delta seconds. And then we want to set the previous camera location to our camera location. There we go. Now we can continue on with grabbing. Now in the start grabbing right function, we first want to check if we aren't currently holding a right actor. So check if not right grab actor, check if it's not valid, and also if the right interface is invalid as well. So right weapon interface. And here again, I will just do the implementation and then I will explain to you what it does because my brain can't really talk and program at the same time. Okay, so first thing we do, we use our start grabbing function to get the actor that we are trying to grab. In this function, we also grab it with our physics constraint. Then we take our grabbed actor, set the owner to this. So the owner of the grabbed actor is the character player. Then we set the reference to our right grabbed actor. And then we check if it implements the iWeapon interface. And if it does and is also the right hand, it means we are holding the weapon at the handle. So we can set our right weapon interface, set the primary hand to right, and on the on hand animation changed event, we can broadcast it with our primary hand animation, our primary hand trigger pulled animation, and false because we don't want to mirror the animation. Because for me, the way I create the animations, the right hand is basically always the main hand when creating the animations, and the left is always the secondary one. And if it isn't the main hand, it means we are holding the grip of a weapon. So we just set the secondary hand to the right and we broadcast only the secondary hand animation because we don't need to pull the trigger with the secondary hand. However, we do need to mirror it, so we also pass through. And then if our grabbed actor is invalid, then we will try to climb by calling StartClimbing. Next, there is the update grabbing right function. This is pretty simple. Update grabbing, and in here we have our right grab actor, our B is right main hand, the RPC, the RMC, and the right hand bone. And then also update climbing, RMC, B is climbing right, and B is climbing left. And that's already that for the update grabbing function. And in the stop grabbing function, again, I will implement it and then explain it. Okay, so when we stop grabbing right, we will call stop climbing, because if we are climbing, then we can stop. And then we also always want the right hand animation change events to be called, which broadcasts null, which will go back to our default procedural hand animations. Then we want to make sure that our right grabbed actor is valid, however, that it is also not a ammo base. And then if our hand is the main hand, we want to simply stop grabbing, and then we can set the right grab actor to null and the B is right main hand false. If the weapon interface is still valid, we want to make sure that the weapon stops firing, because if you're firing full auto and we let go of the weapon and don't stop this, then it will just keep firing on the ground. And then we also want to make sure that the primary hand is set to any hand. which in this case is no hand. Then we can invalidate the weapon interface, and in the else clause here, first we need to create the shotgun class, and after that we can continue here. So this is a placeholder for now. And now we do all of that just for the left. So we can simply copy paste it and then change everything from right to left, and everything that is left, for example here in StartClimbing we pass the left grabbed actor, this would then be the right grabbed actor. Also here make sure that you now mirror the animation, because again the handle animation is only for the right hand being created, so we can simply mirror it, and now we also have it for the left. And however here for the secondary hand animation, since this already exists for the left hand, we don't have to mirror it. And then of course we do the exact same for the update grabbing left and stop grabbing left. And now before we continue with the start grabbing function, since we need the shotgun class again, we are going to first create those classes and then we can come back here. So I will compile first, just to make sure that it's still building. And now in the editor, we can create our safe game class. We'll just create it in the public folder. Then you can go to all classes and search for safe game. Use this safe game object, and I will call it VR safe game. Create a class. Great. And for the includes, all we need to include is the Kismet gameplay statics. Then in our header file, here we need to make sure that we include the VR character character.h, and then we can add a default constructor view VR safe game. So, and in here the first view property is visible anywhere and blueprint read write. Then it's category variables. This is an T enum as byte, and this is our E turn style, and we'll call it turn style. Copy paste this. However, instead of turn style, we want the E movement direction. The next one is a float master volume, and I'll set it to 1.0 by default. Next we have another float, which is our base height, and I'll set this to 180 centimeters because that's the height of the mannequin. And then for our functions, I'm going to add a U function, blueprint callable. This is a static U VR safe game load VR safe game from slot, and we want to input the slot name, and an integer 32, which is the user index. This is basically like the default load safe game from slot. However, here, if we don't find anything to load, then we will automatically create a new one. So we don't have to do that every time we try to load a safe game and it doesn't properly load it. Here, another U function, blueprint callable. So it can be called from blueprints. Static return type bool, safe VR safe game to slot. Here we pass a UVR safe game object, a game, and then again the slot name and the user index. And at last, because I don't always want to have to remember what the slot name is, we're going to create a static function that returns an f string, static f string, gets default slot name, and we can do this in the header file. We simply return safe slot 01 or whatever you want to call it, doesn't really matter. So yeah, with this we can simply call this anywhere and then always get our safe slot 1 or default or whatever you call it. Now we can create the definitions for these functions. There we go. The constructor we can leave empty, and in the load VR safe game we are first going to try to load it. So UVR safe game, I'll call it safe game, is equal to cast UVR safe game, and here we get U gameplay statics load game from slot, and here we have the slot name and the user index. Then we want to check if this is invalid. So save game. This isn't valid. We want the save game to be a new object. Type UVR save game. And then we simply save this. So uGameplay statics, save game to slot game, slot name, and the user index. And by the way, I don't just simply use the default slot name in here, because you can still have different slot names to save different VR save games if you'd like, and you can still input custom names. Great, and after that's been saved, we simply return the save game. And for the save VR game plot, here we simply want to first check if the save game is valid, and then return new gameplay statics save game to slot. And this is the save game object, slot name, and the user index. There we go. Yeah, that's it for the save game. So now we can advance to the projectile weapon base. Back in our editor, I will go into the weapons class, and then I will right click on weapon base and create C++ class derived from weapon base. I will call this projectile weapon base. Make sure the folder is correct, weapons, and create the class. And now we begin again by adding the includes. Include VR character, then the weapons, magazines, here the magazine base, then weapons, magazines, ammo, and ammo base, and projectiles and projectile base. From the engine, we include sound base, then the Niagara system, Niagara function library, Kismet. We want the gameplay statics components, box component. We will need this for our magazine hitbox, Kismet math library, motion controller components, the static mesh component, and from physics engine, the physics constraint component. Then in the header, we will include our weapon type enums. So go a step back, enums, weapon enum types. Here for our classes, we have the A ammo base, U sound base, U box component, A magazine base, U Niagara system, the U static mesh component, and at last U physics constraint component. Oh, and of course the U motion controller component. Private variable, which is an F timer handle. I'll call this the magject timer handle. We use a timer handle because we first will set the physics constraint of the magazine and the weapon to just have free linear limits, so the magazine will fall out of the weapon without colliding with it and flying off. And then, like, let's say half a second later, we will actually break the constraint. Because if we break it while the magazine is still inside of the weapon, there will be some physics bugs, and this is just to avoid them. And in the public section, I will create my region again. And for our U properties, here we have a visible anywhere, blueprint read only, and the category components. Here we have our U static mesh component, which is our slide mesh. Then the next component is another U static mesh component, which is our trigger mesh, and another one for our selector mesh. Then we have our U physics constraint component, which is our magazine constraint, and at last the U box component, which is the magazine hit box. So here the U property first of all is edit anywhere, and the category is variables firing, and here we have a float fire rate. I'll set it to a default of 0.2, and the next one is visible anywhere, and this is the last fire time 0. Here we have an integer, which is our projectile count. I'll set it to 1. This is how many bullets are being fired at once. I didn't really find a better way to do this, because when I just overwrote the fire function in the shotgun, most of the code was exactly the same, and the only difference was that there were more bullets being spawned. So what I did is add a projectile count, so even if you want to have a custom weapon, or if you have, for example, an AK-47 that you can upgrade, like in Call of Duty Zombies, then you can spawn multiple bullets at once, and the first bullet will always be straight out of the barrel. So where you aim, you will fire. It's only after the first bullet where there will be a random projectile spread applied. And with that, the next variable is the max projectile spread, which I'll set to 10 degrees. And the next one is our trigger max rotation. We will use this to lerp the trigger rotation, and I'll set this to a value of -20. And we'll get to that, how you can find out what the correct rotation is for your weapon. And for the recoil, we first have a float, which is our recoil distance. I'll set it to -5 per default. Make sure this is negative because it's supposed to be going the opposite direction of where the weapon is facing. Then the next one is the recoil pitch, which I'll set to a positive value of 5.0. And then we want a factor to minder recoil when we are holding the weapon with two hands. And I'll call this two-handed recoil dampening factor. And I'll set it to a default of 2.0, meaning if we fire the weapon with both hands, recoil will be divided by 2. Now next we have our firing modes, and in here we have a T array, which is T enum as byte, E firing mode called firing modes, and I'll set a default value of FM semi-auto. I think that's what most weapons use nowadays. And then we have another T enum as byte, which is our E firing mode, which is the selected firing mode. I'll set this FM semi-auto. And at last we need a T array of type F rotator. These are our firing mode selector rotations. And I'll set it to a 0 rotator by default. 0 rotator. This is just if our weapon has a selector, for example an AK-47, and we have 3 firing modes, for example semi-auto, triple fire and full auto, then here we can also add 3 entries for the 3 different selected modes, where first one is at 0 degrees, and I will be using it for the pitch, but I thought, hey, maybe someone wants a firing mode selector that rotates vertically or maybe even diagonally for whatever reason. So you can set it to whatever you like. I will be using it for the AK, for example. 0 degrees out on the pitch is semi-auto, -10 degrees is triple fire, and -20 degrees is full auto. Here we have an int, is current firing count to 0, and I'll also make this visible anywhere. And then editable anywhere, we have our int max firing count equals 3. Now, of course, you can simply change this, and then you'll have a weapon that has double fire or that fires 5 shots. I called it triple fire, but you can change it to how many shots you'd like. Here we have a T subclass of a magazine base. This is our matching magazine class. We use this class to check if the current magazine that's overlapping the magazine hitbox actually fits into the weapon or not. And then as visible anywhere, we have our A magazine base, which is the loaded magazine reference. First one is also visible anywhere. And this is our A ammo base, which is a reference to our loaded ammo. This is the ammo that is currently in the barrel. The next one is editable anywhere, and this is an F vector, which is our shell eject trajectory. And I'll set a default value of 0.0 for the x-axis, 1.0 for the y, and 1.0 for the z. So it flies in a 45 degrees upwards to the right. This is editable anywhere. For example, on a P90, they just fold straight down. So you can simply set X and Y to 0 and the Z value to a -1. And at last we have a float shell eject force, which defines with how much force the shell is ejected, and I'll set it to something like 200. Next we have our slide variables. And the first one is a float, which is the slide travel distance. I'll set it to a default of -5.0. Again, negative because it goes in the opposing direction the weapon is facing. Next, we have a visible anywhere. This is a bool b was slide pulled. This is so we know if the slide has already been pulled or not, because without it, when we check if the slide is at the back and we want to play a sound, it would constantly play that sound. With this, it only plays it once. And we also need it for loading the next ammo. Then the next one is B was slide released. Then another bool B is slide being held. Because if we are holding the slide, then we don't want to snap it to the front or back. Then it should be wherever you're holding it. And with this, the weapon will not fire. Unless, of course, you have the slide all the way in the front. Then we also want to know if the slide is stuck, so B is slide stuck. This is true when you have an empty magazine inside of the weapon and you just fired your last bullet, or you pull back the slide so it gets stuck at the back. And we have an F vector, which is the relative slide hand start location, which by default is an F vector 0 vector. We use this so we know where you started grabbing the slide, because I had some issues, especially with the physical animation together, where it would either not move it at all, or the slide was instantly being pulled without you being able to change its location unless you let go, but that also felt weird. So we remember our relative start location of the hand when we grab the slide, and this makes it much better. Next, we have some properties for our hands. So first we have the E controller hand, which is the primary hand, and I will set this to any hand. And then we have the same for the secondary hand. Then we have our effects, and we'll start with the VFX, so video effects. This should be edit anywhere, category effects. And we have a U Niagara system, which is our muzzle flash. Then for our sound effects, we have a U sound base. And the first one would be the mag in sound. Now we can just copy this 6 more times. We would have the mag out sound, firing sound, the trigger click sound. We'll be playing that every time we fire and every time we try to fire. So if the mag is empty, you'll just hear the clicking. Then we have a slide back sound and slide release sound. And then we have the firing mode sound. We are almost done, I promise. Here we have some names. Set to edit anywhere. The first one being the loaded ammo bone. This is important that you remember this name because it depends on the socket names on your slide and weapon mesh. However, I define them here so we have it all in one place. So if you want to change something in future, you only have to change it here and not at 10 different places. Then the next one is the muzzle bone. We use this so we know where to spawn the muzzle flash. And the last one is the magazine bone. This is where the magazine is supposed to be. We can use a preview mesh in the socket manager of the skeletal mesh of our weapon to figure out where this exactly needs to be. And the last few variables are our animation variables. This should also be edit anywhere. Then you have a U animation asset, which is our primary hand trigger pulled animation. Because if you remember, the primary hand animation itself is in our weapon base class. Copy this, and this would be the slide grip animation. Now let's continue on with the functions. So we have our default constructor. However, then we also want the tick function, so virtual void tick float delta time, and make sure to override it. Next is a U function, blueprint callable. This is a virtual bool called fire. Next would be void eject shell, then another U function, which is the void move slide back. This snaps the slide all the way to the back. Then we have the same for releasing the slide, so release slide. Then we have one to check our mag. So we need a return type of E mag check turn type, which is check mag function, and then also check the ammo check return type, check ammo. Regular bool without a new function, spawn loaded ammo, the subclass of a ammo base, virtual void load round. A bool is slide pull, another bool return which is slide released, slide recoil, void init mag ejecting, since you're using a timer, and then void finish mag ejecting, which is where we will be breaking the constraint. Load the magazine, which takes a parameter of a magazine base, which is our new magazine. Then we have a function, the virtual void on magazine begin overlap, which is the overlap event that we will bind to for our magazine hitbox. Primitive component, overlapped component, a actor, other actor, u primitive component, the other comp, int other body index, bool from sweep, the const f hit result, which is the sweep result. Then our interface functions. Here we have the virtual u primitive component, get slide component, try to override it. These are all virtual, by the way. Void fire weapon, stop firing weapon, void change mode. I will just shut up for the rest of these so I can focus a little better. Also make sure to add the virtual void begin play function in the protected section. And that should be it for all of the functions. So I'm just going to select everything and create declarations. Should be all of it. And I'm going to just call the super functions in begin play and tick. Super begin play. This is important. Tick. And now we start by creating the components. And by the way, when you see this green squiggly line, here it says that the variables are uninitialized. This is fine because these variables, we will be setting them in the blueprint. So you can just ignore this. Anyway, first we want to create this light mesh. Mesh, there we go, and we want to attach this to the weapon mesh. So set up attachment, weapon up, weapon mesh. And we want the collision profile name to be a grabbable object. So set collision profile name object. Next we have our trigger mesh. We also attach it to the weapon mesh. And this has no collision. And the same goes for the selector mesh. There you go. Next we will be setting up the magazine constraint. This is also attached to the weapon mesh, but then to our magazine bone. Weapon mesh and input magazine bone. Then we want to make sure that everything is locked. Magazine constraint. Set linear x limit to LCM locked 0.0. And then we do this for the other axis and also every rotation. And at last, we want to make sure that the collision is disabled between the two constrained actors. Then next we have our magazine hitbox. This is also attached to the magazine bone. Then we want to set the collision response to all channels to ECR ignore, and then only enable it for our game trace channel 1, so our grabbable objects channel. So ECC game trace channel 1 and ECR overlap, since we only want to be overlapping grabbable objects, which is the profile that our magazines are using. Next, we want to make sure that set generate overlap events is set true, and we can disable set notify rigid bodies because we won't be having any hits, only overlaps. And we want to make sure that the set collision enabled is set to e collision enabled query only. And at last, we want to make sure that the object type, at collision object type, is an ECC world dynamic. There we go. Now we can continue on to the begin play function. In here, first we want to check if we have less or equal than one firing mode, because if we do, then we want to destroy the selector mesh, destroy component, because if we only have one, or less than one, which shouldn't be possible, but just for safety I put it in here. So if we have one, then we don't need the selector mesh because there is no firing modes to be switched between. Then we will set up the magazine hitbox overlap event. So on component begin overlap at dynamic, this and a projectile weapon base on magazine begin overlap. Now in the tick function, we will be using this for firing the weapon. So first we want to check if the selected firing mode is equal to FM triple. Because if it is, we want to also check if the current firing count is less than the max firing count. If this is the case, we can try to fire. Now if firing is successful, we can increase the current firing count. Otherwise, if the current firing count is equal or higher than the max firing count, we simply want to disable the actor tick. So set actor tick enabled to false. And if the selected firing mode isn't triple fire, so if it's anything else, then we can simply call fire. Next, I will be implementing the fire function. I will implement it first and then I will explain what I did, because it's a lot again, and if I try to talk over it, it will just take 3 times as long. I just noticed a little mistake I made. This load round function should return a bool and shouldn't be void. Here as well, load round should be bool. There we go. Okay, that would be all. So first thing we do, we check if the time since our last firing time is greater or equal our fire rate. If it is, we will set the last fire time to the current time. Then first we want to check if the slide is released, because we only want the weapon to be able to fire when the slide is at the front. Then we want to make sure that our loaded ammo is valid and that it hasn't already been fired. If those things are both true, then we will set the loaded ammo to fired. And here we'll create our actor spawn parameters, where we set the owner to this, and we want to make sure that it can always spawn despite of collision. Here we get our muzzle transform, and this is where we loop through our projectile count, where if the index is 0, so if it's the first bullet, we will just simply shoot it in the direction of where our weapon is pointing. And for every projectile that's supposed to be spawned after that, we will add a random offset. So a random pitch and random yaw. We don't need to add a random roll because it would only rotate it along the axis where it is flying, so you wouldn't be able to tell the difference. Then after we've spawned our projectiles, we spawn our muzzle flash and the firing sound. Then we apply the recoil. Then we check if the selected firing mode isn't FM single and if the slide isn't already being held. And if those things are both true, because on a FM single, which is for example a shotgun, we don't want the slide to move back by itself because we want to do it manually. However, if those conditions are true, we move the slide back. This just sets the slide into its back position. We eject the shell, then we try to load the next round. Now the load round function returns true if the slide can release. So if you're holding it, or if, for example, the magazine that is attached is empty, it would be false. However, if there is no magazine attached or the magazine still has ammo in it, it will return true. And for that, we use a timer handle, and we want to release the slide after half the time of our fire rate. And then, of course, we don't want it to loop. However, if the round couldn't be loaded, it means the slide is at the back and it cannot release, so we set the slide to stuck. And if it is single or if the slide is being held, we simply set this slide to stuck. And we return true, meaning that the weapon has fired. This way, you can also move the slide to the front after a new round has been loaded. And even while you're holding it, as long as it is released, you can fire one round. However, since the slide won't go back due to our condition here, then the next round won't be loaded. So we can still return true that this round was fired successfully. However, for the next round, it would return false. And if our slide is already stuck at the back, then we first check for this, because maybe it's in the middle, which it would mean that it isn't released. However, it's also not stuck at the back. But if it is stuck at the back, we try to load the next round. And if, for example, we release the empty mag or add a new one, then we can simply press the trigger and then it will release the slide and load a new round. You don't have to add this. I just thought it would be neat that after switching out mags, you could simply press the trigger once and then you would be ready to fire again. And if none of these conditions are true, we simply return false, because then we could not fire. Next, we will implement ejecting the shell. First, we check if the loaded ammo is valid. And if it is, we want to enable the actors collision. So loaded ammo, set actor enable collision to true. Then also for the ammo mesh, we want to set the collision profile name grabbable object. We also want to make sure that it is simulating physics, so set simulate physics to true. And we want to add an impulse to our mesh. So add impulse. Here we get our weapon mesh, and we want to get the component rotation, and we want to rotate the vector that is our shell eject trajectory. And then we multiply this by our shell eject force. And the impulse is applied to no bone, so name none. And true, then we can call the init despawn ammo function. And at last, we can set our loaded ammo to a null pointer. So the next one is ready to be loaded. Then in our move slide back function, we first get the slide mesh, and we set the relative location, an F vector, which is our slide travel distance for the X, and the Y and the Z are both 0. Here it is important, if you import your own meshes, that you set the origin of your slide mesh to the same origin of your weapon mesh. I did it this way because it seemed to me easier, because otherwise we would have to first get the relative location of the slide mesh compared to the weapon mesh. And this way we only have to set the X direction and don't have to do a whole lot of other calculations. And it's also easier when creating the weapon blueprint, then you don't individually have to set the slide mesh. This way you can just add it and it's already in the correct position. Now after that, we want to check if the slide was not pulled. So B was slide not pulled. Now if that condition is true, we set the was slide pulled to true, and we will set was slide released to false, and we want to play a sound. So you gameplay statics play sound at location, get world, slide back sound, slide mesh, get component location. We need this check because otherwise, if we move the slide back with our hands, as soon as it reaches the back, we would be constantly playing that sound every time the game ticks. So we only want it to be played once. Then for releasing the slide, we again get the slide mesh. Here we set the relative location to a 0 vector. B is slide stuck. We'll set that to false. And here we want to check if the slide was pulled and it was not released. So B was slide released. Then we set was slide released to true, and B was slide pulled to false. And here again we play a sound. However, we set the slide release sound. And this condition again is so this sound only plays once and not all the time. Now here in the checkMag function, you can change this return type to MCRT not attached. This is our default case if the condition is false. And here we check if our loaded magazine is valid and if the mag eject timer handle is not valid. And here we have another if condition. The loaded magazine get current ammo count is greater than 0. We return MCRT not empty, and otherwise we return MCRT empty. That's already it for that. And the check ammo function, if everything fails, we return ACRT failed. And the first condition is to check if the loaded ammo is invalid. Here we had a switch, which is our check mag. Our first case is the MCRT not attached. And actually we can remove the default here and just copy paste this 2 more times. Here, change this to MCRT not empty. And this one is MCRT empty. Now, if it's not attached, we can just simply break and then return ACRT failed. If it's not empty, however, we want to get the loaded magazine and remove a single round. And if that succeeds, we can spawn the loaded ammo, loaded magazine, get ammo class. Oh, I forgot the if. And then we can return ACRT success. And then we also don't need this break here. Never mind, we actually do need the break here in case this condition fails. For example, if we somehow get not empty, but it still fails when spawning or removing a single round for whatever reason, then we still want it to break and not go into the MCRT empty. However, if the mag is empty, we simply return ACRT mag empty. Next is the spawn loaded ammo function. I will implement this again and then explain. Okay, so first we want to check if the ammo class that we've passed is valid. Then we create our actor spawn parameters again, where the owner is this, and we don't want any collision when spawning. Then we spawn the actual ammo at the loaded ammo bone on the slide mesh. And if the spawning was successful and our loaded ammo is valid, we want to attach it to the slide, because here we only spawn it at the location. So we attach it to the slide, and then we want to disable the ammo's collision, because it's only there for visual purposes. And then we can return true, and if anything here fails, we'll simply return false. Then in the load round function, here we add a switch, which is our check ammo, case ACRT success, our first one, break, and I'll copy it 2 more times. If here we have ACRT failed and ACRT mag empty. In ACRT success, all we need to return true, because we want the slide to release. In failed, we want the set actor tick enabled to be false, because the weapon should no longer be able to fire. And then we can still return true, because even if the mag is not attached, which then it would be failed, then while the round cannot load, the slide can still release. And at last, if the mag is empty, we simply set the actor tick enabled to false, because the weapon should not be able to fire. We break and we then turn false. Now in isSlide pulled, we can simply return slide mesh get relative location .x, and we want to check if this is less than or equal our slide travel distance, and I'll add an error of 0.5. So if it gets close to our slide travel distance, it will see the slide as being pulled, and the way it works, it will then snap back, and this will return true. And in isSlide released, it's the opposite. So return slide mesh get relative location .x, and we want to check if it is greater or equal negative 0.5. And this is very important. We add to our slide travel distance because this is negative. You remember the default value we set is negative 5.0, because this moves in the opposite way of where the weapon is facing. So this is negative. In the apply recurl function, we first want to get a reference to our character. So a VR character. I'll call this character reference. It's cast to a VR actor from the owner. Get owner. Then we want to make sure the secondary hand is equal to eController hand. And if this is equal to any hand, it means we are holding the weapon in one hand. So we can get the character reference apply recoil, primary hand, weapon mesh. From that, we want to get the forward vector times the recoil distance, and at last the recoil pitch. However, if the secondary hand isn't any hand, it means that we are holding the weapon with two hands. First, again, we get the character reference, apply recoil, primary hand, and here we want to get the weapon mesh, get forward vector times our recoil distance. However, we then want to divide this by the two-hand recoil dampening factor. Then we have our recoil pitch, which we also divide by the two-handed recoil dampening factor. And now I'm going to copy paste this because we now want the same but for the secondary hand. Next, we are going to initialize the mag ejecting. First, we want to check if the loaded mag is valid. Then we get the magazine constraint, and here we set the linear X limit to LCM free 0.0 because it doesn't matter when it's free. Then we have our Y limit and Z limit. Now, of course, in theory, you can only set the C limit, so the magazine falls out straight. However, I found that it can sometimes still get stuck, and especially when you're moving the weapon. So this way it can just slip out in any direction. Then we have our loaded magazine. We will set the owner to null, and then we have our U gameplay statics, play sound at location, the exact one, just the regular one. And then we have our world, mag out sound. We play this at the magazine hitbox, get component location. There we go. We use the magazine hitbox location because in the blueprints we will be moving this, so it's right where the magazine should attach, so the sound will be played at the correct position. Down here in finish mag ejecting, we can copy these three and we can set them back to locked, so LCM locked. First, we also want to the magazine constraint again and break the constraint. Then we set the loaded magazine to null pointer so we can load the next one. And we also invalidate our timer. So get world timer manager, clear timer, mag eject timer hand. Okay, next up is the load magazine function. This is a little bit of a bigger function again, so I will implement it first and then explain it. Okay, so first we check that the loader magazine is invalid. Then we want to check that the new magazine is valid, and we also want to make sure that it is the same matching magazine class. Then we will set the constraint components of our magazine constraint, and we also want to set the constraint reference frame to the magazine constraint relative transform. This moves the magazine to the correct position. After that, we want to get the owner of the magazine, which should be our VR character. If the owner is our VR character and we didn't just pick it up from a table with our weapon, then we want to release the grabbed actor, which is the magazine, so our player is no longer holding onto it. Then we can set the loaded magazine reference, set the owner to this weapon, and play the magazine in sound. Next, we have our onMagazine begin overlap event. Here we want to check if the other actor is a magazine. So magazine calls to a magazine base from the other actor. And then we want to load the magazine. There we go, that's already it. Then in our interface function getSlide component, we simply return the slide mesh. In fire weapon, we first want to play the trigger click sound. So U gameplay statics, play sound at location, world, trigger click sound, and then the trigger mesh get component location. So it plays the trigger click at the trigger mesh location. Then we add a switch. This is our selected firing mode. Case FM single break. And now we can just copy this 3 more times. And here we have FM semi-auto, FM triple, and FM full auto. Now in FM single, we simply just fire, and in semi-auto as well. Now in triple, we want to set the current firing count to 0, and we'll set the actor tick enabled to true. Then we can copy this because in full auto, all we do is set the actor tick to enabled. That's already it for firing the weapon. And then for stop firing the weapon, all we do is set actor tick enabled to selected firing mode equal FM triple and current firing count is less than max firing count, and if the slide is not being held. This might seem a bit confusing. However, when we release the trigger, we will call the stop firing weapon function. However, while our weapon is still triple firing, and for example the current firing count is still at 1 or 0 maybe, just not at the max firing count, we want to continue to fire. Unless of course we start holding the slide, then it should stop. So with this, even if you press the trigger really quickly and release it again, while it is triple firing, it will still shoot those 3 shots, or how many shots you set in the max firing count. And if it's set to anything else than triple, it will stop as soon as you stop fire the weapon. The next function is a bit bigger again, the change firing mode, so I will implement it and then explain it. Alright, so at first we check if we have more than one firing mode, and if we do, we want to find the index of the selected firing mode in our firing modes array. If the found firing mode would be -1, it means that the selected firing mode was not found in the firing modes. This can happen, for example, if you forget to set it in the blueprint, and if it doesn't find it, we just want to set it to the first index of our firing modes, and then we can use the same index for our firing mode selector rotations. This is why we created this array, so it's easier to set the selector mesh rotation. However, if we did find a firing mode, then we want to check if the index is the last item, and if it is, we go back to the first item, so at index 0, and in any other case we want to increment the found firing mode index and then set the firing modes to the set index and the selector mesh rotation also to the found rotation in our firing mode selector rotations array. And then, of course, play the firing mode sound at the location of the selector mesh. Then for release mag, all we have to do is to call init mag ejecting and then get world timer manager, set timer, mag eject timer handle, this a projectile weapon base, and the finish mag ejecting function. I'll add a delay of 0.5 and we do not want it to loop. Then in pull trigger, all we do is get our trigger mesh, and here we'll set the relative rotation to an F rotator, F math lerp from 0.0, which would be the starting point, to the trigger max rotation and the alpha. And the other rotation we want to be 0 and 0. Here, of course, this trigger max rotation, we set it as a float because I just assumed that a trigger is always pulled on the pitch axis. However, you could also make this a rotator. Now in start moving slide, we first want to check if we aren't holding the slide, so B is slide being held. For now, this whole condition will always be true because we have no one else who could be holding the slide. So yeah, this is like a very early stage multiplayer functionality that if someone else is already holding the slide of your weapon, you cannot pull the slide. So then we want to set the B is slide being held to true, and we want to set the actor tick enabled false, and the relative slide hand start location is equal to U Kismet math library, U Kismet math library, make relative transform. We want the MC get component transform, and it should be relative to our weapon mesh get component transform. We get the weapon mesh and not the slide mesh because the weapon mesh is the origin of our weapon, and then from this whole new relative transform we want to get the location. Then in stop moving slide, we first want to set B is slide being held false, and then we want to check if the slide is pulled, so is slide pulled. Then we want to check if we can load a round, and if it does, we want to release the slide. However, if the round was not loaded successfully, we want to check if the slide is stuck, so B is slide stuck. Then we want to release the slide. This is so if the slide is already stuck, we can just simply grab it and let go, and then it will be released. And by the way, even if a mag is still attached, that is empty. So first time you do it, it is released. Then if you were to pull it back again, then it would get stuck again. And if it isn't stuck, we then want to set it to stuck. So B is slide stuck true. This is again if we pull it back while it isn't already stuck, but the mag is empty and the slide should not be released. Then if we let go and the slide isn't pulled, we want to first check if the slide is released, or isn't released, I should say. And if it isn't released, we want to release the slide, because that would mean that it is somewhere between being pulled and being released. And since our semi-automatic weapons use a spring for the slide to always move it forward, this will move it forward again. Next up, we have our move slide function. The longer function again, I will implement it and then talk about it. Okay, so first the move slide function is called every time while our input triggers on our update interacting, and we move the slide accordingly on the x-axis, and we want to clamp it because otherwise it will go past its travel distance. And here again, the minimum value is the slide travel distance of our clamp, because this is negative, because it goes against the direction where the weapon is facing, and 0 would be where the slide is fully closed. And to move it, we want to get the relative offset from our current motion controller transform to the weapon component transform, then its x location, and then we subtract our relative slide hand start location x location, which we set in start moving slide. Then while we move it, we want to check if the slide is pulled, and it will also move the slide back. So it's just a snappier feeling, and in my opinion, it feels a little bit better. And then we can eject the shell. However, if it isn't pulled, then we want to check if it might be released. And if it is released, then we want to do the same as we did with moving the slide back. We want to release the slide, which means it snaps forward a bit. After that error tolerance, it will play the release sound, and the weapon will be ready to be fired. However, if it is somewhere in between, then all we want to do is want to first check if the slide was already pulled and if the loaded ammo is invalid, because that means that we are moving from back to front. And then we want to load the next round. Now in set primary and secondary hand, those are easy. We just get our primary hand and set it to the hand, and then the same for the secondary one. And our primary hand trigger pulled animation, we just return the primary hand trigger pulled animation, and in slide grip animation, we just return the slide grip animation. And that is all for our projectile weapon base. Now I will compile just to make sure everything is still fine. And yes, the build succeeded, so everything is working as intended. Next, we are going to create our shotgun base class, and this will be a child class of our projectile weapon base class. Shotgun base, and I'll create the class. Great, now that we have our class, we can again add our includes. So we'll need the ammo box base, the ammo base. Actually, I'll duplicate this, ammo base, and we also need the ammo container component. And from the engine, we want the Kismet gameplay statics from the component box component and the static mesh component. Now we can add our variables and functions. Now for the components, we have a new property, which is visible anywhere, blueprint read only, and in the category component, this is our static mesh component, which is our latch mesh. And for upgraded, I'll add the class definitions. So ammo base, static mesh component, and the ammo container component. Then we have our ammo container component, which is our ammo container. Now in the latch section, we want an edit anywhere property. I'll put this in the category variables and the subcategory latch. So here we have an F rotator, latch, rotation offset. They'll add a default rotation pitch of 20. Then we have the float, which is the latch reset delay. This defines the delay of how long the latch is open until it closes again. Down here we have the configuration, and all we have here is a bool, which is B has internal ammo storage, which is by default true. We use this so we can differentiate between the two types of shotgun, one that stores ammo inside and one that takes ammo from a magazine. Then for our functions, here we have our default constructor, a shotgun base. Then we have a virtual void tick, float delta time, and override it. Then we have a void load ammo. We pass an a ammo base, the ammo to load. Next function is void move latch and the reset latch. That we want a virtual bool called load round, and we want to override it, and a virtual void on magazine begin overlap, which takes a U primitive component, the overlapped component, then the A actor, which is the other actor, another U primitive component, which is the other comp, an integer, which is the other body index, then a bool, which is from sweep, and a const f hit result, which is the sweep result. And here we don't add a U function because if you remember in our projectile weapon base, here we have a virtual void on magazine begin overlap. Here it is already defined as a U function. So all we need to do is to override it, and that's that. So oh yeah, I almost forgot. So make sure to override it here at the end. Then for our interfaces, all we are going to use is the virtual void stop moving slide. Override it, and then in the protected section, all we have here is the virtual void begin play. Override that as well. And here we can start creating our meshes. The latch mesh doesn't need any collision because it's purely cosmetic. Therefore, it also doesn't need to generate any overlap events or hit events. There we go, and we'll move the begin play up here because that's how it's by default. Then call super begin play, the same for the tick. And then in begin play, we want to check if B has internal ammo storage is false, and if the ammo container is valid. Because if that's the case, we want to destroy the ammo container, destroy component, and also destroy the latch mesh. Because if it doesn't have internal storage, it doesn't need those two because that means that a magazine is attached. And actually, let's also check if the latch mesh is still valid, just in case. Because again, in C++, if you don't check if something is valid and then try to call any function or any property from it, it will simply crash your game. There won't be just an error message in the background like it does it in Blueprint. It will just simply crash. Then the tick we can leave as it is because all of our firing logic is in the tick of the projectile weapon base. However, in load ammo, we need to add logic to load ammo into the shotgun when it's overlapped. So I will add that now and then explain it. Okay, so first we check if the ammo that we pass into the function is valid. If it is, we want to check if it matches the ammo class. And we also want to check if we can still add a single round to the ammo container. Because if it's already full, we obviously don't want to add it. All of this is true, then we want to play a sound at the location. Here I will just use the mag in sound. So here you can just use a different sound, like one of a slug being loaded. And we will still use the magazine hitbox to detect the ammo that we are loading. Then we want to get the ammo box of our ammo to load and then clear the spawned ammo. This will make sure that the ammo is destroyed and that it won't return to the ammo box when we let it go. And if for whatever reason the ammo box is invalid, maybe you want to have a survival game where there's just ammo laying on the floor, then it would simply be destroyed. Next comes the move latch function. This is a small function, just check if the latch mesh exists. Oh, and actually, I just realized I also want to make sure up here that the ammo container exists, just in case. And then latch mesh set relative rotation to the latch rotation offset. Then we will create an F timer handle I'll call this th. We get the world timer manager, sets timer, th, this, and then we will call a shotgun base, reset latch. Here we have the latch reset delay, and we don't want it to loop. And in the reset latch function, all we do first, we will again check if the latch mesh is valid, and then we will set the relative rotation of the latch mesh to 0. So set relative rotation, f rotator, 0 rotator. Then in load round, we first want to check if the loaded ammo is invalid. Then we want to check if it has internal storage. And if it does, we want to again check the ammo container and remove a single round. Because again, if this is true, this should already be valid. Then we can spawn loaded ammo, the ammo container, and here we will pass the ammo class. And then we return selected firing mode does not equal FM single. Because if it is single, we don't want the slides to automatically move forward. Since on a pump action shotgun, we want to manually move it back forward. Then if the shotgun does not have internal storage, then we will just simply turn super load round, because that means there should be a magazine attached. Then in on magazine begin overlap, we want to check again if it has internal ammo storage. If it does, we want to check if the overlapped actor is an ammo base, or ammo to load, cast a ammo base. Here we want an ammo base, not an ammo box base, is the other actor. This is true, we want to load the ammo, which is the ammo to load, and to move the latch. However, we don't have internal storage, we will just simply call super on magazine begin overlap and input all of the other parameters. So overlap component, other actor, other component, other body index from sweep, and the sweep result. There we go. And at last, we want to stop move the slide. In here, we first check if the selected firing mode is equal to FM single. And if it is, we just simply set is slide being held to false. And in any other case, we just call super stop moving slide. And that's already it for the shotgun class. Next, we are going to create our settings menu. So in our C++ classes, right click, go to all classes, and search for user widget. Select user widget, and then I want this to be not in the weapons folder, but in the widgets folder. And I will call this the audio settings widget, and then create the class. Great, now we can add the includes. Here we want to include our VR safe game, and from the engine, sound mix, sound class. From the components, we want the slider, and from Kismet, we want the gameplay statics. Then first for our classes definitions, we have the class U slider, class U sound mix, and the U sound class. In variables, the first one is a U property, meta equals to bind widget. This means that our blueprint widget, where we will do all the graphical stuff, will not be able to compile successfully if we don't have a component with the same name and the same component type. And this here would be our U slider, and this is the master volume slider. So we will have to add a slider component to our blueprint widget, which is named master volume slider. And for now, I will keep this simple and only add a master volume. Then we have a U property, which is edit anywhere, blueprint read only. Then the category variables doesn't really need more. And this is the float current master volume. And I'll set to a default value of 1.0. Then we have our U sound mix, which is our sound mix modifier. We will need to set this so we can apply our audio changes. Then we have a U sound class. This is our sound class where we want to apply the modifier to. And at last, a visible anywhere property, which is the F on audio. Oh yeah, right. My bad. I forgot to add the delegate. We have the declare dynamic multicast delegate, which is the F on audio settings changed delegate. I'll call this on settings changed. And don't worry about this showing red for now, it will resolve itself eventually. And for our functions, first we have the virtual void native construct. We want to override it. Then the virtual void native on initialize, also override it. And we have a U function, which is blueprint callable. We want a return type of float and call this get master volume value. Then a U function without anything else. This is void on master volume changed, and it takes a float, which is the value. We will be using this to change our current master volume variable after the value has changed. And then we have another U function, which is a void on slider let go. We will use this as soon as we let the slider go to save our changes, because if we did that in the on master volume changed, then we would try to save after every change, which is just unnecessary. And then at last we have void apply audio settings. Great, now let's create these functions. There we go. And here we have super native construct. Here we have super native on initialize, and here we have the master volume slider value delegate dot bind U function. Here we have this, and then get the master volume value. I want to get the master volume slider again. And the on value changed, adds dynamic, this U audio settings widget. And then we have on master volume changed. I'm going to duplicate this to make it a bit easier. Here we have on slider let go, and we want this to be our on mouse capture end. There we go. In the get master volume, we simply want to return the current master volume. And in on master volume change, we want to first apply the audio settings and then set the current master volume to the value. Actually, no, we want to do that first and then call apply audio settings. Then on slider let go, we first want to cast to a UVR save game. So UVR save game equal to UVR save game load VR save game from slot. Here we will get the UVR save game get default slot name and the index 0, or the player index 0, I should say. In here we have save game. We want to set the master volume to our current master volume, and then we get UVR save game, save VR game to slot, our save game object, UVR save game gets default slot name, and the player index 0. And then we can call on settings changed dot broadcast. The reason why I didn't suggest it here, because this is still red for some reason, but that shouldn't be an error. Actually, I'm going to try to compile. Nope, it's just Visual Studio's issue. And in apply audio settings, what we want to do, we want to get the U gameplay statics, set sound mix class override, get the world, the sound mix modifier, sound class, and the current master volume. And then again get the U gameplay statics, push sound mix modifier, the exact version, just the regular one, get the world, and the sound mix modifier. There we go. That's already it for this. Next, we will create the general settings widget. So actually, I'm going to go back and go into widgets, new C++ class, user widget, and I'll call this general settings widget. Create class. Great, and let's add the includes again. Include VR save game, and from the engine we want components button, and also from the components the text block. Here we want class U button, class U text block, and here we want to include the VR character because we will need our turnstiles. Then we want to declare a delegate, declare dynamic multicast delegate. I'll call this F on general settings changed delegate. And here we have a U property, which is visible anywhere, blueprint only, category variables. F on general settings changed delegate, and I'll call this on settings changed. Then we have a U property, meta bind widget button, which is the previous turn style button. Another U button, which is the next turn style button. Then we have a U text block, which is the turn style text. Copy this whole block. This is the previous movement direction button, next movement direction button, and the movement direction text. Oh, and almost forgot, we have the property which is visible anywhere, blueprint read only. This is a t enum as byte, e turn style, which is the current turn style, and then the same for our movement direction. So again, t enum byte, e movement direction, movement direction. For the functions, we have again our virtual void native construct to override it, then virtual void native on initialized void save general settings. Then we have a u function blueprint callable void next turn style, previous turn style, and f text, which is the get turn style text, and then the same for the movement direction, next movement direction, previous movement direction, and get movement direction text. And again, call these super functions. Here I'm going to set up all of the events. Great, and save general settings is pretty much the same as we did in the audio settings, just for the turn style and the movement direction. Oh, I just realized I named this incorrectly. There we go. I'm just going to make sure that it still compiles because of this event here. Great. In the next turn style, first we want to check if our current turn style +1 is greater or equal TS for turn style max. And if it is, then the current turn style should be equal to E turn style 0. If it isn't greater or equal TS max, we want the current turn style to be equal to E turn style current turn style +1. And then at the end, we save the general settings. Now with this system, you can add your own custom turn styles. Doesn't matter how many you add. As long as TS max is at the end, then this system will work perfectly fine. You won't ever have to change anything here. You will always be able to loop through it. So even if you're at the end, you will just restart at the first turn style. So this makes it a whole lot easier to add custom ones. Now for the previous turn style, here we first check if the current turn style is less or equal than 0. We could just check if it is just 0, but just to make sure, I will make sure that it's less or equal 0. Current turn style is E turn style TS max -1, and otherwise we can get the current turn style and set it to E turn style current turn style -1, and then save the general settings again. For the E turn style text, what we want to do here, we want to get the U enum, and here we want to get display value as text from the current turn style. What this does in our turn style, here we set this display name. That's what it will return. So it will say, in our text, it will then say snap or smooth. And now we do the exact same just for the movement direction. There we go. And that's that. The next class that we are going to be adding is our graphics settings widget. Graphics settings widget. Also make sure that this is in the widget folder. Great, and now let's add the includes. What we need here is from components, the button, then the Kismet system library, and from the game framework, the game user settings. And here we have our class U button. I will keep it simple for this graphics settings widget. And that means I will just add a button that sets the overall quality to low, medium, high, or epic. Of course, you could add individual buttons for changing every individual setting. However, I think that would be a bit too much for this tutorial, so I'll just keep it simple. So first we have our U property, meta find widget, and this will be a U button, the all low button. Now I will copy and paste this 3 more times. This will be all medium, this will be all high, and all epic. Then the next property is editable anywhere, blueprint read only, category variables. And here we want an F linear color. This is the selected color, and it's equal to F linear color. I'll choose blue. We can paste this and change this from selected to unselected color, and I'll choose gray for that. And down here in the functions, as always, you have our virtual void native construct. We write it virtual void native on initialized. Then we need a function to set the graphic settings. So it will be a U function, so it's blueprint callable. Then I'll call this set all low as well. We can copy and paste this 3 more times, and then we can rename it from low to medium, high, and epic. There we go. That's all the functions we need. In here, we want to make sure to call the super native construct in here. And here we want to switch on the game user settings, and we want to get the game user settings and get the overall scalability level. This will return an int. So our first case will be case 0, case 0, and we want to set all low. Sure to break. Now I'll copy this 3 more times. Then this would be case 1, 2, and 3. And here we have all epic, all high, and all medium. And I'll also add a default case. And here I'll set all to epic. Of course, you can also choose a different quality. Then in native on initialize, we will set up our button press events. Dynamic, this fix settings widget, set all low, and then do the same for the other buttons. Now in set all low, what we first want to do is get the game user settings, get game user settings. Then we want to set the overall scalability level to 0, and we want to change the color of our buttons. So all low button, this one is supposed to be blue now since we selected it. So set background color to selected color. Then we have our all medium button, set background color to unselected color. And then we do the same for the other 2 buttons. Then we can copy all of this, go into medium, here it would be scalability level 1. And now we want this to be the selected color and this to be the unselected one. For high, we have the scalability level 2. This and unselect this color. And here's for the epic settings, we have the scalability level 3. And we want this to be selected color and this to be unselected. Oh, and very important, one thing that I forgot is to get the game user settings and get the game user settings and then call apply settings true. True will just make sure that it checks for command line overrides. And this will also save your graphics settings. So you don't have to worry about actually having to save all of these values in your save game. It will automatically save it in its own save game. Yeah, that's already that for the graphics widget. So let's compile and see if everything is fine. There we go. Everything was successful. Okay, now next we want to create the overall settings menu widget. So right click again, create another user widget, and this I'll call settings menu widget. And for the includes, we need to include our VR save game, our widgets, audio settings widget, and the other 2 that we've created as well, general settings widget. Then we need a button component, also a widget switcher, and from the game framework, the game user settings. And here, let's define the classes again. U button, U VR save game, U widget switcher, U audio settings widget, U general settings widget, and U graphics settings widget. Then we want to declare dynamic multicast delegate, which is the F on settings applied delegate. First we have a U property, which is meta find widget. And we have a button, which is our back button. This is how we get back into the main menu. And we have another button, which we use to view our general settings. So general button, and also one for the graphics and for the audio settings. Then we'll need a U widget switcher. It's going to be our widget switcher. And to make sure that our settings widgets are actually defined, we can create another U property with the meta bind widget. Then we have the U general settings widget, which is our general settings widget. This makes sure that we do set this widget in the blueprint. Otherwise, it won't be able to compile. And then we do the same for the graphics and the audio settings widget. And at last, a U property that is visible anywhere, blueprint read only, and category variables. Although you don't really the category here, I would say, but I will still add it just so everything is the same. And here we have our F on settings applied delegate on settings applied. Great, and now we can continue with the functions. There we go. Then you have a U function, blueprint, callable, void apply settings, another U function, void open general settings, open graphics settings, and open audio settings. So here again at the super native construct, and in here we also want to get our save game, UVR save game, load VR save game from our default slot. And here we initialize the settings on our general settings widget. Current turn style, save game, turn style. Same for the current movement direction. Then we also have the audio settings widget, current master volume. And here we also need to make sure to apply the audio settings. Then in native on initialized, we also have our super. And here we set up the button presses. And here we make sure that we bind our apply settings event to the on settings changed, the general and the audio settings widget. There we go. Now in apply settings, all we want to do is to broadcast our on settings applied event. Again, this didn't show up in the IntelliSense because of Visual Studio. If open general settings, we want the widget switcher set active widget to be our general settings widget. And for the graphic settings, it's graphic settings widget, and here the audio settings widget. And that's already it for the settings menu. Next, we will be creating our hand menu widget. Again, let's add all of the includes, which is our save game, our VR character, and from the widgets, the settings menu widget. And from the engine, we need a button, and we also need a widget switcher. At last, from Kismet, the Kismet system library. And for our classes, we have class U button, a VR character, U widget switcher, and U settings menu widget. Great, and then we can again add our variables. At the first, doesn't need to be a U property at all. This is just our A VR character, which is our player rep. Then we have a U property, meta bind widget. Here we have a U button. This is the auto height button. We will use this to automatically calculate the height of the player. Then the next button is the settings button, and another U button, which is the quit button. Then we need a U widget switcher, which is our widget switcher. And at last, our U settings menu widget, which is the settings menu widget. And here again, we have virtual void native construct, which will override. Then we have a U function, which is blueprint callable, void recalculate height, and another U function, which is the void open settings menu function, another void quit function, and void return to hand menu. And now we can call the super construct. And then in here, we want to check if the owning player is valid, so get owning player. And if it is valid, we want to set our player ref cast a VR character, get owning player, and then get the pawn. There we go. Here we will set up the button events again. Here we set up the onPressed event for the back button. So when we're in the settings menu and we press back, we get back to the regular hand menu. There we go. Now in recalculate height, first we want to check if our player reference is valid. Then we want to get the player ref and calculate height. And then we also want to store this in the save game. If view VR save game, first we need to check we already have a save game. And then save the VR game again. Then in open settings menu, we simply get the widget switcher, set active widget to our settings widget. Since it has the meta bind widget, it should always be valid, otherwise the blueprint won't compile. And in the quit, we get the U-Kismet system library, and we call quit game. Here we input the get world and get owning player and the eQuit preference, which I'll just set to quit. And I'll set ignore platform restrictions to false. When we want to return to the hand menu, we simply get the widget switcher and set the active widget index to 0, since we will be creating the hand menu inside of the first element of the widget switcher. And now let's compile it. It's fine. And now we're done with that. Now we can come back into the VR character. And now let's come back to the begin play function. And in here, let's set up the delegate of our hand menu. So if view hand menu widget, here we want to get the hand menu and get the widget, because we will be setting this in the blueprint. So, and if that is valid, then we just check the hand menu widget. And if the settings menu widget valid, oh, and I just forgot, we also have to include this to the save game. Actually, we can include all of those. There we go. So make sure you now add the includes if you haven't already, the VR save game, shotgun base, hand menu widget, and settings menu widget. And if this widget is also valid, even though it might seem a bit contradictory, because in the hand menu I told you that this will always be valid because the blueprint won't compile otherwise, it would still be able that we could create the blueprint even though it's invalid. But if we then set the blueprint in our character, even if it doesn't compile, and it then tries to access the settings menu widget, it would most possibly crash the editor. So just to be sure, I'll add this check here. Then in here, we can get the settings menu widget, get the on settings applied, delegate, and add dynamic this, and the AVR character on settings applied. So every time we apply a setting in the settings menu, this on settings applied will also apply the settings to our VR character. Then here in the load VR save game, this is the next function that we need to implement. Here I will get our VR save game, and in here we want to set the turn style to the save game turn style. Same for the movement direction, and same with the base height. There we go. Then the next thing we need to update is in our stop grabbing right function. Here we need to implement the shotgun class. So here first we want to check if our right weapon interface is invalid, or if our right grabbed actor is a shotgun base. And we don't have to check if this is valid because we already do it up here. And we need to do it this way because if we're grabbing a shotgun, our right interface is invalid. Then we want to call stop grabbing and input the RPC, right grabbed actor, and the left grabbed actor as the other actor. And then we want to check if the interface exists. So I weapon interface on the right grabbed actor. And we want to call the weapon interface set secondary hand to E controller hand, any hand. And then we set the right grabbed actor to null. And here we have to check if our right interface is invalid or not, because when we are grabbing a shotgun, this interface is invalid, but our right grab actor would be a shotgun then. So we cast to the interface from the right grab actor, and then we can still set the secondary hand to none. Because on the shotgun, we want to be able to move the slide while gripping the weapon and not while pressing the trigger. That would just not feel natural. And then we can just copy this, come down here to stop grabbing left and implement the same just for the left now. Now we can continue with the start grabbing function. This is a bigger function again. I will first implement it and then I will explain it to you. Okay, so first thing we do, we will trace for a grabbable object. Then we assign the actor of our hit to its local variable. Then we want to check if the hit actor is actually valid and if it isn't an ammo base, because we could be holding an ammo in our other hand and try to grab that, and we don't want that. Then first we check if the actor that we hit, if its owner is a weapon, because if it is, then we have hit a magazine or in the future an attachment or something like that. Then we want to get the root component because we want to grab the weapon mesh. This makes sure when you grab, for example, the slide, that you automatically grab the weapon itself and not the slide, because then it would be off again. You only want to grab the slide when it's either a shotgun, and otherwise you only want to grab the slide with the interaction. So then we want to check if our hit actor is equal our other grabbed actor, and if the other hand is the main hand. If it isn't, we set our main hands to false, and then first check if it's a shotgun. And if the shotgun has the firing mode single, then we also want to make sure that we get the interface, and then we want to make sure that the slide component is valid. I know this isn't very pretty. This is actually a programming sin, but I haven't found a much cleaner way to do this. That's why it looks like that for now. Then we constrain the components. We set the constraint reference frame. This just aligns the weapon and the hand mesh to the correct position and rotation. And the reference frame 2 we just set to an empty transform. I can't explain exactly how these reference frames work. It basically sets the offset between the two constraint objects to the physics constraint, and this is the way where I managed it to work, but my whole understanding of this is still a little bit blurry. And then we can call start moving slide on the interface and return our shotgun that we've grabbed. However, if it isn't a shotgun, then we first set the constraint components. We make sure that our component to grab has the socket, the grip socket, because otherwise we don't want our hand to snap to that bone's location because, well, it doesn't exist. And then our procedural hand animation would take over. However, if the bone does exist, then we can again set the constraint reference frame, and then we return the hit actor. And if our weapon doesn't equal the other grabbed actor, or if the other hand isn't the main hand, then we know that, for example, we've held a weapon in two hands and we've let go with our main hand, or we are grabbing a weapon that we aren't already grabbing. Then we can set the main hand to true, can set the constraint components, and then again make sure the socket exists so our hand has something to snap to, and return the actor. And if everything fails, we just return null. Next comes the update grabbing function. This is mainly for the shotgun. So first we want to check if our B is main hand. Well, if it's not the main hand, then we want to make sure that our grabbed actor is a shotgun. Then if our shotgun, the selected firing mode is equal to FM single, then if the weapon interface is valid, so I weapon interface, and if the slide component is valid, then we want DC set constraint reference frame, the constraint reference frame, constraint frame 2 in this case, and WI get slide component, get the relative location. Oh, I just realized, my bad, we don't want to set the reference frame but the reference position. And then from WI we call move slide, MC get grip bone name, and to the bone to constraint 2. That's already it for update grabbing. And stop grabbing, pretty simple. We simply get the physics constraint and break it. Then we check if the grabbed actor is valid, and the grabbed actor does not equal the other grabbed actor. I just realized I named this incorrectly. My bad. Other grabbed actor, that's what it should be. And if that is the case, our grabbed actor, we can set the owner to null. Because if you remember, if the owner is null, the weapon won't do any damage. This is to prevent us or an enemy from simply walking over a weapon and just dying or taking damage at all. And if we let go, for example, with our secondary hand, and the owner would be set to null, then obviously our weapon wouldn't deal damage anymore. So we only want to do this if we completely let go of the weapon. And here in the release grabbed actor, this is what we call when we insert a magazine and the weapon actually tells the player to let go of the magazine. Here we want to check if the grabbed actor that's incoming is the right grabbed actor. And if it is, call the RPC, break the constraint, and set the right grabbed actor to null. And the B is right main hand to false. Else if, or actually, we can call return here. Otherwise, we can simply copy this all and then do the same for the left. There we go. Next is our trace for objects function. Here I'll create a hit result, I'll call it hit. And here we'll get the UPismet system library, the sphere trace signal for objects. Then we'll get the world. Actually, I'll do it like this so you can see it a little bit better. Get the motion controller, get the component location. And for the end, we also get the motion controller component location. However, we are going to add an offset of 1 to the z-axis. This might seem a bit confusing. However, I found in the past that when we don't add the offset, the trace can sometimes be weird. I haven't had the problem as much in the newer versions, but in 5.1, which I'm using for this tutorial, it happened quite a lot. That's why I add an offset just so the trace is done properly. I understand if it's a bit confusing, it's just what I found to work. Then we put the grab radius, our object types, then we want false because we don't want to trace complex. Actors to ignore should be this. Draw debug trace with none. You can set something else if you want to debug it. Then we have our hit, and we also want to make sure that it ignores itself. And then we can simply return our hit. There we go. Next, we'll do the interactions. Again, I will implement it and then explain it. Okay, so first, we want to check if we can interact with a weapon. And if this fails, we want to check if we can interact with an ammo box. However, if after both of these, the right grabbed actor is still invalid and our right weapon interface is valid, that means that we are currently pulling a slide on, for example, a pistol. So we want to set the animation of the right hand to the slide grip animation and return. However, if this is also invalid, then we want to press the pointer key on our widget interaction because only then we want to be able to interact with the menu. I did this so it wouldn't get confusing. For example, when you're holding a weapon and you also try to interact with the menu, then you would have shot the weapon every time you try to interact. Then in update interacting right, we simply call update weapon interaction. Then we input the right weapon interface. The B is right main hand, the RMC, the right hand phone, and the RPC. And that's it for that. And in stop grabbing, we are going to do the following. So here first we want to release the pointer key because if we press it up here, then it will remain pressed. So if we try to press it next time, it wouldn't work anymore. So that's why we need to release it first. Then we check if we can stop interacting with the weapon. If this fails, it most likely means that we are holding ammo from the ammo box. So we want to stop that interaction and then simply return. However, if this succeeds and our right hand isn't the main hand, then we want to change the hand animations to null. So go back to the procedural animation and also delete the reference from our right weapon interface. If our main hand isn't the right hand and we stop interacting, it means that we were gripping a slide and didn't just pull the trigger, because if we stop interacting, however, we're holding the weapon at the handle and simply pull the trigger, then we don't want to set the right weapon interface to null, because otherwise next time we couldn't fire the weapon again. And now we do the exact same for the left. There we go. Now, one thing that's important, the way I create the animations, I will only be creating the left-hand animation for the slide interaction, so we don't need to mirror this. So make sure this is false, because otherwise it will mirror the wrong hand. Oh, and also, since our left hand does not have the interaction component, when we begin interacting left, we don't need to press the pointer key. So we can actually shorten this a bit, and we can also do this check up here, so we have one if statement less. It's a little bit cleaner. There we go. For this tutorial, we will only be interacting with the menu from the right hand. Great. Next, we have our release mag right function. Here we have an if clause, and we want to check if the b is right main hand, and if the right grabbed actor is valid, and if the right weapon interface is valid as well. If it is, we call the right weapon interface and then the release mag. Then we can do the same for the left. And for changing the firing mode, it's pretty much the same, just that here we call change firing mode. There we go. The apply recoil function is a bit bigger, so I will implement it first again. Here we only need the left and right hand. Okay, so here we have two hands, and in each one we want to add our location and pitch offset to the appropriate offset, so the left recoil offset and the recoil pitch. Then we check if the left recoil timer is not valid, because if it isn't, that means the recoil isn't currently being lerped. So we want to create a timer for our recoil timer handle, and here we create a lambda from our ftimer delegate. We have to do it like this and not with the other function that we've used where we've input the function by a string, because with this we can actually pass the addresses of parameters, and for some reason it wouldn't work the other way. That's why we have to do it like this. Then we pass our left recoil offset, the left recoil pitch, and the recoil timer handle. And then we want this to loop with our recoil lerp timer interval. Coming up, the next function is the lerp recoil function. So here we have our location offset, which is equal to f math, then lerp between the location offset and f vector 0 vector. And here we have our recoil lerp alpha. Then we have our pitch, and here we do the same. So f math lerp pitch, and we want it to lerp down to 0.0, and again with our recoil lerp alpha. And if our location offset is nearly 0, with a tolerance of 0.1, and f math is nearly 0, our pitch also 0.1, then we simply want to set the location offset to a 0 vector, and then the same with our pitch. And then we get the world timer manager, clear timer, recoil th. This is why we need to pass the address of our variables so we can change them in here. And you don't have to write basically the same code once for the left and once for the right. Next is our check for slide function. So first we want to check if the actor is valid that we've passed. Then we want to check if the actor's owner is a weapon, because if it is, it means that we are trying to interact with the magazine. And then we want to check if it implements the weapon interface. And if it does, then we want to set the interface first, then check if the slide component is valid, and then constrain our hand to it. And at the end, we want to start moving the slide and return true. Otherwise, we return false. Now in here, in get grip bone name, we will be naming our grip bones that we use for the grip location and rotation. Grip underscore plus hand bone name dot to string. And this is how we are going to name them. So we always want to name them grip underline and then our hand bone name. So for example, hand R or hand L. So with this, you only have to change it here and not in 100 different places. And then we practically do the same for our handle bone. Just instead of grip, it's called handle. Next, we have our start weapon interaction function. Okay, so first we want to check if our grabbed actor and our weapon interface is valid. If they're both valid, it means that we are holding the weapon at the handle. So we simply want to fire the weapon and return true. However, if none of them is valid, then it means that we are currently not holding anything, and we want to trace for our grabbable object. And before we check for the slide, we want to make sure that what we are holding or trying to interact with is not a shotgun, because we want to move the shotgun slide when gripping the weapon and not when pressing the trigger to interact with it. So if that is the case and the shotgun has selected firing mode FM single, where we have to pump it manually, then we simply want to return false. So if you have a semi-automatic shotgun, then this would still work. And if it's not a shotgun or a semi-automatic shotgun, then we can simply check for a slide and return its result. And otherwise, we simply return false. Then in the update weapon interaction, all we do is we check if the web interface is valid. We check if it is not our main hand, and if from the widget interaction, the slide component is valid. Now, if it is, we want to move the slide to the motion controller, get grip bone name, bone to constraint 2. And then the physics constraint, we want to set the constraint reference position of the E constraint frame 2 to the weapon interface, get slide component, get relative location, and return true. This here will make sure that our hand will move with the slide that moves, because otherwise, apparently simply constraining the two components isn't enough. Otherwise, the hand will just stay put while the slide moves. I think that is because our slide doesn't simulate physics, only its owner does, and that's why it doesn't follow along automatically. I tried having the slide also simulate physics, but then we would need another physics constraint, actually 2 more physics constraints on our weapon. One, so the magazine can't hit the slide, and another one to make sure that the slide is constrained to the weapon and doesn't just fall off. So I found this to be a simpler solution. Then in the stop weapon interaction, we check if the weapon interface is valid, that we pass. Then if the grabbed actor is invalid, and if it is, we simply want to break the constraint, and with widget interaction, stop moving slide and return true. However, if our grabbed actor is valid, then we call the weapon interface and call stop firing weapon and return true. Otherwise, return false. Now in our ammo box interaction, we want to check if our grabbed actor is invalid, then create a hit result, trace for objects, MC grabbable object types. Then we want to check if the hit actor is an ammo box. If it is, we set the grabbed actor to the ammo box, take ammo, and we input get mesh, and we pass the bone to attach to. Now when stop interacting with the ammo box, we first want to check if the grabbed actor that we pass is an A ammo base. Here, if the grabbed actor is invalid, this will simply be null and it won't enter the condition at all. And then we have the A ammo box base. This is the owner of the ammo, and that is valid. We simply want the ammo to return to the ammo box, so return ammo. And if the ammo box is invalid for whatever reason, we simply destroy the ammo. And at last, we set the grabbed actor to null pointer. But make sure this is still inside of the if condition. Next, we will implement the climbing function. First, we want to check the motion controller is valid. Then create a local variable for our hit result, hit, and its trace for objects, motion controller. And here we will pass the climbable object types. Then we want to make sure that our hit is a B blocking hit. And then we want to set the current slipping speed to 0.0. Then B is climbing, we want to set this to true, and B is other climbing, we will set this to false. Next is the MC start location. This is the location of our motion controller. MC get component location. Then we want to make sure that the hit component is valid, and in here we want to set the climbing offset based on our hit. We want to get the character movement, and here we want to set the max step height to 0.0, so we won't snap off the ground and go up smoothly. Then get the character movement component again, and set the gravity scale to 0, because otherwise we would always be lagging downward since it thinks it's falling and tries to adjust for it. Then we want to get the velocity and set it to 0, vector, 0, vector. And at last we want to update the component velocity. Then we get the previous hit, set this to hit, and our sliding start normal, we will set this to hit.impact normal. Great, then in UpdateClimbing, we again check if the motion controller is valid, and if B is climbing is true. Then we want to add an actor world offset, of the MC start location minus our current motion controller location. And we want to make sure that it sweeps. Then we want to check if B can slip while climbing is true, or if the previous hit. Actually, I will rename this because I just realized that I named it incorrectly. Previous sliding hit, it should be. Or if the hit physics material is valid and the previous sliding hit physics material get has friction that is greater or equal than 1.0, then we simply want to update the climbing offsets from the previous sliding hit. However, else if the check slipping returns false, we want to pass our motion controller into that. If this is invalid, we want to stop climbing because it means we fell off a ledge. So MC, B is climbing, and B is other climbing. Now, real quick, the first one here, if you grab something that has a friction that is greater or equal than 1.0, you don't want to slip at all. Or if you disable slipping on your character altogether, then you can just simply set the offset. Otherwise, we have our check slipping function, which will update the character's position based on how much he should slip. And after all that, we can set the previous MC location to the motion controller location. There we go. Now in stop climbing, again, we check if the motion controller is valid, and if B is other climbing is false, and if B is climbing is true. Now we get the character movement component, set the gravity scale to 1.0, and get this component again. Set the max step height to the base step height. That's why we created this variable. And if B can launch character is true, then we can set the velocity to U Kismet math library, and we want to clamp the vector size of our previous motion controller location minus our current motion controller location divided by the get world delta real time seconds, and we want the range to be from 0.0 to, let's say, 600. If we didn't clamp this value, then player would be able to just fly off when he nudges himself into a corner. So that's to prevent that. And then we need to update the component velocity. And here at the end, we can set B is climbing to false. There you go. Next, we have our check slipping function. Here we have our motion controller check, then the F hit result, hit trace for objects, input the motion controller and the climbable object types. And if it is a blocking hit, then we first want to check the normal of our hit. With this condition, we want to see if the impact normal of the previous sliding hit is the same as the current one. And if it's not, then it means that, for example, there is suddenly a slope. So then we want to check if we can do a secondary hit, because if this normal isn't the same, then it could also mean that we are at a ledge and we are about to fall off. Or, for example, if you are sliding down a ball or a rounded surface, then this also would not be equal. And then you want to adjust your character's sliding direction, because otherwise you would just slide off the tangent of a round ball, and we want to slide along the ball. So we want to return check secondary slipping. We'll simply pass the motion controller. And then the next check is if the hit.impact normal.z, and we'll add a tolerance of plus 0.0001 is greater than 1.0. Sorry, not is greater, but is less than 1.0. Then we want to set the MC start location and add the update slipping offset to it. And here we'll pass our hit result. What this does is it checks if we have a slope. So if the Z value is exactly 1.0, then it means that we are grabbing a flat surface. And in this project, I made it so that if you're grabbing a flat surface that's looking straight up, you can always grab it, no matter how slippery it is. However, we add 0.0001 because I found that there is sometimes an error. Even if the surface is perfectly flat and looks straight up, it sometimes returns like 0.999999. And with this, we just make sure that even if it's almost correct, that we can get rid of that error. After that, we can call the UpdateClimbing offsets function and input hit, then set the previous sliding hit to hit and return true. Otherwise, we want to return check secondary slipping, input the MC. This is just because I realized, especially when transitioning from one mesh to the other, there was a tendency that one hit failed, but the second hit was still able to catch the error, or to catch that the player was supposed to continue to slide. That's why we also want to do the secondary slipping check, even if our blocking hit was false. Because if both of these are false, we know, okay, now we're at the ledge and now we can fall off, or we're supposed to fall off, I should say. Then the check secondary slipping, I will implement that real quick and then explain it. Okay, so here again, as usual, we check if the motion controller is valid. Then we create our second hit result, and here we create the impact rotation and the start. The impact rotation is the direction in which we sliding, and then we subtract 90 degrees from it, so it's facing the way of the face that we're sliding along. And start is defined by our motion controller start location plus the diameter of our grab sphere times the vector of the impact rotation. This will offset this enough so we can do the line trace, and here we set the ends, so all of this offsets the trace in the direction in which we are sliding, and then we can trace again for another face or object, and with that we know, okay, now for example, if we are sliding along a ball or a curved surface, we need to adjust our sliding start normal. Or if we hit another object, then, for example, if we're transitioning between two cubes, with our first hit, it is possible, since it's using a sphere trace, that it hits the face where the two cubes are touching. But that's not the face we want to slip along. So we do the secondary check, and this will return us the face that we actually want to slip along. And then we can use that to slide along the correct face. Now in set climbing offsets, we get our climbing offset, and we get the MC start location minus the hit.getComponent. And from here we want to get the socket location, and we want to get the hit.bone name. We need this offset because when we are climbing on a skeletal mesh, we want to keep the offset to the bone. Otherwise it would look weird when it is moving. Realized actually there should be a check if the component is valid, otherwise it might crash. Then we set the last climb actor quad to the hit.getComponent getSocket quaternion hit.bone name. We use this to rotate the actor along an object that is rotating. And for this, you will see it in a second when we update the climbing offsets. I've chosen to only rotate around the yaw axis, because I first tried to implement a system where we can rotate around any direction. But first of all, it's just a puke fest, like you will throw up. And secondly, it had a lot of issues with keeping the correct body location. And then together with the procedural legs, there were just too many issues to fix in this short amount of time. It might come in the future, but for now, we will only rotate around the Z-axis. Then I will implement this one and then tell you what I did. Okay, so first we check if the component is valid. Now if the hit component is not the same as the previously hit component, we want to set the climbing offsets again. And then we want to get our quad offset from our sock location of our current hit to the last climbing actor quad. This is just how you calculate this offset, or quaternions. I don't understand the whole math behind it. That's just what I found online on how you can do it. And then we set the climbing offset to the previous climbing offset, but we want to rotate this by our quad offset. Then before we rotate our VR origin, we want to set the X and Y axis to 0. These are the ones that rotate the actor around the pitch and the roll. Like I said before, we don't want this for now. Then we apply the rotation and we add this to the MC start location and also the last climbed actor quad. Now I will implement the slipping function. Now, this is quite complicated, I know. I created this once before and I got it to work. To be completely transparent with you, I don't understand everything exactly to the point. All I know is that I just tried, and this is what worked. So first we check if our physics material is even valid, because only then we are supposed to be able to slip. Then we want to get the clamped friction. However, if we have a friction of 1, we don't actually want to slip, because that's a lot of friction, or 100% friction, I should say. And if we have 0 friction, only then we should be able to slip. That's why we subtract the clamped friction from 0 to 1 from 1. And we clamp it just in case you set a friction that is, let's say, 10, for example, or maybe a user doesn't know that friction in this project should only go to 1. Then the friction would be negative, and then the player would slide upwards since the value would be negative. Then we have the slip speed. This is our clamped friction times the current slipping speed times the world delta real-time seconds. We have to multiply it by the delta seconds because the update slipping is called every tick. Otherwise, the slip speed would grow way too fast. Then we have our slip velocity. At the beginning, this is just downwards. And then we have our rounded normal from our impact normal. Here we round the normal up or down. This is, again, because of grabbing a flat surface that's pointing straight upwards that may return 0.9999, or if you're on the underside of something, negative 9.9999, because if you're on the underside of something, you just want to slip straight down. And if you're on the top, you don't want to slip at all. That's why if you're above 0, we want to add this little bit, and otherwise we subtract it, simply because of that error tolerance. Not pretty, but I haven't found a workaround for that just yet. Then we want to check if the rounded normal is between 1 and 0, or if the player can slide down an overhang, because if this here is true, it means we are not on an overhang, we are just sliding down a slope, and this is fine, that we can do that. However, if this is false, it means that we are grabbing onto an overhang, and usually you don't slide down overhangs, you fall straight down and you just fall off. But I added an option to enable can slip down overhang, then we can slide along the overhang. And then here we want to calculate the impact rotation. So we get the impact normal rotation, and then we subtract 90 degrees from the pitch. This is because we want to get the rotation of where we are supposed to slide, because if we just use the impact normal, this is facing the face of whatever we are grabbing onto, and it doesn't face where we are going. So the slip velocity would just squish us into the rock or whatever you're slipping down on. That's why we need to rotate that. Then we want to take the negative vector of that and multiply it by the slipping speed and subtract the hit impact normal. This is the main part that I just figure out through trying. I'm not exactly sure anymore because I did this like a year or so back, maybe a little bit more. And after this has been calculated, we can update the current slipping speed, which we want to lerp from the current slipping speed to the gravity z. And I multiplied the delta seconds by 2, so it lerps a little bit faster, but you can change this to whatever you like. And then we add the actor world offset, and also add the slip velocity to our climbing offset, so the next calculations will be accurate as well, and return it. And here we have the lerp climbing body z offset. We used this all the way in the beginning when we were creating our update collision function. This is when we are climbing, our collision capsule will contract into a ball, and we don't just want it to snap back to the actual height of the player, and we want it to slowly lerp back into its original shape. And also, of course, if we are lerping down into a ball, we also want that to be slow and smooth to avoid motion sickness. And the reason why we even contract into a ball is so you can easily climb up ledges and you won't hit your feet. Here we will get our climbing body z offset. We will get f math lerp, and we want to lerp from the climbing body z offset to the target offset. Here we will get the world, get delta seconds times climbing offset lerp speed. Then we'll get the capsule component, set the capsule half height, and here we will also lerp f math lerp. Here we will get the capsule component, get scaled capsule half height. We want to lerp to target half height, and again we will use the get world, get delta seconds times climbing offset lerp speed. There we go. Now we're almost done with the character class. You can see we already have quite a bit of code written. So all we need to do now is just to set the finger values. Here we get the right thumb axis value. This is equal to the value dot get a bool. There we go. Although this is a float, if the bool is false, this will be 0. If the bool is true, this will be 1.0. So this is fine. And then here we want to do the same for the left. Here in the index, we have our right index axis value. This is equal to value.get float. And here we want to check if the right weapon interface is valid. and if the bIsRight main hand is true, because if it is, then we want to move the trigger. So get the right weapon interface, pull trigger, and input the right index axis value. Then we can copy paste this for the left and rename everything that's right to left. There we go. And for the right grip axis value, this is just value.get load, and then the same for the left. There we go. Now all we need to do is to add one last C++ class, and then we can go into the editor and set everything up. So back in the editor, I'm in the public folder. I'll create a new C++ class, and this is going to be an Anim instance. And I'll call this the VR character Anim instance. There we go. And I will put it in the folder animations. We will use this animation instance class to create our animation blueprint for our VR character. And since there are some functions in the tick event, I wanted to use C++, so it's a little bit faster. Now let's add our includes. And then in the header files, let's add the class definitions, public variables and functions. I'll create my regions again. Here we have a U property, which is visible anywhere, blueprint read-only, and category variables general. This is our AVR character, which will be our character reference. Then we have a U animation asset, which will be the right hand anim asset. Then the same for the left. Then we have a bool b mirror right hand animation. Oh, and my bad, this should be the right hand trigger anim asset. Now we can copy all of those, and the same for the left. The following U property should be edit anywhere, and this is going to be an F vector, the right hand offset equal to a vector, and here I'll set it to -2, 0.0, and 9.0. This is the offset from our motion controller to our hand R bone. The hand R bone is at the wrist, so if we just move that bone to our motion controller location, then it would look off because the controller is in the middle of your palm and not at your wrist. That's why we add an offset so it feels more natural. Then we can just simply copy paste this, and this we can leave because that's a local offset, and we can change this to left hand offset. What mainly matters if you want to add a Y offset here, you have to make sure that, I believe for the right hand it would have to be positive and for the left negative. But I'm not using it here, so I'm not 100% sure. Then we have another edit anywhere property, which is a float, which is the camera offset. I'll give it a default value of -20. This is how far the head bone is away from the camera. And here we take the forward vector. That's why it's only a float, because we always want the head to be behind the camera, if possible. Here again, we have an edit anywhere property, and I will change to fingers collision. Here we have a float, finger collision check radius 2.0. This is how far the trace will go from your fingertips that we are using for the procedural animations. So for example, if your fingers are moving fast, you want this to have a bigger radius, because if it's too small, your fingers will stop too late and then are glitched inside of an object. Then next we have a bool. B is right thumb colliding. Then we have the same for the left. And now we do that for every single finger, because we want to move the fingers independently of each other. Here again, we want visible anywhere. We'll change the category to values. And then first we have a float finger value interbeat. I'll set this to 0.25. The higher you set this, the faster the finger will move. Then here we have the right thumb value. And again, here we need a value for every individual finger. So yeah, bear with me a second. Okay, that's all the variables. Now we can add the functions. So we have a U function, blueprint callable, and blueprint pure. The blueprint pure part is that little checkbox that we ticked so that the function collapsed in its own little box and that we didn't have to hook it up to an input and output execution pin. Here we return f transform, and this is the get camera transform function. Then we need the same for the left and right motion controller. Then we want to get the total body z offset, so float get total body z offset. Then a simple bool do collision check, and here we want to input a bone name, then check finger collisions, set finger values, check if finger can retract, and here we want to pass a bool v is colliding, a float, and this should be an address, the previous value, and another float, new value. Then we have another new function. This returns a vector. It's the get character velocity. Then another vector, get character pelvis offset. Then a float, get character pelvis rotation. We will use this when we go from crouched to prone. We want to slowly rotate the pelvis on the pitch so that it looks more natural. Then we want to get the character height ratio, and this is a regular U function, which is a bool. Get is climbing. Then we have another regular U function. This is our event on right hand anim changed, which takes an U animation asset, anim asset, another animation asset. This is the trigger anim asset, and a bool b should mirror animation. And then we also have the same for the left. And then here in the protected section, we have a virtual void, native initialize animation, override it, then virtual void, native begin play, make sure to override it, and virtual void, native update animation, which is the tick event. This takes a float delta seconds, also override it. There we go. Now we can go ahead and declare the functions. And actually I will move these up here all the way to the top. So the native initialize animation, we can leave that empty. In the native begin play, we first want to call the super native begin play. Then we want to try to get the pawn owner and cast it to our character. So a vr character, try get pawn owner. And if it is valid, we set our character reference to the character. And now we will set up the right hand and left hand anim changed events. There we go. Then in native update animation, we also call super native update animation, input the delta seconds. And here we want to check if the character reference is valid, and then check finger collisions and set finger values. Now in get camera transform, we first want to check if our character reference is valid. If it is, we create a transform, the camera transform, and here we will set the location, character reference, camera get component location, and then we add the offset, get the forward vector, so it adds it into the direction the camera is facing. Then we have the camera transform, set rotation, character reference, camera get component rotation. Never mind, get the component quad, and then the same for the scale. There we go. Then we can simply return camera transform. Now the RMC transform is a little bit tricky on the location part, so I will implement it first and then explain it. Okay, so first we get the location of our motion controller, and then we add the right hand offset times our forward vector. We don't simply just use the right hand offset because this is in world space, and we want it to be if our controller is rotated, for example 45 degrees to the right, or is even facing the y-axis, then we still want this offset from the x-axis to be applied to the local x-axis of the component. That's why we get the forward vector for the x-axis, right for the y, and up for the z. And in the end, we add our right recurl offset, so our hand moves back when we have recurl. And then rotation and scale is the same as usual. And as always, for the left, we can copy it and rename right to left. Now for the total body Z offset, as always, we check the character reference and return the character reference body Z offset plus character reference climbing body Z offset. Otherwise, we return 0. Here in do collision check, we create an F hit result, but only because we need to. Then in return, we get the uKismet system library, sphere trace signal, get world, character reference, get mesh, get socket location, bone name. This is the start, and we can actually duplicate this and use it as the end as well. And then we have the finger collision check radius, the E trace type query. We are going to use trace type query 1, which is visibility if I'm not wrong. The trace complex can be false. The actor to ignore would be this, although nope, that doesn't work because this is a animation instance, so this will just leave empty. Then we have our E draw debug trace. I'll set it to none. The hit, and we want to ignore self. That's already it for that. Then check finger collisions. Here we want to first check if the right hand anim asset is invalid, because only then we want the procedural animation to be used. So is right thumb colliding is equal to collision check on the thumb 03R. This means it will trace on the very tip of the thumb, or whichever finger you input. Assuming you are using the default Unreal Engine 5 mannequin, if you have a different skeleton, you will have to go and check which is the tip bone of the finger. And then we do the exact same for all of the other bool values. And then, of course, also for the left. There we go. Then in set finger value, we are going to check if finger can retract. B is right thumb colliding, right thumb value, character reference, right thumb axis value. Then the same for the left. And now for every other finger. I'll leave a space so it's a bit easier to see. And here for the middle ring and pinky finger, we will use the right grip axis value and the left grip axis value from the character reference. Okay, and that's that. Here in check if finger can retract, we first want to check if it is colliding. And if it is, we want to check if the new value is greater than the previous value. And if it is, we simply want to return. However, if it isn't, then the previous value is equal to fmath lerp previous value to new value. And here we have our finger value interp feed. Then in get character velocity, we check the character reference as usual and return character reference camera velocity. And otherwise, we'll simply return a 0 back. And for the character pelvis offset, this is a little bit more again. So see you in a second. Okay, so first we get the height ratio. Then we want to map range clamp our half height, the input being the height ratio, and our lower value being the prone ratio, and our max value being 1.0, meaning standing up. And we want to clamp from 10 to our scaled capsule half height. I chose 10 because if it's 0 and you're lying down, then your body will clip into the floor. So that's just the value that I've played around with, and that's what worked for the mannequin. And then we want to check if our half height is greater than our base height, because if it is, we want to set the half height to the half of our base height. This is, for example, if your room scale tracking is offset from the actual floor and you for some reason stand taller than you actually are, then it would lift the character from the floor and with this it will stay on the floor. Then we have the Y offset. We use a Y offset and not an X offset to move the character back when we crouch down, because we will be using this in a control rig, and the control rig has the Y axis as the forward axis. At least with the Unreal Engine mannequin. I believe it's because the mannequin is facing the Y direction. So if you have a custom mesh, make sure if it faces the X direction, you would want the Y offset to be the X offset and return it in the X and have Y as 0. But yeah, for the mannequin, it will be a Y offset. And our input is the height ratio, and we want to go from the prone ratio to 1.0. If we are laying down, we want to move the character back 1/3 of our base height, just the value that I played around with and which worked for me. And if we are standing up, we don't want it moved back at all. And for the Z offset, we get our half height. We add the half of our climbing body Z offset and scale it by the map range clamped value of our height ratio, range being prone ratio and standing up, and 0 and 1. And then we simply return these offsets in a vector. We're almost done. Now we just need to get the character pelvis rotation, check the character reference, and then we will return new Kismet math library, map range clamped, character reference. I'm going to copy that so I don't have to write it every time. Get height ratio, that's the input. Then we have our character reference, and we want to range from prone ratio to our crouch ratio, and the range should be 90 to 0.0. So if we're standing up, the pelvis isn't rotated at all. The pitch of the pelvis, I should say. And if we're laying down, we want the pelvis to rotate 90 degrees, so it's facing down to the earth. Then in here, we want to get the character height ratio. So simply return reference, get height ratio. And in get bIsClimbing, we want to return character reference bCanClimb. And if he can climb, we also want to know if he is climbing right or climbing left. Now, if the right hand animation has changed, we want to set it to our right hand anim asset. So set this to the anim asset. Same goes for the trigger asset and the B mirror right hand animation. We should mirror animation. And if the right hand anim asset is valid, it means we are holding a weapon where a animation exists. So we want to make sure that all of the collisions are set to false, because otherwise the finger values wouldn't update. So B is right thumb colliding, false, and then the rest for all the other fingers. Yeah, that's it with all of the C++ code. Let's compile and pray. Now we can go into the editor and start implementing all of this C++ stuff. Okay, now we can continue with creating our control rig, which will be controlling our body. Now, what I've done, I've gone ahead and added some meshes, sounds, textures, and visual effects. I won't show you how to create these. There are countless tutorials on YouTube already. These are just the assets that I'm going to be using. But in the meshes, I will show you how to set up the sockets and how you can figure out where your hand needs to be on the pistol, for example. But anyway, let's start by creating a new folder called Blueprint. And in here, I'll create a subfolder called Animation BPS. In here, I want to go to Animation, Control Rig, and create a new control rig. I'll call this CR Procedural Body. Now, at first, I wanted to do this in C++ as well. However, it's a bit more complex than just calling the individual functions as you can do in a Blueprint control rig. And the performance difference won't be that noticeable because this will only be used for the player. So if you had hundreds of enemies, for example, that use a control rig, then you would definitely want a C++ control rig. But for our purposes, this is sufficient. And also I didn't want to drag out this video much longer just to have this in C++ as well, because all of the functions that we are calling in here in the backends, they are C++. So the only thing that isn't C++ is the calling of the functions. So if we go to rig hierarchy on the left, we can import a hierarchy, and we want to import our SKM many. Click OK. And I will move the forward solve down a bit, and we want to get the construction event. Now, before we continue, to the left, we want to go to my blueprint And in here, we are going to set up some functions and also some variables. So first we need some variables. So let's add those. First, we have a float. This is our step size. With this, we want to define how big of a step our character takes. I want this variable to be public, so we can easily adjust it from the animation blueprint. And after compiling, I set a default value of 50. Next, we have again a float, which is the max step height. I'll give this a default value of 30. By the way, in here we will be handling the head IK, the arm IK, and also the procedural legs. The procedural legs, that is not my code. There is a link in the description to the tutorial that I used to create it. I did change it a little bit because in the tutorial it was used on an 8-legged character that's much bigger. But all in all, it's all of the procedural leg logic is from that tutorial. So yeah, make sure you check that out in the description. Then the max step height should also be a public variable. Next, we have our velocity. This should be a vector, and I also want it to be public. Next, we want a vector array. These are our world locked foot locations. And to make an array, you can select it, come over here to the right, and choose array. Then the next function is also a vector array. We will call this world target foot locations. Then we want an integer. At this, I will call it current foot count. This should be an integer and just a single. And next, we have our foot timings. This should be a float array because the timings of when we move our feet should be offset. Otherwise, our legs will move at the same time and it will just look like the character is hopping around. Then we have our pelvis offset. This should be a single vector and we want this to be public. Next, we have the pelvis rotation offset, which is a float, also public. Then we have our head target transform. This is of type transform. It's also public. Now I'm going to duplicate this 2 times and I will call this our right hand target transform and our left hand target transform. And these should also all be public. And at last, we have a bool that's called bIsClimbing. And this is also publicly visible because we will be passing all of these from the animation blueprint with our functions that we created. Okay, now we can start setting up the construction event. First, we want to get the children. And in here, we will be setting the initial values for our foot location, target location, and the foot timings. Again, this here doesn't come from me. This is from the tutorial linked in the description. Here we want to get the pelvis bone and loop through them. So for each, here from the element, we want to check if the name contains the string foot at a branch, because then it means that the current bone is a foot bone. And with this is infinitely scalable. So if your main character has 4 feet, or is like if you're playing as a spider, for example, then this will automatically adjust it. Because in the tutorial, the guy also applied this to a spider and not a humanoid. But anyways, then we want to get our world locked foot locations and add. We will implement the element to add shortly. Then we want to get the target foot locations array and also add an add node. Last, we have our foot timings and also add, because we need initial values in here. Otherwise, the following logic wouldn't work. And here from the index, we can cast this, and it automatically knows that we want to cast to float. And then we want to multiply this. Make sure you get multiply, and we will multiply by 0.5. This will automatically create an offset based on the foot index, or how many entries are already here. So the first index won't be offset at all. The second one will have an offset by 0.5 and so on. Great, but now for our initial foot locations. Collapse this and then get our item. Here I want to get transform from a bone. Space should be global space and initial is unticked. Then here from the translation, we want to add, and I'm going to add an offset of 100 on the z-axis, then duplicate this and add an offset of -100 to the z-axis. We will be using this for line traces, so the foot knows where it should be in the world. Then we want to get a sphere trace by channel. The first one is our start the minus 100 is our end. We will trace by visibility, and the radius of 5 is fine. Then we want to get a conditional if, and this we don't want it to be a bool, we want it to be a vector. If it's true, we want to get the hit location. However, if it's false, it means we haven't hit anything, and we simply want to return our bones location. Then we have to make sure that we cast this to world, and then we can input this into the array, or add it to the arrays, I should say. Compile, great, everything's successful. I forgot, very important, make sure you tick recursive, because otherwise it won't get the children of the children. Great, and now we can start adding our first function. And our first function, I'm going to call this pelvis IK. And in here we want to get our pelvis offset, make some space, and then set translation or transform, and then it will automatically realize that it should be translation. We want to add this to a bone, that is our pelvis, should be global space, not initial, the value is our pelvis offset, weight 1.0 and propagate to children. Then next we want to set the rotation, again set translation, and here we change this to a quad. Then we want to get the transform of our pelvis bone, then split this and then cast this to a rotator. And then we want to cast to a quad again after we've applied our rotation offset. And here the X, which is the roll, can be the same, so can be the yaw, because we only want to apply this to the pitch. And here we simply add our pelvis rotation offset. And then here, of course, we want to set the rotation to the pelvis. There we go. Now I'm not quite sure why it says item not valid. This shouldn't interfere with anything. Then we can add this node to our forward solve. So call pelvis IK. And the next function is our head IK. This is quite simple. We simply get the head target transform, and then we want to add a basic IK. For the bones, I choose the spine 01, spine 04, and the head. Then we want to get this from world and simply input it into the effector bone. Now for our primary axis, this we can leave this. However, our y-axis should be -1, because otherwise we will get weird twists in our body. Or actually, we can just set the secondary axis weight to 0. That's fine as well. Now for our pole vector, I want this to be 0 at z and -100 at the y-axis, so it's always behind the character. And then we also want to make sure that the pole vector kind is a location. This is just to make sure that when you crouch down that your back will move back and not forward and bend the wrong way. And yeah, that's already that. Now we can add it to our forward solve. Now you can just ignore this up here because it will look weird, because of obviously now it will try to move the head to our head target transform, which is currently 0. You can of course set the offset manually here if you want to debug it. So you can see it does work. The rotation, this is fine like this. We will be adjust the rotation offset in the anim graph of the animation blueprint. But yeah, for now it will just look like an ostrich. Then our next function is our arm IK. Here it's basically the same as we did with our head. We get a basic fabric, and then here for the items, we add 3 items. First one being the clavicle R, the upper arm R, the lower arm R, and I meant to add 4 items, and at last our hand R. There we go. Our effector transform is our right hand target transform. Here we also have to make sure to get it from world, and then we can input this. And then we can copy paste this and change everything to left. There we go. Now I'm not quite sure why the hands are still in the air. They should actually be where the head is. Ah, yes, now I see it, sorry. In the basic fabric, we also need to make sure that the type of the item is a bone. There we go. Now the right hand snapped where it should be. It's my fault. I don't even know why we can select the bones if this is none, but whatever. Now you can see our hands are also going to the location 0, 0. Next will be a bigger function. Here we will be calculating the new foot targets. So let's call this calculate new foot targets. And here we will need a lot of space, and I will actually disconnect that. Okay, so first thing we will do is create a local variable called current foot index. This is of type integer, and we will set it to -1. Then we want to get the children from a bone that is our pelvis, and we want to loop through them. So get a for each loop, then make sure that recursive is ticked. First we want to check again if it is a foot, so contains the word foot, then we add a branch, and actually we can get our return node and move it here to the completed output. Now then we also want to get the transformer of our item. Now, if this is true, we want to set the current foot index, and we want to increment it. So we want to get our local variable, get current foot index, and add 1 to it, and set it as its new value. Then we want to get another branch, and here we want to check our foot timings. So get foot timings, and then we want to get the item at a specific index. This would be our current foot index. And we want to check if this is greater or equal than 1.0. Because only if the foot timing has gone past 1, then we want to reset it. Now, if this is true, we want to get our world locked foot locations and set the item at. Index, again, is our get current foot index. And from our get world target, from our world target foot locations, we also want to get the item at this index, and we want to set the locked foot location to the target location. Then in our foot timings array, we want to set the item at our current foot index. Now we need to reset it because after it's reached 1, it should go back to 0. For the element, we want to get an if condition, and here we want to get the current foot index from our foot timings. We want to get the item at this index, and we want to get the index before, so subtract 1, and we want to check if these two elements are nearly equal. So is nearly equal to this one, and we want to have a tolerance of 0.2. And if this condition is true, we want the value to be 0.5 and otherwise just 0. Because if these are almost 0, it means that the feet are syncing up, and then we would be hopping around. And with this, we can add an offset to the foot timings, and this way the feet will keep themselves from syncing up and moving together. Then after that, we can get our world target foot location, set the item at current foot index, and for our value here, now we want to get the transform of our item. Now the sphere trace that we are going to do here is dependent on if we are climbing or not. So we're first going to get isClimbing at a conditional if, and we want this to be a vector. Now, if we are climbing, we want the trace to start from behind the player and otherwise from above. First, we add this to the bone, and for the other, we simply want to subtract. You can also get another add node and just call negate here. Then you will simply turn -100 to 100 and 150 to -100, but I'll just simply use a subtract node. Then we can do our sphere trace. So sphere trace by channel again. Channel should be visibility. Radius is also fine. Then we add another conditional if. If this is true, then we want it to be our hit location. If it's false, we simply return the bone location. Make sure you got it to world. Then we want to clamp our velocity size to our maximum step size. So get the velocity, then call clamp length, and the minimum length is 0. The maximum would be our step size. Then we add this to this value. So add. There we go. And then we can set this as the new target. There we go. Now in here, let's call calculate new foot targets. Now for now, it doesn't do anything because we don't tell our feet where they have to go. And before we do that, we want to add another function. This we will call increase foot timings. First, we want to get our foot timings and get a for each loop. And if it's completed, we return. For the loop, we want to set the item at. The index is just the index. And here we want to add some time offset. So we want to base this offset on our velocity, because if we move faster, we also want the legs to move faster. So we will first get our velocity and get the length of the vector, and we want to divide it by our step size. Then we want to check if this equals 0, because if it does, it means that we are standing still. Add a conditional if it's false. If it isn't 0, then we can simply use our value here. However, if it's true, I will set a default value of 1.0. So the legs will update every second when we're standing still. Then we want to multiply this by our delta time. So get delta time, then multiply this value. There we go. And that be this function. Now we can add it here. These foot timings, and at last our foot IK. So in here, first thing we want to do is set the current foot count to -1. Then get the children from the pelvis. Make sure it is recursive as well, and then loop through them as we did before. Check if the name contains foot. Make this to a branch. And now if it's true, we want to set the current foot count, and we want to increment it. Get current +1. So after we've increased this, we can add a sequence. And here, this is a bit different from the tutorial that I've linked in the description, because now we want to check if our bone contains R at the end, because then it means that we have the right foot. Add another branch. And if it's false, then it means we have the left foot. And we need to do this independently, because due to the primary and secondary axis of our knee, if we try to apply the same axis to our left knee than our right, then one will be just weird and twisted. You will see what I mean. So for true, we will add a basic IK. By the way, I added a basic fabric for our arms, because at first I wanted to use the pole vector on the arms on a basic IK for our elbows, so we can control them a little bit better, but I had some issues where that didn't really want to work. That's why I used a fabric there, and I will fix this in the project on Fab later. So yeah, for now we're using a fabric for the arms. Now here we don't want to set these items manually. We can simply get the element, because when we're there, it should be our foot. Then we can get the parent, and I will add a comment because this should be the calf. Then we can get the parent of the parent. This should be our thigh. So, and the thigh should be our first bone, calf our second, or the item B, and the third, or item C, would be our foot. Then here we want to split this effector, and also here we want to make sure that Y is -1, and we want to get the transform our bone, set the rotation and the scale. However, the translation is going to be a bit more complex, so I will first duplicate this, connect it to the false output. Now the items are all the same. Also make sure to connect the rotation and the scale. And here is the difference between the two, because now we have the x-axis that needs to be -1 and the y-axis on the secondary axis that is 1. This is why we need to split it up like that. Otherwise, one leg is just all crooked and weird. Actually, I think I can show you this. We can connect completed, and if we now call the foot IK, yeah, you can see the left leg is all weird. So if we come back here and this up to that, now they are correct. Again, they look weird because the feet are going to 0, 0, and it's trying to adjust the knees. Actually, that reminds me, we also want to set the pole vectors to something like Y500, so it's in front of the player. However, you can adjust it as you like. You can see now the knees are bending forward, the correct direction. Again, it looks weird because our character doesn't have the correct values right now, but it will as soon as we are in VR or in the editor as well, and after we've connected everything through the animation blueprint. All right, now for our location. We first get the foot timings, and we want to get the item at our current foot count, and we want to remap this. So remap. We want to remap it from 0 to 0.5, and the target output, the target minimum and maximum should be 0 and 1. And we also want to make sure to clamp this. Then for our step height, we want to evaluate a curve, And here I'm going to add a new key in the middle, 0.5. This should be 1, value 1, and last value should be 0. Then I will select these three, right-click one of them, and select Auto. So you get a smooth curve. This will determine, based on our foot timings, the height of our foot. So when it's in the middle, we want the foot to be up, and if it's in the front or in the back, it should be at 0 or on the floor. So the source minimum and maximum is 0 and 1. The target minimum is 0, and for the target maximum, we also want this to scale with our velocity. So get velocity, get its length, then remap this from 0 to, I'll give it a maximum of 400. With the source maximum, you can tell it when your feet should be at the maximum. You can set this to something like 100, then the feet always reach maximum height, even when you're crouching, for example. I set it to 400 because it works for me. Target maximum should be the max step height. And we also want to clamp this. And this is our target maximum. That's for the height. For our location, we want to get the world locked foot locations, get the target at our current foot count from world, and we want to interpolate this to our target foot location. So here we want to get the world target foot locations. Now for the T of our interpolation, we will use the remapped value of our foot timings. And then we can get add vector node, and here we can add the Z value, our step height, and I will add another Z offset of 8 because our foot bone that we apply the offsets to is in the ankle. So if you move that to the floor, then the foot itself is in the floor. So if we add an offset of 8, then this will be correct. And now we can hook this up to the translation. There we go. Now you can see the foot is nice and even on the floor. That should be it. Sorry for the mess with all of the lines. Yeah, that's already our control rig done. All right, so next we want to add our animation blueprint. So in our animation BP folder, I will add new animation blueprint. And here we want to go to the parent class Anim instance, and we are going to search for our VR character animation instance. And also make sure to select the SK mannequin and then create it. I will call this ABP VR character. Now, before we add anything to our anim graph, I want to add a new animation layer, and I will call this fingers. Here we will set the position of our fingers based on the procedural animation or the animation that we pass with a weapon. Also make sure to select the animation layer and then add an input. All we need is our input pose, and now we can continue on from here. So first we want to set our finger position based on the finger values. Now, before we can continue, we will need an animation for our fingers to play. So what I will do, I will go into the control rig folder, characters, mannequins, rigs, and drag out the CR mannequin body. Then the sequencer should open up. And now what we can do, we can simply make a fist for the right hand. We will only create the animation for the right hand and then mirror it to the left. So I'll create this animation real quick and then I'll be right back. Make it easier, you can also tick this, then it will create a key every time a property changes. I forgot to do it, but I will be using it for the next animation. So now here we have our pose, and now we can right click the CR mannequin body, the sequencer, make animation sequence, and in content I will create a new folder called animations, and I will call it a fist right. Okay, export to animation sequence. Then we can close the sequencer. And here you can see we have our animation. The rest of the body doesn't matter because we will only be blending the finger poses, nothing else. And one more thing that we need, I'll add this to the animation blueprint, is under animation, we have a mirror data table. We'll use it on the SK mannequin, and I'll call it MDT Mani. With this mirror table, we can easily mirror animations. And for the default Unreal Engine 5 mannequin, this works automatic. So you can see hand L is for the mirrored name hand R. The thumb 03L is thumb 03R. And again, for the mannequin, it does this automatically. If you have your own mesh, it should still work automatically if you have named it like that. If it didn't, you can simply select an entry and then enter your own name for the mirrored name. But other than that, we don't have to do much more. Now we can go into our animation blueprint and create our fingers animation layer. So I want to get a fist right and then get a layer blend per bone node. And here in the layer setup index, we want to add a new element. For the bone name, we are going to use the thumb O1R. Blend depth can stay at 0. And then we connect this. And our blend weight is our right thumb value. Now we can duplicate this. And for the left thumb, we can simply add our mirror table. So we can call mirror. And you can already see, since we only have one mirror data table, it already suggests our MDT many. So we can add this, make sure mirror is selected, and now our right animation will get mirrored to the left. I will hook it up real quick just to make sure everything works. So the fingers, and now what we can do here, we can set the default value. Oh no, we can't because we didn't set it to edit anywhere. Okay, let me just do it like this. If we now mirror it, and I just realized I can't show you because here this needs to be thumb O1L now. Now if you recompile, you can see the thumb animation plays. But our right thumb value currently is 0, so they are like that. Now next we have the next fingers, so we just copy paste this, and here we have our index, and now we just do that for all of the fingers. Great. Now in the end we want to save this as a new cached pose, and I will call this default finger pose. Next we want to get our right hand anim asset, and we want to cast it animation sequence, anim sequence. Then we want to create a sequence layer, and in here under sequence we select this bind drop down and select expose as pin, and now we can input our animation that we've passed from the weapon. And I will save this as a new cached pose, and I will call it right hand weapon pose. We store it into a pose so we can use this multiple times, because you can't connect this to two different outputs. So that's why we store these things. So first, let's get use the default finger pose. And here we want to do a layered blend per bone. And we want this to be on every finger. So add 5 entries, and then add all of the first finger bones that we've added up here. We use this because in our input pose node, we have every bone. So for example, we also have our current leg position that we will set previously in our control rig, and we want to keep that the way it is. That's why here we input this default pose and potentially the finger that we've adjusted, and then we only want to apply our changes to our fingers, since the rotation and position of the hand on a weapon is defined by the animation and the sockets on the weapon. And actually I will create some space here, and now I'll add the bones. Make sure to add the O1 bones, and here these are only the right ones because currently we are in the right hand, and the blend depth is everywhere 0. Great. Now here we can add a mirror from MDT many, and for the bool we will use our mirror right hand animation bool, and here we want to blend poses by bool. Our condition is if our animation asset is valid, or better yet, if the cast is successful. I almost made the mistake and used the right hand anim asset. We already used that for our right hand weapon pose. We want to use the right hand trigger anim asset, because here we will be holding the weapon. If this is invalid, for example, if we hold something like an axe, then we don't want to play any trigger animation since it doesn't have any. And again, if this is invalid, we want to get our right hand weapon pose. We want to use that. And otherwise, if it is valid, we want to get a sequence player and input this animation. However, that's not all. We then want to blend it, and we want to blend from our right hand weapon pose, which is the release position of the trigger, to our hand trigger pulled animation asset, and for the alpha we will use the right index value. There we go. So if this asset is valid, we will, depending on how much we press the trigger, slowly move our trigger finger to the pulled position. And now here we add another blend per bool node, because we want to check if the right hand anim asset is true. Here we simply cast, because you can't input it directly. Otherwise I would input it directly and do the cast later. But now we want to check if this is valid. If it is, we can use its animation. Otherwise, we simply want to get the default finger pose, because then it means that our finger will be moving procedurally. And then we can save that in a new cached pose. I will call it right hand pose. There we go. Now we can pretty much duplicate all of this for the left hand. However, what I will change, first of all, this is supposed to be saved as the left hand weapon pose. Here, of course, we want our left hand anim asset. Here, the left hand trigger anim asset. And instead of the default finger pose, we now want to use our right hand pose, because it includes our updates that we did to the right hand. And here, of course, we want this to be our left hand weapon pose. Same down here. Here, make sure you're using the left index value. Here we want to mirror the left hand animation. Again, left hand anim asset. Default, we will use the right hand pose. And here we can simply output this pose. And actually I will change the transition to 0.2 seconds, the blend time I mean, just so it's a little bit smoother. And something very important, I nearly messed it up. Here we have our right thumb, this is our left thumb, so we also need our left thumb value. And of course, for the index, we want the index values. So give me a quick second while I fix this. There we go. And that's it for our fingers animation layer. Now in the anim graph, we can leave the fingers as is. And I'm going to get a control rig, and here under control rig class I will choose our CR procedural body file, and we can tick all of these boxes. Now the step size I will leave as it is, also the max step height. However, for the velocity we want to get character velocity, then we want to get the character pelvis offset, get the character pelvis rotation, then our get camera transform, get RMC transform, the LMC, and at last our bIsClimbing. Get is I just realized that in our VR character anim instance header file, I forgot to add the blueprint callable and blueprint pure function definitions to our U function of getIsClimbing. So make sure you add that if you haven't already. Now let's compile this. And now we should be able to get isClimbing. There we go. Now we can do local to component, because now we want to add some transforms. Transform modify bone. This here we want to add an offset to our head bone, and we will only be applying a rotation, so can set this to add to existing, and we want it to be in bone space. Now the rotation that we need here is 90 and -90. Plus 90 on the y-axis, -90 on the z-axis. Now we can copy and paste this 2 times. And here we have our hand R, and the rotation for our right hand should be 70 on the y-axis and 180 on the z-axis. For our left hand, it is 180 degrees on the x-axis, -70 on the y-axis, and 0 on the z-axis. There we go. And now we can connect this to our fingers. There we go. Now you can see this also collapsed down, because all of our inputs here are still 0. They will have different values as soon as we start the editor. But that would be the animation blueprint for our character. Now before we create our VR character blueprint, we want to set up the widgets, and we want to start with the audio widget. However, for that we want to create some sound classes. So down here I already have the folder sounds with my sounds in it. Create a sounds folder, and then in here we want to go to sounds, classes, create a new sound class. And I will call this main sound class. Then under the same tab we want to create a sound class mix, and I will call this main sound submix. Before we continue, we want to go to the project settings, search for sound, and here you can see we have our default sound class, default media sound class, and default base sound mix. So here I will select our main sound class for these two, because the master is from the engine, and if you want to change things, I would suggest you add your own class. And for the base sound mix, we want our main sound submix. That's that. Make sure everything's saved. And then what we can also do In here, I will just search for all files. You can do that by adding a space. And then I want to select all our sound cues and sound wave files. Right click, asset action, and bulk edit via property matrix. And then we want to set for all of these the class to our main sound class. And that's all we need to do in here. We only need to set the class. So now we can save these assets. Great. Now that that's done, in our blueprints folder, I will create a new subfolder called widgets. And in here, we will start by creating our audio class. So create a new blueprint class, all classes, and search for audio settings widget, the one that we created earlier in blueprint. And I will call it WBP audio settings widget. Let's open it. Here we don't have much. We simply add a canvas panel. Then I'll use a grid panel, and I want its anchor to stretch to every side. And for the column fill, I want one column. And next we'll add a horizontal box. This horizontal box we want to center line vertically. And in it we have our master volume text. So search for text. And we don't want a text box. We simply want a text. Add this, and then here I will call this master volume. And the next is a slider, which is the slider component that we defined. And actually for the text, I'll set it from auto to fill and set it to 0.15. That's what works for me. And we want it to be horizontally aligned to the left and vertically to the center. Then our slider, because right now when we try to compile, you see we get an error. No master volume slider defined. This is because of the bind widget meta that we set in our C++ class. So we need to call this master volume slider. Now we can compile it. It recognizes this component, and we can also set it to fill 0.85. So in total we have 100%, and the alignment we can leave as it is. I also want to change the step size to 0.05, and then down here under style, first we have the bar thickness. I'll set this to 10, so it's a bit better visible. However, now our slider here is rather small. So we go to our normal thumb image, and I will set its size to something like 20 and 40. Now it's nice and big. And then we do the same for when we are hovered over it, also 20 and height of 40. There we go. And this would already be our audio settings menu. Like I said, I will keep it simple and only apply this to the master volume. Now, one more important step, if you go to our graph, here we have our sound mix modifier. So we'll select our main sound submix. And for the sound class, we want our main sound class that we created. Again, if you had multiple sliders, then you would also want to add multiple inputs in your header file. Yeah, that should be it for the audio settings widget. Next, I'm going to add the general settings. So another blueprint class, search for general settings widget, the one that we created, WBP general settings widget. Here we want to start by adding another canvas panel, and we'll add another grid panel and make sure the anchors are set to stretch. And again, we want one column fill with the value of 1. Then at first we have a horizontal box. I'll rename this to turn style HB, so we know it contains our turnstile stuff. This we also want to be center aligned vertically. Then first we add our text. This is our turnstile text, so turn style. Then we'll add another horizontal box. Oh, and also the text should be 0.4, and the horizontal box should have a fill of 0.2 and should center align. There we go. Real quick, after this horizontal box, we want to add a spacer. And the spacer has a fill of 0.5. This is just so that our horizontal box and our actual settings aren't that far away from the text, but it's purely cosmetic. So now in this horizontal box, we have our first button. This is our previous turn style button. If I compile, it's one of the buttons that we need. Then next I'll add a text. This is our turn style text. And then I'll simply duplicate this button and move it below the text. This is our next turnstile button. But again, you see a lot of error messages just disappeared. I will also add a text to our button, so we can add these little brackets, and also so we know what it's supposed to do. Change the color and opacity to black, so it's a little bit more visible. Then under our turnstile horizontal box, I want to add another spacer. Want it to be in row 1, and we want its size to be 30 on the y-axis. Then we will duplicate the turnstile horizontal box, copy this and add it to the grid panel, and I will call this the movement direction HB, and this should be on row 2, the whole horizontal box. Then I will rename this to movement direction. Our previous turnstile button is now the previous movement direction button, and the same for the text and the other button. And now for this text, we don't have to set anything. I will, however, set a default value of snap for the turnstile and controller for the movement direction. But this is just a default value. It will get updated as soon as we start our game. Now, one more thing that I almost forgot. We want the button to be fill with 0.2. We want this for both buttons. But of course, you can design this however you like. There is no rule. And this I will set to 0.8 and should be aligned in the middle. There we go. 8 and in the middle. There we go. Now it's all nice and aligned. So here you just have to add all of the elements that we've added with the bind widget settings in our header file, and then you can design it whichever way you like. Great. Then next we have our graphics settings. Start with a canvas panel and then add a grid panel. And now for our column fill, we want 5 elements. And for our row fill, we want 9 elements. For the first index, I'll set 1.2 and the rest should all be 1. And the same for the ones down here. This is just to align things. Again, you can do it whichever way you like. And here also we set only the overall settings, not every single one for like the texture and the shadows and whatnot, because just it would have unnecessarily stretched the tutorial out. So now first we add a text. This is just our quality text. Quality. We want this text to be center aligned. Then next we want a button. This we want to add to column 1. That'll add 3 more buttons. So duplicate this. This is for column 2, 3, and 4. Go. Now this is our all low button, all medium button, all high button, and all epic button. I'll say so. You see we have all the elements now. Now I will quickly add a text to those. And I'll set the padding on our buttons to something like 5.1. Because we have a little bit of an offset. And after our grid panel, I'm going to add a spacer. Sorry, not after the grid panel, but to the grid panel. And it is in row 1 and has a column span of 5 and a row span of 8. There we go. Now it's not that stretched and our things are neatly aligned at the top. There we go. That's our graphics settings. Next, we have our settings menu. Again, a canvas panel, but this time we don't need a grid. This time we can add a button. This will be our back button. I'll also add a text to it. I'll set the button size, first the position to 50 and 50, and the size to 250 and 75. There we go. Now it's neatly packed into the top left corner. Of course, you can put it wherever you like. Then I'll add a vertical box to the canvas panel. I first set this to stretch, and on the offset, the top left, the left offset should be 50, the top offset 250, the right offset 50, and the bottom one 50 as well. Now we have it neatly packed to the bottom here. And to that, vertical box, we will add a horizontal box, and I will set it to fill 0.15. Before I continue in this horizontal box, I want to add a widget switcher to the vertical box, and this is also set to fill but 0.85. All right, back to our horizontal box. Here I will be adding 3 buttons. Let's select them all and set them to fill 0.3. And at the end, I will add a spacer. I'll set this fill to, I'll leave it at 1. And for our buttons, I'll just add a padding of 5.0 and 0.0. There we go. Now there is some space between them. Now a text to the buttons. First one will be our general. Second one, our graphics. And third one, our audio. Therefore, the first button, we will call it the general button, then the graphics button, and the audio button. Now, if we compile, we have a few errors less. That's great. And then down here in our widget switcher, make sure it's called widget switcher, because that's what you call it in our header class, or whatever you called it. You will see it down here in the error list. So down here, we will add our 3 widgets. So first, our general widget. This is why we don't need to check if those are valid or not, because they will always have to be valid. Otherwise, this whole widget won't compile successfully. So then graphics. And at last, we have our audio settings widget. And also make sure that it's named correctly. Remove the WBP and you should be fine. And now when we compile, no more errors. Yeah, and that's already it with our settings menu. Now the last menu that we need to add is our hand menu. I'll just call this hand menu. And in here, again, canvas. To the canvas, we'll add a widget switcher. And I will call it widget switcher. Set it to stretch into every corner. And then for the first widget, here it is important that the order is correct. We'll add a canvas panel. And now this is our first widget in our widget switcher. The second widget will be our settings menu widget. WBP settings menu widget, add this to the widget switcher, and then you will be able to switch between these two. And in the first one, we have 3 buttons. Our first one is the auto height button, and it has a, and here the anchor, I'll set it to the middle. It has a X position of 0, a Y position of -300, an X size of 400, and a Y size of 100. And we also do this with the rest of the buttons. This one can stay at 0, 0. Oh, and I also forgot set the alignments to 0.5 each, because then the position that you add is from the middle outward and not from the actual origin. And we want this button is called the settings button, and the size should be the same, so also 400 by 100. Position is at 0. The last button, our quit button, X position 0, Y is plus 100, plus 300, and the size is the same as for the other two. And also, of course, 0.5, 0.5, and anchor is supposed to be in the middle. Of course, now I have to set this again. There we go. And at last, we can simply add some text to the buttons. There we go. Oh, of course, and rename the settings menu widget to the proper name. And here you can see we can now switch between the 2 menus, our main menu, so to speak, and then our settings menu. Now, before we create our animation blueprint, I quickly want to edit the physics asset for our mesh. So go to Control Rig, Characters, Mannequins, Rigs, and here we have the physics asset for the mannequin. I will duplicate this and then call this PAVR character. Let's open it. Here we have all of our bodies. However, we don't need all of them. I will leave the clavicles. However, I will remove the neck 1 and 2. Then I'll keep spine 3 and 5 and delete these 2. Yeah, that should be about it. Now for the collisions, we only really want collisions on our arms. So first I'll select all of them and I will make sure that nothing collides with each other, and also disable the collision response. Now for our hands, I do want to enable collision. You can also enable it on the lower arms. I won't, just because it's a little bit more stable and sometimes they can be in the way. For example, if you're holding a weapon, only the collision between the hand and the weapon is disabled. It can still collide with other bones if they have this collision response enabled. So, and especially while aiming, this can get in the way. That's why I disable it for those. And now I want to select the bodies which can collide with each other. And if you want to set up bodies that can collide with each other, for example, the hand and the leg, you can select the two bodies and select Enable Collision. And now you can see if I select the hand, this is blue. And if I select this, the hand is blue. So you can select two bodies, enable or disable the collision. But yeah, I will set it as disabled for this. Now, another thing that I want to do, I want to select all of these constraints from the arms, and I want to make sure that they are free on every angular limit. Just because with physics, this can get in the way. For example, you want to stretch your arm and it won't properly stretch, or you try to move your arm in a way where it does work with your real arm, but then here the constraint is in the way, so we just simply want it to be able to rotate in every direction. Then we can save this and close it. And one more thing that I want to do for the mesh of our mannequin, I want to add the sockets for our ammo that we grab, and I will add them to the thumb 3. So here I will add a socket. First I rename the socket. I will call it ammo bone L. Right click, add preview mesh, and I will choose our shotgun ammo. So we can see where it is. You can now set it by hand if you'd like to somewhere where it suits you. I have already done that, and I will simply copy paste the values. So you can follow along if you want to, or just do it yourself. There we go. This is pretty much how I want it to be aligned. And then we do the same for the right thumb. There we go. Then we can save it and close it. Actually, there is one more thing I want to do. In our C++ class, let's go to our Advanced VR Character Tutorial Game Mode Base. Right click it and create Blueprint class. I'll add it to the blueprints, and I will call this BP at VR Car Game Mode. And in here, we will afterwards set our character. So now, finally, after all that, we can create our VR character blueprint class. Let's search for our VR character. I will call it BP VR character. Let's open it. Then in here, first thing that we are going to do is set the mesh of our character. So this is our SKM many. Hey, it's editing me again. One thing that we forgot to do after creating the physics asset, we have duplicated it and we have created it, but we have not assigned it. So what we need to do is go to our VR character, select the mesh, and then search for physics asset and physics asset override. And in here we can set our PA VR character. Then here we want to use an animation blueprint. Here we have our ABP VR character. This might look weird, but I can assure you this is how it's supposed to look like when you're not currently in the editor. Then for our hand menu, here we can set our class, so WBP hand menu. And here it might look weird, but again, these are offsets that I found that work for me. Of course, you can adjust them if you want to, but in the editor, everything looks a little bit weird. Next, we have our laser pointer spline mesh. Here I have the shape cube. And now, of course, this is way too large, so I will set its scale to 0.01. See, now it's just this little bit. Then I also want to make sure that our collision preset is set correctly. So we want, this should say custom. We want the collision to be enabled, query and physics. The type should be physics body. We want to ignore visibility, pawn and vehicle, and the rest we want to block. Actually, menu, we can also ignore that. No, we do ignore it by default, but I guess because we added this later, that maybe that's why it set it to block for whatever reason. And in our class defaults, I will search for variables. And here now we have a whole lot. First, we have our input. The IMC is our IMC default. And then here we will set all of our input actions. So bear with me. Now the rest I will leave as it is. We don't really need to change anything there. Our event graph should remain empty. You can delete those. Now we can go back to our game mode, and here we can set our default pawn class to our BPVR character. And in our settings, we can come to maps and modes. Here we have our default game mode, BP at VR car game mode, with our BPVR character as the default pawn class. Meaning if we press play now, we should spawn at the player spawn, and you can see it looks weird because right now I don't have a VR headset hooked up. However, we can grab the camera, pull it up a bit. Actually, I will turn off snapping, and you can see the character moves with it. Now, currently we are moving very slow. That's why the legs don't adjust that fast. That is still something that I have to play around with to fix that. However, you can see if we grab our character and move it around, our feet will move with it. They are still a bit snappy. This is still definitely experimental. This is also why the Fab project is cheaper currently, because it is still in development and also in early access. But for now, this should suffice. And also when you're climbing on a wall, the feet will move up. However, they will move up and snap to the wall, but half of them will be stuck inside of the wall for now. And then we can also get our motion controller, move our hands around, rotate them. This all works fine. And I will go back into our animation BPS folder and create a new animation blueprint for the SKM mannequin. This time it's just the default class, and I will call it ABP animation debugger. All we need here is a sequence player and a mirror by MDT many. There we go. And now here we can set our animation. I will just choose a default one so it isn't complaining. And with this, we can then mirror our animations. And then to use this, all I will do is go into controller folder, get the SKM mannequin mesh, place it, and then here you have the animation mode, use animation blueprint, and we will input the animation debugger. And now you can see it has left fist. However, if I don't mirror it, so it's the right fist, and I compile and save, it doesn't change. All you have to do is just change some property. I usually enable and disable this disable post-process blueprint, and you can see it updated. That's how you can easily update it. Great. So now, before we can actually set this for our weapon, we need to create a one. Now, before we can debug the hand rotation for our weapon, we obviously need to create one and also an animation. I will do this for the pistol because in our meshes, I removed all of the sockets from everything here. And this way I can show you how on one, and it's exactly the same for all of the other weapons. So just as a quick example here for the pump action shotgun, here we have our different sockets. We have our handle bones, left and right. We have the magazine bone, we have the muzzle bone. And these bones here, they are usually only in magazines because they contain ammo. But since our pump action shotgun can hold ammo, they are also on this mesh. But we'll get to that in a second. So first, on the blueprint, let's create a new folder called weapons. And in here, I will create a subfolder called magazines, another subfolder called ammo, and another one called projectile. Now let's start in projectiles. So here we have our blueprint class. This will be of Projectile Base. I will call this BP pistol projectile. In here for the mesh, I will set my pistol projectile mesh or whatever. Pistol bullet. That's what I called it. And if we here search for our variables category, you can set things like damage, well, the projectile speed, the lifetime, decal fade screen. I'll leave this as it is. However, in here, I want my ricochet sound. Again, I won't show you how to import the sounds and create the particles and decals. You'll find plenty of tutorials for that. Here you can add those. The impact sound is what it sounds like when the bullet impacts somewhere, obviously. So for anything that's a projectile, I want it to be a ricochet sound. Projectile is explosive. You might want an explosion sound, whichever you like. Then for the impact particles, I have the bullet impact Niagara system, and for the decal, the bullet hole decal instance. Make sure that your material is an instance, otherwise you won't be able to add it. That's already it for the projectile. And we can go one folder up, and here we will be creating the pistol ammo. So search for ammo base, BP pistol ammo. And it is the exact same procedure for every other weapon that you add. Except, of course, melee weapons, there you only add the weapon class, but we'll get to that. So in here, first we want to set the ammo mesh. Here we have our pistol ammo, and for the fired ammo mesh, I only want the pistol shell. There we go. The shell is hidden by default, so you won't be able to see it, but you can still scroll down, and then you have the visible tag. You can also set this to invisible so you can see it. For the shotgun, this would just be the fired shotgun mesh, and the regular ammo mesh would be just the regular shotgun ammo that hasn't been fired yet. We go to our variables. Here we don't have much. All we really need to set here is the despawn delay, how long it takes, and the projectile class, which is our BP pistol projectile. Was fired, you never actually need to tick that, because if you tick it, then the loaded ammo can't be fired anymore. So actually, I must have forgotten, but this shouldn't even be editable anywhere. So you can, in the blueprint, in the header file, you can set this. In the C++ header file, you can set this to visible anywhere and not edit anywhere. That's my fault. Then we can close this class, and we go one folder up to the magazines. And here we have a magazine base. This is our BP pistol magazine. The mesh is our pistol magazine mesh. Then for the carry, again, pistol carry. You can leave it where it is. It will be set automatically as soon as we start the game. Next, we can select the ammo container. And here we have our ammo container, ammo class. So we want our BP pistol ammo. And you can also set how much ammo you want in here. I want a default of 8 rounds in this magazine. And now I will show you how you can add the bones to this magazine mesh. Let's open up the pistol magazine. And for now, I will simply add the ammo and carry bones, not the handle bones. We'll get to those. So here we have our ammo bone 0. And these are by index, so 0 is the first ammo, or I should say the last one that's left. And if you come to the right under advanced, you can set a static mesh. I will search for pistol ammo, so you can see exactly where you place it. I want my last ammo to be somewhere around here. Then we can duplicate it and set the next ammo's location. This is purely for the visual ammo indication. This does not define how much ammo is in your round. You can have 1,000 round magazine at this size, and only the last 8 rounds will be loaded. Something that is a little bit annoying, it doesn't realize that I want from 0, now I want 1. So you'll have to manually rename this, and I want to duplicate it again. So yeah, this is how you can set the ammo. I'll only add 3 for now, because you get the concept. You can add as much ammo as you want. And then for the carry, we have our carry bone. And here the first index is -1, because we want to set it to our ammo count -1. So if our ammo count is 0, then the index would be -1. So here the preview mesh should be the pistol carry. Now we can move it all the way up. I want it to be somewhere around here. That is good enough. Next we can duplicate it again and align it with the ammo. Then it would be the carry bone 0. Duplicate it again, carry bone 1, and so on and so forth. Now for magazines that have 2 ammos besides each other, I usually skip one carry position. So for example, you have 1, and then you have carry bone 3, 5, 7, and so on. And yeah, that's how you can set these things. And once they are set, here just to test it, I will get the magazine. And now I will simply simulate it. You can see our ammo is loaded, and our carry, for whatever reason, is in the wrong position. Oh, right, of course, because we only have until carry bone 1, but we have until bone 2. So just let me quickly fix this. Okay, again, here this would be ammo bone 2. And now if I press play again, you can see the carry is in the right position, and so is the ammo. And now if you were to fire a round, this would move up. And just to show you, in our stored ammo, if I set the ammo count, in our ammo container, if I set the max ammo count to, let's say, 100, and I press play, you can see it only fills up those 3 rounds for which these sockets were defined. So you don't have to worry about putting actual 100 rounds into a magazine. Now we can go one folder up again and come to our weapons. So right click. For our pistol, we want a projectile weapon base, BP pistol. Of course, if you want to add an axe or a baseball bat, you would simply add a weapon base Here we first have our weapon mesh, which is the pistol body. Then we don't have a selector mesh, but we do have a trigger. And this is important when you export your mesh. The body needs to be itself, of course, the trigger needs to be itself, and here we can move it to wherever we like. I want it to be around here. And for the rotation, I want it to rotate, let's say 25. We can search for max trigger rotation, a trigger max rotation. It's by default -20. I want it to be 25 here. Then we have our slide mesh. Here we get our pistol slide. And this is also very important. The origin of the slide should be the same as the pistol body, because now we can pull it back and see, okay, if the slide is pulled, I want it to be around here. So we can copy this X offset, set it back to 0. And then we can come back to our BP pistol and search for slide travel distance. It's by default -5. That's a bit much for the pistol. So I want it to be that exact value. And now every time we fire or pull slide back, we can pull it to a max of this value. So maximum to here. And here we don't have a blade on it. You could theoretically add a bayonet. This is also why we have the penetration hitbox, but you can leave it as it is. These things will get deleted as soon as we start. So coming back to the pistol, we have our variables. Here we have our fire rate. I'll leave this as the default values. Max projectile spread doesn't matter for the pistol because we're only firing one projectile. Then the recoil distance, this is how hard your recoil is. I will again leave this, but you can play around with it. Our firing modes, here you could add multiple firing modes if you had a firing mode selector. Or you can do it anyway, of course, you don't need a firing mode selector, but if you don't want anything for the pistol, for example, I only want it to be semi-auto, so I leave this as default, but you can also set it to single, for example, but then you would have to pull the slide after every time you fired. Set this back to the default values. And of course, when you have multiple firing modes, you can add another one as a semi and full auto. And for the full auto one, I want the firing mode selector to rotate on the pitch axis by -10, for example. This is how you can add those. I don't want them for the pistol, so let's delete them again. Then for the triple fire here, the max firing count is how many times it fires when we triple fire. By default, of course, it's 3 times, but you can also make it shoot 6 rounds or only 2. Then for the matching magazine class, we want our BP pistol magazine. Here we have our shell eject trajectory. By default, it is 45 degrees to the right. So out like this, and the shell eject force is 200. In my eyes, plenty, so you can leave it. Our slide travel distance that we set. Here we have all of the different sounds. I will set them real quick. And the firing mode. This is just if we change it. Actually, we don't need to set this since we can't change the firing mode on this pistol, but just if you wanted to. Just make sure that if you change them here, you also have to change them on the mesh. Now, here would be our animations. We'll come to those in a moment. Here we have things like damage. This damage is the melee damage, which is why it's in the melee category. So if you hit someone with the weapon itself, this is how much damage you do. Linear breakable is for the penetration, but this pistol doesn't have anything sharp on it, so you can ignore this for the pistol. The hit rate, how fast you can hit something. And the minimal damage speed, so the minimal speed required, this is about 2 meters per second. Weapon melee type is blunt. If it's sharp, then you still have the penetration hitbox and blade mesh, but we want it to remain blunt. Here we have our hit sound. For this, I'll use the concrete cue, the penetration sound. Never mind, we don't have to set it since we don't have anything sharp on it, but here you can set, for example, a slicing sound when you stab something. Also the decal when you stab something. Actually, I should move the decal, this penetration decal to decals, I just realized. For the hit decal, I want my hit decal instance. And VFX, we have the hit Niagara system. And then the same for the penetration, but again, we don't have this here. Decal lifetime 10 is fine. Fade screen is also fine for me. Like I said, you can just play around with it. That would already be it for the pistol. Oh, no, never mind. We have our magazine constraint because right now it's 1 meter by 1 meter, but we want to scale this down. Sorry, not the constraint, the magazine hitbox. We want to scale this down a bit. So I'll set it to 0.05 and I'll put it here. So as soon as the magazine overlaps this, it will be inserted. And we can also test that if we add our pistol to the world. And now as soon as we overlap it, it's inserted, and it even plays the sound. Now we can come to the animations. Here we have our control rig. Actually, I will open up our sequencer, open level sequence, and I will reset our keys just so the control rig is back to default, and then set all of the keys again. Now I want to attach the pistol to our mannequin body, and I will attach it to the hand R. And now we can reset all of the transforms. And now to add the offset, we want to switch into local mode and first apply a 180-degree rotation. And now we can move it to where we seem fit. For me, that would be around here-ish. Yeah, that should be fine. And now we can create the animation. I will quickly create the pose that I want it to be in, and then I'll be right back. There we go. Now we can save the pose. Animations. Actually, I'll create a new folder. Pistol. I will call this a pistol right trigger released. The hand rotation, everything doesn't matter. We only need the animation to figure out our hand position relative to the weapon, and we'll use the animation for our fingers. So even if you stretch it like this, it doesn't really matter. Now I want to create the grip animation, so I'll see you in a sec. And that's good enough. Now we'll bake this to animation. Set it to pistol, a pistol left grip. Save it. This is why in our code we only wanted to mirror the left grip animation when we are gripping with the right. So we only have to create the left animation, and then we can simply mirror it to the right. And same goes for the left trigger released and trigger pulled animation. This way we can simply mirror it. What we can do now, actually I'll show you because you don't have to watch me create every animation, and then the same for the slide. For the slide, you can use this position from the right hand and then simply set it for the left hand. So quick example, set it to here, somewhere like that, wherever you want to grip it. And then you can say if this animation, again, only for the left, and then do the calculations for the offset. But I'll make an extensive video on that for the fab version, because this video is already way too long. And at this point, I believe I have like 15 hours of footage or even more. So yeah, I'll make a separate video for this setup and how to use all of that. So now what we can do, we can get out of the sequencer. Now we have our animations that we want to mirror. Hey, it's editing me here. So there was supposed to be a whole setup for how we can figure out what the socket location and rotations are supposed to be. And while recording, I found an easier way to do it, which is good for you, bad for me because I spent like an hour here. But yeah, open up the sequencer that was created when we created the fist animation. And okay, here it's saved a pose from before, which is actually good because this is still attached to our hand bone. And here you can see the offset that we want to give it. So here we can go to our pistol body and add our first socket. This will be the handle hand R bone. And now what we want to copy paste these values into here to the relative location, because this pistol is attached to the right hand bone. So this is where the hand is supposed to be afterwards. Then for the rotation, we want 180 degrees on the Z-axis, the yaw. So we add this to the yaw. And now this was supposed to be from the grip. I just showed how you can add this to be your slide grip, but I will move it back. So yeah, for this tutorial, I'll say this is fine. This is where my grip hands is supposed to be. So now what I want to do, I'll go back to the outliner. I unparent my pistol and I reparent it, and now I want it to be on the hand L, on the left hand. Now if we go back to the details, we have that offset. So in our pistol body, let's create a grip and L bone, sorry, not R, L. Then here we can copy paste the values again. There we go. Now we have our left grip bone and our right handle bone. Now for whatever reason, I can't really mirror this using the mannequin. So, oh no, actually, sorry. Before we mirror it, we want to bake this into animations. So animations, I'll add a new subfolder for the pistol, and I'll add my first animation, a pistol trigger released right. And okay, this is a little bit unfortunate because before I only created this hand was still in its default pose and not here. That's so I do it as I would have done it before. Now I would have added the grip hand and then saved this animation again under pistol, A, pistol, grip, left. There you go. But I just now realized that you could in theory also use one animations where you set handle and grip, and that would be fine. And then what we also want to do to get our trigger hand animation, or our trigger pulled, I should say, we want to move the trigger and add its trigger offset to the pitch, which is negative 25. And now we can adjust our index finger to that. This I'll call fine for this tutorial. And now we can bake this again. Animation, pistol, A, pistol, trigger, pulled, right. There we go. In animation debugger, for the animation, I will choose the pistol trigger released right. Don't worry about these meshes. These are from the ammo bones that we set. And I also just realized this, you might think it looks weird because our hands weren't that close together when we animated it in the sequence player. This is because for some reason it chose the SKM Quinn simple and not our SKM Mani. You see here it's better. So for example, if you now want the pistol grip left, you can apply this. Let's not mirror it because it's the same animation, but get it. Now it's like that. However, we want this to mirror. Then we take our pistol, we attach it to our SKM Mani and to the hand L, that this, and from our x-axis, we simply need to negate all of the position values. So this 3.15 becomes negative 3.15. And all we have to figure out now is the rotation, which here is 180 degrees on the roll. And that would also be it for our handle bone for the left hand. So handle bone, handle hand L, and then simply negate these values. And here we want the yaw to be 0 and 180 on the roll. To get our right grip bone position, we unparent it, reparent it to the hand R bone, because you can see the pistol is still in the same location. And now we can copy over these values to our grip R. Actually, you can simply mirror or negate, I should say, the location values. They should all be the same. Check, yes, they are. The problem lies with the rotation. So the rotation values, we want to copy these. Although even with the rotation, sometimes it's weird. Sometimes you just have to add or subtract 180 degrees from X and Z and just negate Y, but it's pretty awkward, this whole thing. So yeah, I recommend you do it like that. And then of course you would also create your slide animation and do the same for the slide. However, the grip locations for the slides, they are on the actual slide mesh. So you would go to the slide mesh and set up these bones here. What I will do, I will also set up the magazine bone, because that's where the magazine is supposed to be. And here I want the preview mesh of the pistol mag, just so you can see where it is. Now, fortunately, while modeling, I made sure that they're already in the correct position. However, for a rifle, for example, this won't be the case. If the magazine bone is in front here, then you want to make sure that this bone is in the correct position where the magazine matches where it should be. But for this, we can just leave it as it is. Then we also want a muzzle bone to know where to spawn the bullet and where the muzzle flash should be. Try to align this in the middle somehow. There we go. Yeah, that's it for the bones on the pistol mesh. One more bone that we won't need on this mesh, but we'll need it on the slide. Remember, the slide has the same origin as our pistol, and for every other mesh, it's the same. It will also be like that for the rifle, that the slide has the same origin as the body. This is our loaded ammo bone, and here I'll use the pistol ammo, and I will align it with the barrel of the pistol. I want it to be approximately here. And unfortunately, you can't copy bones for whatever reason. However, I am going to copy the relative location, go to the pistol slide, add another bone, call this loaded ammo bone, right click, paste, and now it is exactly where it should be. And then you can delete this bone here again. There we go. Of course, I didn't add the grip hand bones for the slide, but it's the same principle. You create the animation first, you mirror it. I know it's confusing at first, but after you've done it sometimes, it will get easier. In this video, I confused myself because I suddenly realized all the calculations that I did were obsolete because you can just reattach it. I don't know why I didn't find that out sooner. Must have been late at night when I came up with that solution. But yeah, now there are only two things left. First, Penetrable Actors. This is pretty easy. All we do, we get a shape. Let's get a cube. I'll turn it into a wall, and I will use the grid gray 2 material. Now, to make this a penetrable actor, we simply search for tag, add an actor tag, penetrable, and that's it. Hey, this is editing me here. One thing that I forgot, for the penetrable actor, for it to actually work, you have to make sure that generate overlap events is set to true. Otherwise, it will not work. What I do want to show you is how you can add a weapon that can penetrate. So add new blueprint class, weapon base. We have our weapon base. We'll call this BP knife. And in here for our weapon mesh, we have the knife body and the knife blade. Here I separated the blade mesh from the body because when you want to add a bayonet to a pistol, for example, and you want it to be attachable, this way it's its own mesh and you don't have to export a pistol mesh that has the knife already on it. Then what we need to do, we need to search for our variables, our BP knife. And of course, set all of this up. I won't do it right now just to save a little bit on time, but we want the weapon melee type to be sharp. Otherwise, our blade mesh and penetration hitbox and constraint would be deleted. And our penetration hitbox, we want this to be aligned with our blade. So I'll scale it down. And I would recommend that in your mesh, you make sure that the collision, go up here to show simple collision, that is somewhat accurate, because if your knife will collide before your collision box can overlap anything, then it won't be able to penetrate because this never overlaps anything that it could penetrate. So yeah, that's just as I noticed. And that would already be the knife. Then for our climbing, another cube. If you don't set a physics material, it by default has the friction is 0.7. And once more, where we have our red, over here we have no friction and only friction. Now, what we want to add, this for now, I copied this from the other project, so I want to show you how you can do this. You can just create a folder where you want your physical materials to be. Right-click, physics, then you have physical material. Select the physical material, and I'll call this PM no friction or PM slippery, whatever. And here we'll set the friction to 0. Duplicate this. PM lots of friction, and here the friction is supposed to be 1, meaning we won't slip at all. So there's two ways you can apply this. You can either select the object and search for material, and then here you have physics material override or phys material override. You can do it that way, or you open up your material and here you search for physics material, and you have your phys material, and you can set it here. So this should be lots of friction, and my red one should be no friction. Now, if you climb on these, here you won't slip at all. Here you will slip a little, and here you will slip a lot. And just make sure if there's something where you shouldn't slip, you either override the physical material, or if you don't want to slip at all, you can disable that in the character. Wow, that was a lot. If you made it through all the way till the end, I applaud and thank you. When you're already here, you might as well want to subscribe to not miss any future tutorials. Let me know in the comments if you need any help, and I will see you next time. Bye!